In this video, we will see how to install Python in Windows. First, let's go to the Python official website. Search for Python in Google. The first link is the Python official website. Let's go into this website. Now let's go to downloads. Now we can see the download Python 3.13.2 option. Let's click on this link. Now it has downloaded the Python installer. Let's click on this. So now the Python installer is open. We can choose the first option, install now. And before that, we have to choose this option, add Python to the path. So install now. Let's click on install now. Installation has started. Now the setup installation has been completed. Let's click on this option. It will ask for confirmation. Choose yes. And then we can close the installer. Now we have installed Python. Let's verify if the Python installation got successfully done or not. Let's go to the start menu. Let's go to the command prompt, cmd. Click on command prompt. Open. It will open a command prompt window. Now let's type Python here. Enter. Now it has gone into the Python shell. Let's come out of this. Press Ctrl Z and then press enter. Now it will come out of the Python shell. Let's type Python version. Now we see the version of the Python is 3.13.2. So this is how we verify Python is installed or not. So this is how we install Python. So today we'll start with Python. Basic syntax of Python and all the data structures and variables within we will look into. And then we will visit object-oriented programming. I'll give a brief intro on classes, and then tomorrow we'll discuss about object-oriented programming. So first thing, I'll just form this repository. So you will know that GitHub desktop application. You need to install this. VS Code. All this you need to install. And then you will need to install Python, python.org. If you go here, you can download the binary for your respective operating system, and then you can follow the instructions. So I have Python installed already, so I'll start with running this repository. So I've cloned this repository. Let me, here it doesn't have. Using there, we can clone this, open GitHub desktop. This is my GitHub desktop application. I'm going to clone this repository. I'll use this as a basis for all my Python code. So I can open Visual Studio from here. Here I'm going to initialize a Python node. So I'm opening terminal. If you go to terminal, new terminal, open, and there is a shortcut for that. You can do Control Shift backward. I'm going to use that. Now, if I type in Python, I can enter into the Python shell. If I want to come out of this Python shell, I can do Control C and enter. So there is a package manager for Python called pip. So I can install packages with pip install Jupyter. Let's say this is a utility for working with Python files. Let's install Jupyter. This is the path variable is not updated with this location. Let me add that. So it's installed, but in order to execute Jupyter scripts, I need to add these paths into our system environment path. Let me share control panel. Basics. So when I enter Python, it goes into the Python shell. First thing that we need to look at is how to do a print. Let's do world. If you see this is called read evaluate print loop, REPL. So whenever I enter a Python statement, it will execute immediately. So compared to C and other languages, Python is an interpreted language, whereas C and Java all are compiled languages. So right now in Python, as soon as you write code and enter, it will interpret and execute that particular statement instead of compiling into a binary code. So it's faster to prototype, but performance-wise, it's a little lacking compared to the compiled languages. So first thing I'm going to look at is, this is one way to execute Python code. So let's say I want to execute Python code through a file. So I'm going to create a new file. Hello. Fine. So in files, the extensions specify which data this particular file will contain. So py extension is used for Python code. This data I'm going to do level from so this one I can execute through the Python interpreter by issuing Python. This is this read evaluate print loop, but except that all our statements are put under one file. So this is statements. There are things called functions. So this is a basic unit of Python. I'll go into how to define a function and all that. I'll just give you a quick glance of function. This is a function. Print the same statement. If I want to execute inside a function, I'll just move this to inside a function. So note here that I'm indenting code within this function. So Python doesn't have semicolons as the ending statements for an ending character for statements. So Python interpreter interprets code based on the indentation level. If I indent one part of the code inside that definition, it means this is a kind of a block. We are creating a block of code. In other languages, if you see C language, so we create blocks in this CR7. We create opening bracket and closing bracket. So in Python, we use indentation for doing the same thing. So we are actually creating a block. So I want to add one more statement here. This is another line. All this will be under the same indentation level. This is out of the function block. So this statement is not part of the function. Let's say I want to execute the function. This is a function. How do I call that? Just throw it like this. So this function gets executed, which prints these two lines, and then this prints this line. If I put this line after this, first this statement gets executed and this gets printed, and these two lines get printed. Let's do it. This is how the function works. This one got executed first, and this function got called and got executed. So that's a small glimpse into what functions are. We'll go into functions and classes and methods. Functions, methods, what's the difference between a class, function, and a method. So let's go to our Python interpreter. Let's execute PWA print loop. So in computer science, if you say X is a variable, so I'm giving the value 5 to this variable. How does computer store this value? Is through memory addresses. So this particular X variable will have a specific address assigned by the interpreter or by the CPU, which will have the value 5 in it. And if I have same thing here, X is now having a specific address. Addresses will be based on the memory architecture. You will have a number assigned to it, and the value of that address, the value that is placed in that memory address, is 5. If I do print X, CPU is going to access that particular location of X, the address, and reads out that value in that address and prints it out. That's the basic functionality of variables. So these variables can be different types. Right now I've stored it as a number. X can be a string or a number. It's a dynamic language. Python is a dynamic language. It doesn't require us to define the data type while declaring the variable. You can assign the value and it will automatically determine the variable type, value type. So let's say I'm going to assign a string. The strings are defined in Python as like this. They use double quotes or single quotes. This is same as double quotes. So now if I do print name, It is a string. So if I want to know what's the type of this variable, I can print it with the type of name. It is a string. So if I do type of, so now we know what's type of the value that we are storing based on the variable that we have, based on the value that is assigned to it. We have the type dynamically found out by the Python interpreter. So it's name variable is assigned with string and x is assigned the type integer. And we also have, so what about the numbers which are decimal values? Let's say, take example of 1.5. So I'll just print the type of 1.5. It's a float. It's a floating point number. So why do we call that a floating point number? Is because let's say I have 1, 2, 3, 4, 5, 6, 7. This is one way. Let's say 1, 2, 3, 4, 5, 6, 7. Dot 7. So this dot is actually floating. The computer does not understand where this dot is. It interprets the numbers and then the position of the decimal point. So the decimal point is actually floating. That's why we are calling it as a float instead of a decimal. So similar to this, if we had background of math, we have like complex numbers. Let's say square root of -1 is a complex number called I. So in computer terms, it is called J. So if I just print 1J, it is 1J. So if I print the type of 1J, it's a complex number. This is also one of the data types. But most of the times we won't be using this data type in our day-to-day work. So I can do complex number operations also here. I just try to multiply 1J with 1J, which is going to be -1. It displays -1 plus 0. So this is a complex number. -1 is the real part of it, and this is the imaginary part of it. So this is how we do complex math. But this is all we won't be using most of the times, our day-to-day programming work. Similar to this, we have strings. Let's say string 1. I'm defining string 1, and I can do operations on string 1. I will append string 1 with string 2. These are two strings. So I'm just summing these two. We'll see what happens. So it's actually appending or concatenating these two strings. When we do 1 plus 2, it does sum. When we do string plus string, it does concat. So this is dynamically determined by the interpreter what to do with this operator. This is called the operator. We have data types. We have seen integer data types, float data types, complex numbers, and strings. Now let's see booleans. So booleans is true or false. Let's say this is true, and Python has true and false. These are the two different boolean data types. So if I just try to print true, it doesn't. True does not exist in Python. The actual boolean for true is capital T, true. Boolean for false is capital F, false. But one thing we can do, true is actually a variable name. So just like X or A or some I name, define true as a variable name that has true as the value. What will be the type of true? It's a Boolean, because I've assigned value true to the variable true. So this is kind of confusing, but don't worry. So just use true, capital F false for all your programming in Python. Let's now visit different types we have seen. Now, how do I deduce booleans? So if I do compare two variable values, 1 equal to 1. So this is actually a new thing. If I say a equal to 1, this is an assignment, whereas I do 2 equal to signs, it is a comparison. 1 equal to 2, this is a false. This is how we compare two values. And then this is basic data types. In Python, there are complex data types also. Let's say in C and other languages, we have arrays. Instead of arrays, we have lists in Python. There are two Boolean data types called true and false in Python. So how do I deduce a comparison versus assignment? Yes, let's say a equal to 1 if I do. It assigns value 1 to variable a. Let's say if I do a equal to 1, this is a comparison operation. This is a true statement, which means it's actually getting the value of a and comparing whether it is equal to the value 1 or not, whether the statement is true or not. Is it, I'm asking the interpreter, is a equal to 1? Here I'm actually assigning 1 to variable a. And similarly, if a equal to 2, I'm asking whether a's value is equal to 2 or not. So that has to give me a false as a written value. That is what it is, because I've already assigned value 1 to it. So if I assign a equals 2 now, and if I do the a double equals 2, it says true. This is comparison, this is assignment. Okay. So now we have seen the basic data types of Python. There are complex data types called arrays and dictionaries. Arrays, we call it in C language, but in Python, it's a different name. So these are called list items. Let's say I'll define a list. That list is going to contain 1, 2, 3. It's a list of items. If I do type of my list, this is actually a list. So this list can contain nested lists also. My list actually can contain one number, one string, one boolean, one float. This is all valid. But in C, arrays do not allow having different data types. This is all. If I do print my list, it will print actual values. And similar to this, we can have nested arrays, nested lists. I have one list. Inside that, I will have one more list. 1, 3. We have one more list called 5, 6. Or I'll have one more list with strings in it. This is all valid. This is all valid. If I print my list, it has a list has a specific property called length. You can find the length of a list by length operator here. The length of this my list is 4 because it has 1, 2, 3, and 4 elements. This doesn't count the nested lists. So as long as my list is concerned, it only has 4 elements. Those 4 elements can be lists, underlying lists, or it can be dictionaries or any other data type. So that's about list length. So this is one type of complex data structure. There are something called sets. So whereas list is a, say, this is a list. Try to print the list. This shows all elements. There is something called set. My set. Sets are defined like this. 1, 2, 3, 4, 5. I'll set again 1, 1, 1, 3, 3. Let's do print my set. Let's see what's the difference. It's only printing 1, 2, 3, 4, 5. It's only printing unique values. So in a list, we can store duplicate values, whereas in a set, we cannot store duplicate values. A set is a unique set of values. Let's try setting, try a set having multiple data types. Print my set. It's only storing unique values. So that's about sets. Let's try getting the length of a set. I'm going to define a set 1, 2, 3, 4, 5, 3. It's 5. Let's make comparisons. Let's do comparison on both lists and sets. There is a list called 1, 2. I'm going to compare if this is equal to 1, 2. Okay, this is true. What if I change the order? False. Lists are order specific. So if the order changes, they both do not equal each other. Let's see how about sets 1, 2. Also have one more element 3. I'll set 1, 2, 3. This is 1. Lists and sets do not differ in this. Let's say 3, 2, 1. Enter. This is also true. So order does not matter in a set. Order matters in comparing a list. Similar to lists, we have something called tuples. A tuple is generally defined like this. Similar to lists 1, 2, 3, but except that it will have this kind of syntax and print A. This is a tuple. Okay, let's come to the definition. What's the difference? I have a list called A, same thing, 1, 2, 3. And I can add one more item to B. Let's say B dot append of 4 if I do, and then print B. It is 1, 2, 3, 4. It has appended 4th element into it. Let's do the same thing with this. Not allowed. Basically, a tuple cannot be edited. Once defined, it cannot be edited. That is having tuples. And why that is not editable, or why do we need that uneditable feature, is for optimizations. So when I'm editing a list, the memory optimizations we'll go for a toss. So whenever we add one more element, it has to relocate the data and store that extra information where the addresses of each of the elements are. If it is split into multiple locations in the memory, it will have to store two addresses for this. So it's an internal mechanism how the interpreter converts this code into machine code. So whereas in a tuple, if I define it once and I don't have to store extra information for me to retrieve or manipulate as that tuple. So if I have to make it editable, I will have to make some more metadata stored in the data structure. That extra information is not required for a tuple. That is why it is efficient, memory efficient. So when we have large sets of coordinate information, let's say especially where we use these tuples is for storing XY coordinates, let's say 1, 3. So basically this XY coordinates are usually XYZ coordinates, both. Even in 3D programming, we have XYZ both, all three coordinates. This is especially very useful in game programming. Not just a game programming. If you want more optimized code, memory efficient code, you can do this. You can use tuples. Similar to this and sets, we have length property for tuple also. Same thing. There's no difference. And now comes the dictionaries. So dictionaries are a little bit more similar to our dictionaries. Dictionaries store words and their meanings. Similar to that, we store keys and values. So let's define a dictionary. So dictionary syntax is like this. It's similar to set syntax, except that we will have keys and values. The keys are always strings. Apple. I'm going to store something like that. Where something with dangerous animal. And enter. Let's see length of my dictionary. There are two elements in the dictionary. Now let's access what is now. I'm just looking for this word, apple. I'm trying to see what's the meaning of that apple. You can store anything in here, not just strings. You can store any even a list or another dictionary also, a nested dictionary also you can have. So it's just that key and value should be there. The value can be an integer, float, list, dictionary, tuple, or whatever you want to have. So the key should always be a string. Let's see now. Let's access something that is not there in the dictionary. Okay. This key is not defined in any of these keys here. It's not a frozen error because this dictionary does not have an element with the name method. Okay. Now I have the dictionary and I will redefine one more value here. Apple, same key I'm going to use. And I'm going to use something like, sometimes it's green. And let's print what is in my dictionary. Access my dictionary. Apple. What is it? It gives the last entity. So when I'm appending a new entry, it is actually replacing that particular key previously defined. Let's say I will define dictionary. It's nothing but saying dictionary of pair and want to do something like here. Some text replaced. Now if I print my dictionary, apple got replaced by this and pair got replaced by this. This is how we manipulate dictionaries. So this is pretty much the data structures in Python. So what we have seen into basic data types like integer, float, string, and then complex structures like list, set, dictionaries, and tuples. And complex data types also is there as a basic data type. Now let's see how to compare two values or two variables, or how to do arithmetic and comparison operations. So let's see arithmetic operations first. So I will define 1 plus 1. This is in general. In every language, this is same. And let's do multiplication. Multiplication is specified by star asterisk. This is how we do multiplication. If I do 2 stars, this is actually raising the power of 5 by 2, which is like 5 square. And 5 to the power of 3, this is how we get it. Double star means it's a power. And let's do a division. By default, the division is going to give you a floating point number, because the remainders will not always be zeros. So if I do 20 divided by 6, it gives decimal values also. That's why by default in Python, it is by default is going to return a float, any division. So if I do 20 divided by 6, this is an integer division. It doesn't take care of the decimal values. It only gives what is before the decimal. And if I want to see what's the remainder, let's see 20 modulo operator 6. This is the remainder. So similar to these operations, we can do operations on strings also. Just like we have seen earlier, string 1 plus string 2 gives a concatenated string. 5, 2 plus 1. This doesn't give 2, but it actually gives 11 because these two are strings. Similar to this, I will do operations on a string. This is a string. I'm multiplying it by 4. Let's see what happens. It's actually repeating this 4 times. This is a convenient way to print for formats or designs. And if I use 1 plus 4, what happens? Goes added. So string and the number is cannot be added. And now this is about arithmetic operations. Let's see comparison operations. Just like we have seen, 1 equals 1, double equals 1. This is a comparison operation. And 4 less than 5, this is true. 5 less than or equal to 5, this is true. 5 greater than 2, 5 greater than or equal to 2. This is all about basic less than, greater than, equals, greater than, equal to. All this we might have already seen. And there is logical operators called and or, and or and not. So how do I do those? True and true. This is like if you have seen logical operators, you would have already visited logic gates, truth tables, true and false, false and false, false and true. All this combinations we can use. And true or false is also true. It's the only scenario when or will fail is both when there is both are false. If both are false, then it becomes false. When and true will become true and false will become false, everything else will become false. False and false becomes false, false and true becomes false. Okay, say I have a sentence. My sentence. This is a statement. Let's say if this will say the syntax and all. I will show you sometime the if conditions and all that. If publish in my sentence, and this is a statement wrote, and then I have this, and if software engineer in my sentence, this is a statement for software engineer. Okay. If publish in my sentence and software engineer in my sentence, this is a statement about publish in software engineer. Let's say instead of software engineer, I'm going to use something like test engineer, or let's say locomotive engineer. Is not executing because this is true, but this is not true. This block of code gets executed only when both these statements are true. So if you consider true, this results in true and this results in false. True and false becomes false. So if condition works only when this condition wholly becomes a true. I do false. Okay. Okay. See, this is kind of true or false will result in true. So if true means it will go inside this loop. Let's see if block. Let's visit the if condition. If true, inside the if. If false, inside if. This doesn't get executed because this is false. So the syntax or logic of if is if something is true, then execute these lines is what this means. If, which is false, if some condition, do something else. This is what if syntax is. If something is true, some condition is true, then execute these lines. Understood? So we have seen and or, true and true. So if true and true, print O, else if true and false, print true and false. This actually does not get executed, this statement, because true and false will always result in false. This if condition or else if condition works only when this statement becomes a true value. And if this thing gets executed, if true and false, this doesn't get executed. Yes, this only is resulting in a false statement. So there is something called not operator, which negates true values. If I do a not on true, it becomes false. If I do not on false, it becomes true. If not true, print. True actually is becoming false. So if condition gets executed only when this entire thing becomes true. If not false, print false. If not false, actually resulting in a true statement. If true means this block will get executed. It can be confusing once we get into coding to see how things work in practical. You'll understand. It's okay. We're just covering the basics. So apart from arithmetic, comparison, and logical operators, we have membership operators. So let's take an example of a list 1, 2, 3, 4, 5. If I want to find out if specific element is there in a list A, I can find out if, or like I can say like 4 in A. This actually checks if element 4, value 4 is there in this list or not. Let's say I will try 10 in A. This returns false because 10 value is not found in this list. Something similar, we can do this membership operator for strings also. Cat in my pet cat. This is true. If I just do cat not in my pet cat, so this checks if cat is not there in this particular string or that statement is false because cat is actually there. We are trying to see if it is not there. So that gives false. So this is about membership operators. Now let's look at if-else conditional statements. So we have already seen that. So I'm going to define a value, assign a value true to A. If A, I want to print something. It is true. And I will execute one more statement there. So let me also print this. If A is true, both these statements get executed. And this gets printed. If you see here, this statement gets executed. These two statements get executed only when A is true. If I now change it back, I will change A to false. And same code I'm going to execute one more time. Only this thing gets executed always. If A is false, these two statements did not get executed. This is how if conditions work. Something similar, if I define another condition called else, print it is false. So if A is true, this gets executed. Otherwise, this gets executed. And this gets executed always. That's it. It is false because A is false. We have made A as false. This is getting executed. Let's define one more value. B as true. A as true. Let's define the same function. I'll just add one more nested if condition here. If B print B is true, and execute now. So it is true. This thing, these two statements, and also this statement got executed because both B and A both are true. So instead of this, I can actually have if A and B print A or B. Oops. This is how we use AND. So something similar. We instead of having nested statements, we can make use of loops also. Let's say I will use a list 1, 2, 3, 4. I want to iterate through all the elements in a loop, all the elements of A in the loop. I can do it with for item. So this is just a value name I'm giving to. I have to use an iterator in. So we have used in as a membership operator. This is a different context. This is part of the for loop syntax. This in is not membership operator in this context. But item in A, print item. So actually lists, dictionaries, and sets, dictionaries, lists, and tuples, all these are called iterables. Iterables means we can actually iterate through each of the elements and do some operation on each of that element. So as long as we have an iterable item, we can use in to loop through all those values in that iterable items. So for item in A, if I'm printing here, it prints all the values. It loops through each of these items and prints them. Similar to this, we have a while loop. While, let's say I'm defining a value A as 0, while A less than 5, print A, and then increment plus equals 1 actually means A equal to A plus 1. So this is one way to do it. That is a better or short way of doing it is A plus equal to 1 means this A equal to A plus 1. I'm just going to use this old syntax itself. Just all the confusion. Later we'll start using the other syntax later. So this loop actually loops and prints through A and increments the A value. Every time it loops, it will increment by 1. So 0, 1, 2, 3, 4, it will print. So this is how we loop through while loop. And next thing is defining functions. So for this, I think we should make use of this. I've already shown you this. If I am executing a print, hello, I'm actually calling a function called print. This is already predefined in Python. Print is a function and hello is the argument to that function. So we are actually saying to the interpreter that you need to print this hello string out into the console. That's the function we are executing. So we can have our own custom functions defined in Python, which does its own operations. So I'm going to define a function. How to define a function is through def keyword multiply by 3. I'm going to pass a value to it. I'm going to store it in a variable called val. Inside that function, I'm going to see this indentation. This is very important. If you don't indent code, it will throw error, or otherwise it will have logical errors in it. And I'm going to return 3 times that value that we are passing. I just defined a function now. I have not executed that function. When I did print hello, I've actually executed the function. Now, in order to execute this function, I need to call that function. Multiply by 3. I'm going to give a value of 4 to the value. It's going to return 3 into 4. 12. And similarly, I can define one more function, def multiply, which this time it will accept 2 parameters, val1, val2. This is how we define. A colon should be there at the end. And I'm going to return val1 to val2. And I'm going to do multiply 3 and 4. So now let's do something with lists. Let's define a value variable A with list 1, 2, 3. We define a function that will append floor to it to accept a list. My list dot append of 4. And now I'm going to do append 4 to which list? To the list A. Now in A, it has manipulated this list object and added element 4 to it. And let's see. This is how we manipulate lists. Even dictionaries you can pass to functions that will in turn edit those dictionaries. So how about having return values? Now we have had a state function which returned return values. Let's say if I store value 3 equal to multiply of 3 over 4. Val 3 now contains the result of this operation. If I am returning a value, this value can be stored in a variable again. Value 1 into value 2, 3 into 4 is going to be stored in val3. If I print val3, it's going to have value 12. Now, what about print statement? Print hello if I do. What's the value it stores? Let's say value 4. Also print of hello. Now let's access file 4. Print file 4. It's actually a null. That means print statement is not returning anything. By default, any function that doesn't return anything will return none. None is a special type in Python. Let's see the type of none. This is called none type. If nothing exists, it is a none type. It's like similar to nil values in Java and C. So null spell. Let's try adding one value to none. Adding values to none is not allowed. This is about the basics of Python. So we will define classes tomorrow. So just a quick peek into classes. We define classes with class keyword. So classes are very useful for object-oriented programming, and an object is what we consider anything in the world, anything, an abstraction. Any object has its own attributes. All this attributes and methods, functionalities of a specific object, we will program into a template called a class. So that we will look. Let's say if you take an example of a dog, what it does, how many legs it has, all those things will be part of the class. So this is how I define a class. There are some attributes and methods in class. Just a quick peek I will do. We will discuss in depth into classes tomorrow. I'm going to initialize this dog. The syntax I will explain in some time. We will visit tomorrow. Example. So I create a dog. And this is an object. How to print this dog object in a human readable format and all that we will define. So tomorrow. So how do we exit from this REPL? Is through Control C and enter. Or if I go here, do exit. Exit. Yeah. Exit function. If I exit it, I'll just quickly go over what's been discussed in the previous recording. So first thing is we have a Python interpreter. So, okay, why do we need an interpreter is something I need to give a context on. So computers will understand only binary language, right? Basically, a CPU can understand CPU instructions. CPU instructions will have specific number codes. Those number codes, for addition, there will be one code, and for subtraction, there will be one code. So computer is nothing but an advanced calculator. So in calculation, in our traditional calculator, we just do arithmetic. So whereas computers can do complex calculations, not only arithmetic, it's more or less complex arithmetic. So in order to communicate what needs to be done, let's say if I want to find out the square root of a number, how do I instruct a computer? There is a way to, all these mathematical operations can be programmed into a computer through some specific format. So we can actually write binary code directly, but it is not easy to write. So in the initial days of computers, we used to have punched cards where we had to write ones and zeros, punch If there is a hole in the punch card, that means it's a 0. If there is no hole, that's a 1. So addition, add, and an instruction, it will have one specific number assigned to it. The CPU understands that specific number. So as the technology grew, we had to write a complex set of instructions. Using binaries was not even feasible. So initial stages, we have discovered the assembly code. So assembly also is kind of a symbolic language. On top of it, we have developed advanced source code, meaning English-like language, an advanced programming language. So in order to convert, basically, computer just means the CPU. CPU does not understand our even source code, our C code also it does not understand. So there should be a middleman who converts a plain English, kind of plain English. C is kind of an English, but it's a symbolic language. So a middleman is called that middleman is the compiler who converts our C language code into binary code that the CPU understands. So when a CPU is working on some problem, executing a program, it actually is fetching instructions from the memory. That instructions is all in the binary format, ones and zeros. And if it sees an add code 1001, let's say, for example, is symbolic way of saying add two numbers, that's what it will do. So for us to convert from a traditional English-like language into a machine language, which is ones and zeros, we need a compiler. So there is another thing called interpreter. So the difference between a compiler and an interpreter is that if you write a program, compiler will entirely read the entire program and converts it entirely into machine code. So during the process, it will optimize some set of instructions. Let's say if I write redundant instructions, it will compress that and make it into a single efficient instruction set and converts that into the machine code equivalent. So whereas an interpreter reads our instructions line by line. So whereas a compiler reads the entire code that we write in a file and then compile it into a single binary, and the interpreter reads each line one by one and converts that specific line of instruction into the machine code and executes it on the CPU. So that's the difference. So there will be an intermediary file generated when we compile the code. So whereas in interpreted languages like Python, we don't have an intermediary file. There is no compiled code. Plain old Python code gets executed line by line by the Python interpreter. So it just reads. If it sees a print statement, it will immediately convert that into machine code equivalent and passes it onto the CPU and executes it. So whereas a compiler will read the entire file, compile it entirely into one single set of stream of instructions, and then passes it into the CPU to execute. So having said that, let's try Python. So Python, for us to install Python, we need to go to python.org. In the browser, we need to go to this www.python.org. You can install. I think when we were discussing about the npm Node.js, you would have already got those binaries installed, so you don't need to install it again. If you watched my previous video, you can get the instructions on how to install Python. So just like npm for Node.js, Node.js has a package manager called npm. Python also has a package manager called pip. So I can install libraries or external packages using pip. So if I want to see what all packages I already have installed in my system, I can do pip list. These are all packages I have installed in my system because I've been using this system for long. So I've installed so many packages which I use for so many purposes. So if I want to install a new package, I can do it through pip install, say Jupyter. Jupyter is a notebook. It's kind of a markup plus Python code. So it's a shareable Python interface. We'll go into Jupyter later. So firstly, Python code can be executed in two ways. You can directly execute Python code inside the Python shell. So if I type Python, if I want to see if Python is installed or not, I will just do Python version. It will give me, if that is installed, it will show the version. Otherwise, it will say that there is no command called Python. Okay, I can go, first way to execute is I can put the Python interpreter inside the Python shell. If it shows the greater than symbols, it is Python shell. So I can write code here. Hello. And each line, it gets executed immediately. This is one way to execute. So I'll exit out of this shell, and now I will show you how to execute a Python file itself instead of typing one line at a time. So for me to get out of this shell, I can type exit. I can call exit function, or I can do Control Z and then enter. So this will come out of the Python shell. Let's say I delete this file and rewrite. So for me to write a Python code, I need to create a new file, name.py, or it can be any name, my name.py, my script.py, something. So .py means it's a Python file. It's not strictly necessary, but it's a convention to keep the extensions according to the language that we write the code in. So my script.py, inside that, the same instruction I can write here. Print. Okay. And similarly, I will write one more line. So there are two instructions here. In order to execute this script, I should do Python my script.py. So this will execute both these lines. Okay, here we have output. The difference between a compiler and an interpreter is kind of, whereas a compiler reads the entire code and converts that first into a binary and then passes it on to the CPU. So what Python interpreter is currently doing with the script is it's reading one line and then printing it. It's reading the second line and then printing it. Let's say if I do some mistake here, print X. Let's see how this behaves. And it has printed hello, and then it failed. So this shows us that Python code is not compiling the entire thing. It's just executing line by line. So if it sees Python hello, print hello, it's printed it, it has printed it. And when it saw print X, which is kind of an error because X is not defined yet. We haven't assigned any value to X. So that's why it is failing. So till we get into an error, it keeps on executing. So if you do the same mistake in C language or any other compiled language, when I do compile the code, this will not even compile. So the compiler will complain that, okay, you have used X, which is not defined. So it cannot convert into binary. So that's the advantage of compilers. So while Python is useful for quickly prototyping software, So quickly write it. So every time we change the code, we don't have to compile it and then wait for the compiler to do the conversion. We can directly execute the script. That's the advantage of Python. So, okay. So this is a way to execute Python scripts. All right. So we have seen how to execute through shell, Python shell, and how to execute through the command prompt. Now I'll go back to the shell mode and show you more about the language features of Python. Let me go into Python shell, Python. So any value, if you are familiar with algebra, any variable x can be defined. So those variables is what is used for all kinds of operations in computer languages and computer science. When I say x, I'm defining a value 3, give a value 3. What the computer is doing is it's defining a memory space for variable called x. So all the data is stored, all the programs, even the data, everything will be stored in memory. So hard disk is permanent storage, whereas memory is where the instructions and the temporary data that the CPU is working on is stored. So any program that we write, if I save this file, it's actually saving into disk. But while executing this script, it's actually fetching this file into the memory, and from memory, it is reading the instructions and passing it on to the CPU. CPU is actually reading from the memory, not from the disk directly. So the operating system is actually loading this file into memory while executing this Python script. So when I defined a variable x equal to 3, so what the computer or the interpreter or the CPU does is it will define a memory address, it will assign a memory address, and x represents that particular memory address. And in that address, the data stored is 3. And now the memory, let's say x has had a memory address. This memory address is all defined by the operating system and the CPU. So each of the locations, every byte of information will have a specific memory address. So once we have defined x, so what it did is it assigned a memory address to variable x and storing the value 3. If I do print x, what it is doing is it's getting the memory address of x and going to that location and reading that data which is stored in that particular location of system memory and printing that out. That's what the underlying thing that is happening here. So whereas here now we have defined x as a value 3. So this is an integer. So Python is a dynamic language. We don't need to specify the type of the data before assigning to a variable. So in C and Java or in any other language, some languages, you have to predefine what's the type of the variable. So what kind of data does X store? So we have to define it as integer, float, or string or something. So in Python, you can dynamically assign and you can change the value of X to a string also at a later point. So Python interpreter will dynamically change the type of the value. So let's say if I want to find out the type of X, what's the data type of X? I can type it down, like find out with this type X. It is actually an integer. Let's define one more value. This is a variable. Instead of X, I'm just using the variable name as name. And for this, I'm going to use my name. In Python, we can define strings with single quotes or double quotes. Both are equivalent. And if I do type of name, it is string. str is a shortcut for string. And there is floating point numbers. This is integers, and we have decimal numbers, right? So 1.2, 1.3 like that. Let's say I want to see what's the type of 1.5. It is a float. So why we have that name is because 1, 2, 3, 4, 5, 1.2, 3, 4, 5. Here, if we see that this dot is floating around, these are all integers, and this point is floating around left or right based on the value of that. So that is what floating point means. And we have floating point numbers in Python, and there is, if you are into mathematics, there is complex numbers and real numbers, right? So complex number is I, represented by I, and it's a square root of -1. So I into I will become -1. So in computer science, I is actually named as J. In Python, it's defined as J. If I type 1J, it is a complex number. If I do type of 1J, it's a complex number. So till now, we have seen integers, strings, floating point numbers, and complex numbers. And there is something called booleans in Python. Booleans are true and false. These two are Boolean values. Only two values are allowed. And there is simple calculations and comparisons, just like 1 plus 1. Let's say I do string operations, string 1 plus string 2. It appends two strings. So the same arithmetic operation, if I do it on strings, it will append the strings. So let's say I can send something to A to 2. And if I want to see if A is equal to 2, how do I compare if A is equal to 2 or not? So I've already assigned 2 value to A. If I do double equals 2, this actually means this is checking whether A's value is equal to 2 or not. It is true. Let's say if I type 3, actually we have stored value of 2 to A. And this statement is checking if A is equal to 3 or not. It's not correct. So that's why it's giving a Boolean false. This is very useful when we are writing conditional logic. If upon some condition, do something. Upon so and so condition, do something else. Okay. So we have comparisons, and we'll go in depth into arithmetic operations and comparisons. So we have seen till now the basic data types in Python: integer, float, decimal. It's a float, complex number, strings. Now there are complex data structures in Python. Those are lists. Let's say I need a list of items. I'll define a variable called mylist, and I'll define 1, 2, 3, 4, 5. 1, 2, 3, 4. Then I'll print the list. Okay, this is a list data type. So the list data type can have numbers, strings, booleans, or other complex data types. Nested lists also you can have. If I do type of my list, this is a list data type. We have a specific function called length of list. Length function on my list, if I call this, it gives 5. So this actually is counting the number of elements in a list. 1, 2, 3, 4, and 5. This entire thing is counted as one parent level object. So if I want to access a specific object, let's say the index actually starts with 0. My list on element 1 is the 0th index. It starts with 0, 0, 0th index, first index, second, third, and fourth. If I access my list of 2, this gives string 1 because 0th index is 1, 1 and 2. This is the second index. If I want to access the first element, I can do it through my list of 0. Let's say I want to access this last one, 1, 2, 0, 1, 2, 3, and 4. If I do my list of 4, it gives me this. Now, this is actually a list. Type, if I do type of my list of 0, this is an integer. This is a string. And this is a list. So now I can do again length of my list of 4. And this is 3 because the number of elements is 3 in this list. So you can embed any number of lists or any number of other data types. There is something called dictionary that we will see now. You can embed a dictionary inside a list also. That's how the lists are built. And similar to lists, there is something called a set. So let's define a set. My set. So definition of a set is like this. For lists, we have defined with square brackets. For sets, we have to define them with flower brackets. I'll define 3 and 4. Okay. Type of my set is a set. Okay. We have the same thing, just like this. But what's the difference? Let's try defining a list. 1, 2, 3, 4, 5, and then 4, 3, 2, 1. Okay. Length of my list 9. Okay, there are 9 elements in it. Let's say my set, I will redefine it to have same set of numbers. 4, 3, 2, 1. Length of my set is 5. Let's print and see what's the my set contains. It has only 1, 2, 3, 4, 5. Even though we defined 1, 2, 3, 4, 5, and then 4, 3, 2, 1, it actually had stored 1, 2, 3, 4, 5. So okay, this gives us one hint on what a set is. A set can only store unique values. You cannot store duplicates in a set. That's the whole purpose of having a set and a list separately. So otherwise, list will suffice. So set will contain only unique values. And same thing, just like sets, we also have one more subtle difference between set and list. Let's say I define a list 1, 2, and I want to see if this is equal to 1, 2. We are comparing two lists here. Are they same or not? This is correct. That's 1, 2 are same. And I'll just reverse the order and again compare. These are lists. We are comparing lists here. That gives a false. Now, this is evident. Now, I'll try the same thing with sets 1 and 2. This is true, similar to lists. I just change the order. Now let's. This is also true. So order does not matter in a set. So a list is an ordered list, whereas a set is a deduplicated set of values, and it doesn't matter the order which order it is in. If two sets have the same set of numbers, it is equal. So it's all mathematical sets. If you have studied mathematics, sets in mathematics, that's the same as this. Sets are unique. So we have seen lists and sets. Now there is something called tuple. Same error that we have seen. Why? The error you're facing is because a tuple. I'm going to explain why we are getting that error. Let's define a tuple, my tuple. So similar to lists, we have tuples 1, 2, 3. This is a tuple, type of tuple. Okay. Now, same thing I'll define as a list. 1, 2, 3. Let's append one element to my list. My list dot append of 4. And then now print my list. Okay, it's added 4th element to it. And tuple, let's do the same thing with it. And it throws an error. Because tuple is a read-only entity. You cannot edit tuple. You cannot add elements to it. So specifically where these tuples are used is to store XYZ coordinates or something that is standardized. Let's say in graphics programming, vectors are stored with X, Y, and Z coordinates. That kind of scenarios, we use tuples because if we have the ability to append data to an element, it needs to store some extra information, metadata, in the memory. So tuples are optimized for memory. So if there is a use case for optimal transactions, then tuples is what we need to use. If we don't have to append new elements to it, tuples is what we will be using. So that's why we are trying to, if we are seeing your error, it's trying to access a function that doesn't exist on a tuple. So starts with. So it starts with is a function that's available only on strings. It's not available on tuples or lists. Okay, that's about tuples. And the more last kind of data structure in Python is a dictionary. I'll define a dictionary. Similar to sets, we have dictionaries. Dictionaries is also are specified like with for float brackets. These are similar to our dictionaries in traditional dictionary, a word and its meaning, something like that. I will define a word and its meaning. A red fruit. Let's say a scary animal. This defines a dictionary which has only 2 words in it. That is, dict is a shortcut for dictionary. So let's do one thing. Why do we need a dictionary? Is for this is kind of stored as a hash table. So each index, Apple, if I want to specifically see if there is an element called Apple in it, what's the meaning of Apple? If I see, it gives the value of it. These values can be any data type. Let's just see one more example. I'll redefine this dictionary and I'll redefine Apple. Sometimes I'm in trouble. And let's see what my Apple has. Dictionary of Apple. I access. It got replaced by this thing. if I just print my dictionary, it is having only two elements, which is apple and bear. So when we have duplicates, just like sets, it will replace the first item with the last one. Similarly, I can also do manipulation of this like this. Another animal. Now if I do print my dictionary, this is what it gives. So you have seen the dictionary. Just like arithmetic operations, we have 1 plus 1, 1 into 1 plus 1, 2 into 4. This is a multiplication. And let's just do a power of 2, 5 power 2. This is an exponent. So we have 4, 3, 125. Just like a calculator, we can do this same thing. When I do a division, it by default gives a decimal number. If I want to do an integer division, I can do double slash. This gives only the quotient, doesn't give the remainder. If I want to get the remainder, it's just do modulo. Modulo means percentage symbol. If I do this, it gives the remainder. And similar to this, we can do arithmetic on strings, just like we have seen earlier. It appends to strings. I can do multiplication on string. Let's just say this repeats the string 4 times. If I do 1 plus 4, it gives an error. A string and a number cannot be added. So if I do 1 and again 1 in string format, it will just append these two numbers. It does numbers. It's not 2, it's 11. It's not even 11, it's just a string that has 2 ones in it. So similar to that, compare elements. True equals true. This is a statement, just like we have seen earlier. This is equal to comparison. This is less than. Five less than or equal to 5 is false. 5 less than or equal to 5 is true. 5 less than 5 is false. And 5 greater than 2 is true. 5 greater than or equal to 2 is also true. And similar to that, we have logical operators, which are and, or, and not. Let's see how to use them. True and false. This will result in false because and means both sides of the thing should be true. True and true, it will give true. False and false, it will give false. If you had studied truth tables in academics, that's what it is. And a similar thing, true or false. The only scenario where this false or gives false is both sides of false. Every other scenario it gives true. And there is something called not, which negates the value. True. If I do a not operation on true, it gives false. If I do false, it gives true. And there is something called membership operator called in. Let's say I have a list. A equals 1, 2, 3, 4. And found in A. If I type this, in is an operator. membership operator and it checks if there is a number called 1 in this list. It is true. If I do the same thing with a number that doesn't exist, it gives false. Similar to the list, we can do same thing with strings also. Cat in, this is my cat. True. Let's do AC. This word does not exist in this. That's not a print. So these comparison and membership operators are especially used in our conditional logic, if conditions, else conditions. So let's define value true. Let's define something. If statement A, so this is the syntax of an if condition. And inside this if condition, if I want to put some code block, the blocks in Python are indented. So in C language, we can see it with if A, something like opening and closing brackets. In Python, we indicate the indentation as the specificity for the block. So if I say here, if A, and we are giving a spaces, a tab inside it. So this means all the statements that are indented 4 levels are part of this if condition or if block. So A is this is inside the block. It's indent outside. Now this is outside. Let's run it. So these two statements got executed and this also got executed. If I change A to false and run the same code again, this thing did not get executed because A is false. It did not go inside this block and this only got printed. And if I have a certain condition called else, I can write it like this. If A is not true, A is true. A is not true. Similarly, I can actually nest things around. I'll just redefine A to true and have one more value called B, also true. I'll add one more nested block inside this A. If B, again, B is also A is true. This is inside the block. B is also true. This also got executed. Now, if I change this to B to false, then execute this block again. A is true, but B is not true. That's why this did not get executed. This also got executed, and this also got executed. So this is how we nest things inside the if conditions and else if conditions. There is something called else if A, print A. There is something called else if. This is in some other languages we use else if, but in Python we use elif. Just reduce the typing. Print A is not true. Okay, else if, I think we should have one more condition. Elif will accept B in the condition. Else. There's a syntax error here. We should use colon. Now click on printer and just change B to true. Let it focus. B got print. And I'll change B also to false. So it again. None of it. This is block code. So you try. Okay, similar to this, we have if conditions and then there is loops. So only two loops are there in Python, for loop and while loop. For loop, I can use something like for I, or we can give any name to it, item, I, A, B, whatever. For I in 1, 2, 3, 4. So this is a list. This for loop iterates through each of the elements of this list, and that I will have that specific indexed element. So I do print I. Here's this. What this is a list, and this is an iterator. In is here, it is acting like an iterator rather than as a membership operator. So we have seen something like 1 in 2, 3, 4. This is membership operator. This is membership operator. Whereas this in is part of the for loop syntax. So this is not the same as this one. So if I want to iterate through 0 to 10, let's do that. I should use a function called range starting from 0 and ending at 10. This does not include 10. So the range function iterates through 0 up to 9. It will exclude 10 from it. It will print 9. It prints from 0 to 9. It doesn't print 10. For 10 to be printed, I should increase the number by 1. And it does print. Okay, this is for. So we'll do a while loop. We'll define a value for a 0. While a is less than 5, print a, and then I have to increment a value. Otherwise, if I run this loop now, it keeps on looping, printing a forever, because a will never become greater than 5 because I've defined it or initialized it with 0. So for us to break out of the loop, we need to add 1 to it. A equals a plus 1. Every time this loop executes, it increments this value. Enter. We can see here 0, 1, 2, 3, 4. This is how while loop works. Okay, now we have the basic syntax, data structures, arithmetic operations in Python. We need to look into one specific aspect of this language called functions. So how do I write reusable code? If I have to write again and again, same kind of logic, it's kind of repeated, right? So in order to optimize that and not repeat ourselves, we define functions. A specific function will take some input, does something, and returns an output. So how do I define a function in Python? So if when I'm calling print hello, this is what we are doing. The system has a print function. Interpreter has the print function, and we are calling that function with an argument called hello. And what it does, it instructs the CPU to display this particular text on the console. So that code we don't have to write. And similarly, we can have our own custom functions defined to do custom operations. So how do I define a function is through this syntax. Def. Let's say I will just add a multiply function. Multiply by 3. And I'll accept one argument called val. This is just a variable name. It can be anything that you want to use. And we should end it with a colon. And whatever statements we write inside the indented block is part of this function. I'll just return value multiplied by 3. Just a second. So this returns, and we have just defined this function. We have not called this function yet. So to call the function, I need to do this. Multiply by 3, and I need to pass a value as a value argument. Okay. And it gives me 12. Okay. I'll define one more function, multiply. This time I'll accept 2 arguments, value 1 and value 2. And then return value 1 to value 2. And just try to do multiply, all this multiply with value 4 and 3. It gives 12. I can do similar thing on complex data structures, like 1, 2, 3 list. Let's say I will just write a function called append 4 value, or just list, my list, or list. So put a colon at the end. Okay, that's because I haven't defined it as definition def. List dot append. Now I'll call this function append 4 for list. Actually, I haven't defined that list. I have defined a list called A. We'll pass A as the list, and let's print A now. Now it has appended 4th element to it. That's how we use functions. So let's see the return value of this function. Let's say if I do a print hello, what does this value, return value of it give? Value, let's say this is just a name to a variable that I'm giving. So I'm storing the value that is returned by print into this value variable to enter. This actually printed something to the console, but the return value will be stored in the val. Let's print val now. See what it has. It has none, because print statement does not, print function does not return anything. That means by default, any function that doesn't return anything is returning none. None is like nothing. Let's do, there is a special type in Python called none type. This none type belongs to that. That's the none type. So let's try some arithmetic on none type. And we cannot do the arithmetic or any kind of operations on none. We can only check if none is true or not. None will always be false. That's the only operation that we can perform on none. So next thing is about classes. So classes is a part of object-oriented programming. I'll just give you a brief intro on classes. Then we will go in depth into some more concepts, and then we'll revisit classes and start off with object-oriented programming. So far, we have seen procedural code. Let's say do this, do this, do this. So how do I articulate a relationship between objects? How do I see the world as objects and do the manipulation on objects, do some actions on objects? So it's the object-oriented programming is invented for humans, not for computers. Computers can understand any kind of gibberish that we write. So for us to think in terms of objects, we found object-oriented programming. So an object can represent an object with an attribute, with some kind of attributes and some set of functions or things that it can do. So let's say a dog is an object. Dog is an animal, of course. It can be considered as an object. It has 4 legs, it has a mouth, it has a tongue, and it can bark. That's an action. That's a method. We can call it as a method. If I ask a dog to speak, it barks. So I can attach together the attributes of an object and the functionality of that object together into one class. So in simple terms, class is a template that stores both attributes of an object and the functionality or the actions that it can perform. So let's quickly define a class and I'll show you what it is. I'm defining an object called dog. This is how I define a class. Class is a template for an object. It's not yet created by us. It's just we are just defining how an object looks like, a dog object looks like. That's what a class is. It's just a template. So it will have by default a function called init. It's a language feature. So it's called a constructor. I'll go in depth into what a constructor is and how to use those constructors. And this is the basic syntax of defining a class. We'll go in depth into object-oriented programming once we cover the basics. So here, this is a standard function that we need to write in a class. So self is a reference to the current object. So I'll define a name value attribute. This is an attribute. This is called an attribute. So you can define any number of attributes with any name. Self.name, I'm just giving this dog a name. My dog 1. Or I can just say Rex as a dog. And self.legs defines 4. These are the attributes of a dog. And this is the end of class definition. So I will just edit it and have one more function defined. I'll just have speak as a function that also accepts a self argument. Any class function should have self as a first argument. Those details why we need that and all we will see later. So this one I'll just print self.name says hello. I can actually append or put a comma. If I use comma separated list of strings, it will append. The print function will append all these strings into one string. Okay. So there's 2 definitions of functions. So specific to classes, the functions defined inside a class are called methods. So the functions defined outside of a class are functions, plain old functions. The functions defined inside a class are methods, called methods. It's just a naming convention. Now we have defined a class called dog. Let's say I will create an object with my dog. is a variable that is actually a representation of dog. So this dog is the constructor. We are actually going to call this constructor here. If I do this, it's going to initialize an object with dog template and have this functionality in it. If I do my dog.speak, then this should be redefined with different quotations. I should do it this way. I'll just create one more object, my dog, and then call the function my dog.speak. That says hello. So now we are attaching attributes and its functions into one single class template, and it is called the object. This is object-oriented programming. So we'll go in depth into object-oriented programming in some time. So let's define a function called factorial. This function accepts a number, let's say 5, and returns the factorial of the number. That is, let's say I have a value 5 in it. It has to give 5 to 4 to 3 to 2 to 1. So all the way till 1 has to give. And just remove this. This value should be passed as an argument, and it should start from that value, and one by one it has to print factorial. This. Okay. But I'm hard coding this 5 as the value here, but we need to pass it as a value that is passed from this column. So if we can do that, that would be great. We need to write a factorial function, definition factorial, that should accept a value and then give the factorial. Let's say if it is n, and n factorial means n into n minus 1 and so on till 1. Let's write it here. Return value into value minus 1 to value minus 2 and so on. This one, we need to write it in a proper format based on the number. Like this kind of thing will become huge if it is 50, minus 1, minus 2, minus 3, minus 4. Up to 50 we will write. That is not the optimal way to write it. We need to write a factorial function to return the factorial of a specific number. Whatever the number we give, any huge number also, it should be able to calculate and give us the result without hard coding. So let's see that. So in our previous class, we have seen the basic data types, variables, and data structures in Python. Let's look into the in-depth of these data structures, and also we'll take a brief introduction to the classes in today's class. So from here, I'll open a new terminal in my VS Code. So if I want to go into the Python shell, I can do it through this command, Python, and now I'm in Python shell. So yesterday we stopped in while discussing about the classes. So to work with object-oriented programming, we make use of classes. So why do we need object-oriented programming? First of all, so if you think of our code that we have written so far, it's all procedural, meaning do this, do this, do this, do this. And well, that is okay. And for us humans, it makes more intuitive sense to think of objects. Let's say in real world, we have objects and their properties and their actions. So what we perform on those objects, any kind of object has a set of properties and a set of functionalities. So if we think in these terms, it makes more sense to have objects, think in terms of objects rather than uh, a set of tasks that need to be done. So that's why object-oriented programming came into existence. So, so for defining a specific object, we have to have a template of that object. Let's say a pen has an ink, has a refill, has a cap, has a body of it. These are all the attributes, and its function is writing. So if I do write, that is an action performed on the object. So to define these set of attributes and its set of actions, we make use of classes. Class is a template of an object. So I will define a class, for example, here, and I'll explain each of those things. For defining a class, we need to use the keyword class. So I'm going to describe a dog object. It's an animal, but of course, if we think of it as an object, that makes more intuitive sense. So every class in Python should start with a capital letter. So I'll use capital T, dog. So this is how I defined a class. So class, if I have to add some attributes inside this dog object, dog class, I need to add those in a definition. So now we have defined a class object called dog, and there is a default function called init for every class object. So I have to define or override that object, that function, like this, def 2 underscores init, and then 2 underscores. And then this is actually a function, but when it comes to object-oriented programming, within a class, if I define a function, it is called a method. So init is actually a constructor method. So I will explain what a constructor is in a bit. Let's define this method. So every class method will have a default argument passed into it, which is called self. Basically, it will pass the object itself. So when I'm defining an object, the object reference is what is passed into this self variable. So I'll explain more into this self variable in a bit. So once I have this defined in the body of it, I can initialize all the attributes of a dog. So a dog has 4 legs, a dog has a name, and so on. Let's say I will do self. To define a property or an attribute, I need to use self and dot any property name. Name of the dog, I'll just initialize it with Rex. And then I will have another attribute called legs. So it's an integer. Let's do self dot color as black. And that's the end of the constructor method. And let's say these are all the attributes. So let's say, what does a dog do? It eats, it barks, all that. Let's define that action also in this. So I define one more method saying speak. This also accepts an argument. All methods accept the default argument if you're not passing anything. Speak. So what it has to do, let's say when I say the dog is speaking, I'll just write something like bar. So this is what we defined. So this object template or a class has a set of properties, name, legs, color, and then it has a function or action it can perform, which is speaking. And this is template is defined. So now I want to create a dog object. So I need to initialize this dog object. I'll do it with my dog, just like lists and integers or any kind of variable, we can define a variable and then initialize it with a dog object. So in order to construct a dog object, I need to call the constructor like this. What this actually does is it will call this function inside this class that will initialize an object with name rex, lex4, color black, and returns that object into this variable. Now I print my dog. This is a class object. This is an object. So if I want to print my dog dot color, it will print that it's black. Name X. X it has 4. Now if I want to do some operation on this, I can do that. It has an operation called speak, and I'll call that, and it printed bar. So let's say I want to create one more dog. I will create a dog, one more dog, same thing. Print one more dog dot name. This also has the same name. So I want to make this name configurable. So if I'm creating a dog object, I want to pass a name to it, and all that color also I want to pass it, and initialize that object with that kind of properties or attributes. So in order to do that, we need to modify the constructor. Let's redefine the constructor here. Going back to the class, here I'm going to add one more argument called name here. So I'm going to use that name argument in the constructor. And then I will also use color. And one interesting property of one interesting aspect of Python I want to discuss here. You can also specify default values for these properties. If I'm not passing any values to it, we can define the default properties. So the default property for color, I'm going to use as black. Default value of color, I'm using as black. And default value of name, I'm going to use as rex. So if I'm not passing these two values, variables, or the arguments, it will by default assign name as rex and color as black. Let's define this, and now dog1, dog of name, I'll give Lucy, color as white, and dog2, I'm going to not use anything. By default, it will be rex and black. Let's print dog1 dot color, print dog2 dot color, dog1 dot name, dog2 dot name, dog1 dot name. It's all defined. And when I do dog2 dot speak, it does the same thing. Dog1 dot speak, it does the same thing. I can do some set of modifications here and print the details of a dog, of the dog. Self dot name, I can access this variable, says going to define initialize dog value, dog1 as Lucy, dog2 as dog. Now I'll just do dog1 dot speak. Lucy says bark. Dog2 dot speak. Rex says bark. So this is how we use objects in Python. We'll go in depth into objects in a bit, but before that, we have already seen the basic data types and data structures. We didn't see how to manipulate these complex data structures yet. So let's do that now. So before we dive into this, let's do a simple exercise for defining a factorial function. So I'm going to define a function called factorial. What it does, given a number, I'm giving a number, and it returns the factorial of the function. Given n, variable n, it returns n factorial. So if you had seen mathematics, n factorial is like n into n minus 1 into n minus 2 into and so on till it reaches 1. Let's say 5 factorial actually means 5 into 4 into 3 into 2 to 1. 5 factorial is this. So I want to do that programmatically now. So I will pass factorial of 5, and it should give me the actual value of factorial of 5. For that, we need to do something like this. If the number n is equal to 0, it will return 1. So factorial of 0 is 1. So factorial of 1 would be like 1 itself. So we can do it in 2 ways. One way is to write some logic. Because before we even do the logic, we need to check if the type of n is number or not. If type of n is not equal to integer, return none. And if it is a negative number, we don't have a factorial. If n is less than minus 1 or n is less than 0, return none. So for these 2 cases, we are not going to calculate. It's an error handling scenario. If n is 0, we have to pass in 1. So first approach we'll define a variable called factorial. We'll go into this later. Right now, let's just define factorial value as 1. So because for 0, it will be 1. Okay. And for 1 also, it will be 1. So I will just count a value. Counter 1. While count number is, so I'm actually going to go from 1 to up to the number and multiply all of them and then sum it up into this factorial, add it up into factorial. So I'm going in the reverse order. Instead of going from 5 into 4 into 3 into 2 into 1, I'm just going the reverse order. 1 to 5, 1, 2, 3, 4, 5. I'm just doing 1 into 2 into 3 into 3. like this. So counter, I'm initializing it to 1 because it starts from 1. And while it is less than or equal to the number, it has to go till number 5. If I'm taking an example of 5 as the factorial number passed, while count is less than or equal to n, and multiply the counter factorial equals factorial into count. And then count, I need to increment. So every time I iterate through this loop, I need to increment by 1, which is 1. First time it should 1 into 1 it should do. And second time the previous value into 2 it should do. And previous next iteration it has to 3 into 3 and so on. What it results in now is first thing, the first iteration, the factorial will be 1. 1 into the count is 1. So it's still 1. Next iteration, count is going to be incremented to 2. That time, the previous value of factorial is, let's go through this iteration by iteration. 1 equals 1 into 1. This is the first iteration and count was 1. Count is 1. No, factorial also is 1. So this will become like this. Next, count will become 2. And previous value of factorial is 1 equals 1 into this count value, which is 2. Now the factorial becomes 2. After this also factorial becomes 1. This is the factorial value. And then next iteration, initial value is 2. Now count becomes 3. Next iteration. Every iteration we are actually increasing the value of count by 1. This is the first iteration. This is the second iteration. This is the first iteration. This is the second iteration. This is the third iteration. Previous value of factorial is 2 equals 2 into count 3. Now factorial becomes this one factorial. This one will become factorial. Let's repeat myself. This is the first iteration. So count is actually 1. Factorial equal to factorial value, initial value is 1 into count is 1. Okay, now count will become 2 because count equals count plus 1 we are doing. This is first iteration. Second iteration, count is already 2. Now factorial becomes, what is the value of the factorial in the previous iteration is 1. Right? This result of this thing is 1 into 1 is 1. So the factorial is actually 1. Value of it is 1. So value of factorial in the previous iteration was 1, and now I'm going to use count again according to this logic. Count value is 2. That time value becomes 2. And third, and also now I'll increment the counter by 1. Now it becomes 3, and third iteration continues. Factorial equal to previous value of factorial is 2, and the count value is 3, and now the value becomes 6. Count will be incremented to 4. Fourth iteration, factorial equals previous value of factorial is 6. into current value of counter is 4. Now the value becomes 24. Like this, it continues till the count becomes 5. So now this count becomes 5. And we have put the condition as less than or equal to. So even when the count is 5, it will run one more time. This will be the last time it will run this loop. So that time it will calculate fifth iteration. Factorial becomes the previous value, which is 24. Current value of counter is 5. This will become the value 24 to 5, 120. So instead of writing all this, this is a representation that I've given explanation. I can just comment out this part and run this code directly. So what this loop is doing this operations one by one in every loop. And after the end of the loop, I'm going to return a value called factorial. I'll call this code. And then now run this code. Python myscript.py. I run this. I haven't printed anything here. So I just print the factorial of 5. Factorial of 5 is factorial of 5. Is 120. Let's use 6 instead. So 6 is 720. No, particular 7 is 5046. Okay, this is one way to do it. There is even a better way to do this. Let's use another approach. I'll define a more function factorial 5. Similar to this, we have to check this conditions. If type of, I think we should use the number. I'll just use the value variable name as num. If type of number is not equal to integer, then return none. This is handling the negative scenarios. If number is less than 0, return none. Now we're going to handle a situation where the number is 0. If number is equal to 0, return 1. If number not equal to 0, then what we want to do is, so if we think logically, so 5 factorial is actually going to be 5 into 4 factorial. And 4 factorial is going to be 4 into 3 factorial. So in general, n factorial is equal to n into n minus 1 factorial. So this logic is what we are going to use in this. So now I have number n. So I need to find out the factorial of n minus 1 factorial, n into n minus 1 number into number minus 1 factorial. Right. That's what I'm going to do here. Return number into this factorial we already defined. This is called a recursion. So we will find the factorial of number minus 1. So this function is actually calling itself again with a new number. So this is an iterative way of implementing this logic. So 5 factorial will become 5 into factorial of 5 minus 1, which is 4. So every time this returns the 4 factorial value. And it will multiply 4 factorial by 5, which is essentially the 5 factorial. Let's do the same, execute the same thing. This function. Just remove this. Seven factorial is 5040. Same thing. Let's try with 6. And then 5. It's the same implementation, but it's a different way of implementing this in a recursive format. So this also can be done, and this is more optimized. Cool. So I'll move this 5 to factorial. Okay, that's about a simple implementation of a factorial. So now let's go back to Python and discuss about the data types, in depth into the data types. So we have seen division operation in our previous class. 20 divided by 4 is actually going to give us a real number, 5.0, which is a floating point number. Let's do some arithmetic on floating point and integer. So these both are integers, it's not floating point numbers. But division operation is always giving us a floating point number. So what if I do operation on one integer and one floating point number? It gives a floating point number. So compared to integers, floating point numbers are a bigger entity. We store larger values in floating point numbers. Always when we do some operation on a bigger value entity, the interpreter will convert the lower value entity into the bigger value entity. Integers also will get converted into floating point numbers if I'm doing addition or any operation with floating point numbers. That's a logic here. So same thing applies to even multiplication, even exponential operations. 4.0 as an exponent, if I do, it becomes a floating point number. So I can actually convert this into integer. Let's do that. How do I do that? Is through this. 4 power 4.0 to 56 integer portion it is extracting and showing here. It's again converting into integer. 45 to 8.9. It's not actually rounding this, but it's eliminating the decimal part of it. It's only giving the real part of it. The decimal portion it is removing entirely. Integer. This is called typecasting in Python. In any language, we call it as typecasting. So one type of variable is value is being converted into another type. What if we do 8.99999 so on? It's almost 9. It's not going to round that value. It's going to eliminate the decimal portion and gives only the real portion of it. Similar to this, if I have 14 by 3, it gives only the integer portion of it. So if I actually do 14 divided by 3, it's actually a regression, repetition of 6666 and so on. It's at the end, it is approximating it to 67. That's the precision level that the system supports right now. So what if I want to round this value into a higher one, which is like almost near? If it is 8.3, it should go to 8. If it's 8.9, it should go to 9, something like that. So if I do round operation on 14 divided by 3 gives 5 because 4.6 is actually greater than 4.5. So round operation will approximate it to the next integer, which is the nearest integer. It will do that. It will convert that. Okay. Coming to the floating point discussion, let's do some simple calculation. 1.2 minus 1.0. What should this actually be? It should be 0.2, right? But it is giving this number. This is called floating point error in computation. You can do research on how these floating point numbers computation matters and how it's going to affect the calculations. So our computers only represent floating point numbers as approximations. So it will first convert a number into a mathematical scientific representation and represents that in an exponential format. So actually, if I'm storing a floating point number called 0.2 or 1.2L, let's just take the example of 12.5. So how the system stores 12.5 in memory is first it will convert that into scientific notation. So the binary equivalent of 12.5 is going to be 1100.1. So how did I come up with this number? So if I divide 12 by 2, the remainder. So how to convert a whole number, integer 10 base 10 integer into a binary number? So these things we divide by 2 every time and make the remainder as the value. So I will show you these calculations later, if how to do that. And the ones that are on the right side of the dot are going to be multiplied by 2. So if I multiply 0.5 by into 2, it will become 1.0. So that's why 1 will become 1. So the binary representation of this will be 1100.1. So this is a multiplied. If I want to convert this part of it, I need to divide by 2 and add the remainder here. If I have to convert the right side portion of the floating point number, I have to multiply by 2. 0.5 into 2 is 1. So that will be down here. So these are all not necessary. Just to give you the background of how these floating point errors happen, it's just enough to know that floating point errors happen. And this is the floating point numbers are just approximations to the nearest value in exponents. So first, system will convert this into a scientific notation called 1, something similar to this 1 dot 1001. So all scientific numbers start with 1 point something into 2 power 3. If this is confusing, just bear with me. It's not important, but just giving you the background of why these floating point numbers don't have exact values. This gets stored in the memory. The real portion of it will be stored in one place, and the exponent, which is 2 power 3, is stored in one place. So all of them cannot be represented exactly. That's the reason it happens. So for avoiding this kind of scenarios, we have another data type called precision decimal. So for decimals, we need to use a library called decimals. So if I just do rounding of 1.2 minus 1.0, it gives the correct value. Round. Okay, I think Let's do 1.2 minus 1.0. So because it is near to 0, it is giving the 0. If I want to round it according to a specific precision, let's say I want to approximate by 2 decimal points and do it this way. And it approximated to 2 decimal points. 0.2. Let's convert integer 100 now. See how this works. And this actually is converting string 100 into decimal integer 100. And I can represent the base of this. So this is actually base 10 number. If I consider this as base 2 number, what will be the value of it? So the integer has an advanced feature to represent a string and convert that into binary. So we have converted this. Previously, we have converted this into binary, right? When we are showing how these floating point numbers are represented. In order to convert number 12.5, we had come up with 1100.1. So how do I convert that? Yes, through this. If I have a string in it, I can convert by base 16 or base 2 or base 10. By default, it is base 10. If I convert this string into base 10 value of decimal number, it is 100. If I make it as base 2, the value of it is 4 because 2 power 0, 2 power 1, 2 power 2. 2 power 2 is 4. So similarly, we can also convert numbers that are represented in hexadecimal format, base 16 format also into this. So base 16 is about base 16 numbers start from 0 to up to 16, 15. C, D. So these are base 16 numbers. So base 10 numbers start from 0 to 9. Base 16 numbers start from 0 and end at F. Base 2 numbers has only 2 values, 0 and 1. So here we are converting this 100 into base 10 number, which will result in the value 100. If I convert this 100 into binary and its value becomes 4. And if I convert this string into a hexadecimal value, its value is equivalent to 427. That's what it is. So now we have decimals, right? 1.2, and we can go back to the discussion about decimals. In order to approximate these or precision numbers, if I want to approximate, I can make use of a special library called decimal library. So for that, I'm going to import decimal library, import decimal, and there is another thing called get context. It's a method. I'll just explain you in a bit. So let's get the context first. So context has a specific precision value. Right now it is set to 28. So the precision is going to be 28 characters onto the right. So I can set the precision value with this get context dot precision. Say I will initialize it to 4. Now if I do decimal divided decimal value of 1 divided by decimal value of 3, it gives me 4 precisions. It gives me 4 values. By default it was 28. Now it is set to 4. This is an advanced data type. You don't have to understand it fully. Just that know that this is there. Let's just use math function or write as 2 decimal of 0.14. This is actually stored as this. So just like I discussed earlier, it's an approximation of the value. It's not actually 0.14, 3.14. The computer stores this floating point number as an approximated value. So that is about floating point numbers. If it's all confusing, just forget about that. Floating point numbers, just this is enough. Knowing that floating point numbers do not get stored exactly in the memory. It's just an approximation of nearest value. That's enough to know. So we already saw casting earlier. So integer of 1 we have seen. Similar to that, we can have casting on other data types. Let's say I will convert a value of 1 into Boolean. What will this result in? It results in true. So any non-negative number is a true value. If I do 0, it's 0. Even negative numbers will become true. So anything that is non-zero is a true. If it is 0, if a value is 0, it is false. Let's say I have a variable called a, which is initialized to 4. And if I do if a, print a, this actually evaluates to true. And if I initialize that back to 0, and if I do the same thing, it is false. If I initialize it to again -1 and print it, it's still going to be true. So any value that is not 0 is true value. Even complex numbers, if I do Boolean of 1j, even complex numbers are true values. Similar to that, if I have an empty list, this is going to be false. Any non-empty list will become true. And there is something called none type in Python. Let's see what that none type. None type is also false value. So in similar context, if I have a list called 1, 2, if my list, if I do print my list, my list will evaluate to true because the length of my list is not empty. It's not empty list. So let's just reinitialize this my list with an empty list. And if my list and this is not getting executed because this is evaluating to false because it's an empty list. Similar to that, if I have A as 5, B as 5, A minus 5, A minus 5 is 5 minus 5, which is 0. Similarly, this also doesn't get executed. If it evaluates to 0, it always becomes a false statement. Instead of this, I can just do A equals B. This is equal to B. A is equal to B. Okay. Is this too confusing? Should we stop here or should we continue?
అర్థమవుతుంది సార్.
Okay. Okay, next logic we have to look at is not logic. Let's just take an example of whether it is nice is a Boolean. Let's say it is false. I have an umbrella or not? I have an umbrella. Okay, true. I'm going to write some logic here. If I don't have umbrella, or if weather is nice, I'm going to stay inside. Else, I'll go for a walk. Is there anything wrong in this statement? So now it says if I don't have an umbrella or weather is nice, weather is okay. If I don't have umbrella or weather is nice, that means I could actually be thinking that this not applies to both these. This could mean, like initially, if I'm thinking like this, if I don't have umbrella or the weather is nice, this not applies to only this statement. It does not apply to this statement. So if I execute this, it's saying go for a walk. Weather is false. I have an umbrella. Let's just do one simple logic here. This not applies only to, so this is actually similar to not have umbrella or if I don't have umbrella or if weather is nice, stay inside. Else, go for a walk. If I don't have an umbrella or if the weather is nice, this should get executed. Have umbrella is true, so this becomes false, or weather is nice is also false. So this statement will not go in because this evaluates to false and this evaluates to false again. So false or false will become false totally. So this statement gets executed. Go for a walk. If I change one condition here, weather is nice is I'm just going to change have umbrella to false and weather is nice to true. What I want to do is if the weather is nice, I don't need an umbrella. So at that scenario, what this code behaves like, let's see. It's still suggesting stay inside. So have umbrella. No, I don't have an umbrella, but the weather is nice. What this statement is evaluating is have umbrella, false, it becomes true, or weather is nice, true or true, and it's going inside this. What I actually intended to do was if the weather is nice, if weather is not nice, then only I would need umbrella. If it is weather is nice, I don't need the umbrella to go outside. So to appropriately represent this in the code, I have to do either this, if not have umbrella, or weather is nice, stay inside. Else, so this actually applies, this not applies to both these. If I have umbrella, or if I don't have an umbrella, or if the weather is not nice, stay inside. Otherwise, I can go for a walk. So, but this again, have umbrella, false, weather is nice. Weather is nice is true, so it's suggesting go for a walk. So what I'm trying to say here is this not is only going to apply to the first next immediate item, not to the entire set in the if condition. If I have to write it to apply to both statements, if not umbrella and not weather is nice, stay inside. Else, so this should be written like this. So the idea here is the not applies only to the next immediate item, not to the entire set. So after the and, if I have to negate this, I have to use not again. So this statement, I can write it in a better format. That's just, it's more clear that way. If I have umbrella, or if the weather is nice, no matter what the weather is, if I have the umbrella, I can always go for a walk. If I don't have an umbrella, this becomes false. And if weather is nice, it's enough to go for a walk. I don't need an umbrella. Else, this becomes stay indoors. So I have an umbrella. Weather is nice. I just change the conditions. Have umbrella equals false. Weather is nice equals false. Both are false. Now I'm going to run this. Stay. It's suggesting stay. I don't have an umbrella, and I don't have weather as nice. Now I'll change the weather is nice to true. Now I can go for a walk. I'll change back weather is nice to false and have umbrella to true. Now I can go for a walk. Even though weather is not nice, I can go for a walk because I have the umbrella. That's how these logics work. The point here is the not applies only to the immediate next item, not to the entire conditions that we put in the if condition. And there's one concept we need to cover in lists. Let's say I have a list of names, or I can just have a name. My name is Mukesh. So if I want to access a specific character, I can access through the index. Name of 0 will give me n. Name of 1 will give me the next immediate item. And if I want to access a range of characters, I can do it through 0. starting index 0 and ending index 7, but not including 7. So it will go till 0 to 6. My name is getting listed here. Similar to this, I can actually, if I'm starting with 0, I can actually eliminate the first item itself. If I just use name :7, it goes up to 7th index, but not including the 7th index. It gives me that. So if I want to list by from the 11th index to the end of the string, I can use it this way. Starting at 11th index to the end, it's giving this name. If you count the indexes 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, starting at 11. So this applies to strings as well as for lists. Similar to strings, I can have a list of numbers 1, 2, 3, 4, 5. I can do the same thing. My list of 2 to 4, it gives index 2 and index 3. It'll not include index 4 because that's how it works. So index 3 and index 4, index 2 and index 3, it will give 0, 1, 2, and 3. Third and second and third index it gave, fourth index it won't include because it's 1 less than this number is what will be returned. And similarly, I can have length function for name, like this is 18 characters in length. And next we need to visit how to do formatting of strings. Let's say I want to have my number is, let's say, string 5. This is how we append strings or format strings. This is one way to append strings. There is a new format in Python that is introduced in 3.16.6, I guess, 3.6 version. So there is called, these are called F strings. I can include numbers in the string itself. So I have defined a variable, or I'm defining the string like this. F strings are defined like starting with F, and then single quotes or double quotes, both are accepted. So I'll just use my number is within flower brackets. I can use 5. Within this, I can actually have some kind of Python function or Python operations also. 5 into 5. This actually does Python calculations and stores that in the string. I can do the same thing with format also. There is something called py in math. It's a import math function. Math.py, I'll tell py value is 3.14. Let me use this py value in a string, formatted string. Py is math.py. This is nice. So I can also do formatting. If I just want to print only the first 2 decimal values, I can do it with :.2f. Gives me only this 2 decimal values, 3.14. Similar to this, we can also do one more formatting. So py means this dot format and dot py. This also does the same thing. So next thing is to, what if I have multiple lines of string? If I just initialize a value to x1 and I want to enter multiple lines of text, in a single value or variable. I can't do it with this format with single quotes. So to define multi-line strings, I need to use triple quotes. Is one, is two, is three. I'm actually entering multiple lines here. This is multi-line. And how do I close the string is again three quotes. Now, if I just print A, it gives this. This is actually backslash n actually means it's a new line. So if I do print of A, it will print multiple lines. This is what the string contains, multiple lines. If I represent in Python format, it is going to be having backslash n characters. These characters mean new line characters. This is how we define multi-line strings. What if I have to use quotations inside a multi-line string? Let's say I have a is one having multi string with quotations. But if I want to use quotations again, I have to use backslash to escape the quotations. And then in order to close the string, I need to use three quotes again. And if I do print A, this has three quotes inside the string. Similar to this, I can have three double quotes. If I'm using double quotes inside single quoted strings, I don't have to escape them. So vice versa. Even this requires single quotes because this will evaluate to empty strings. I need to still use back quotes if I'm using multi-line multiple quotes inside a string. If I print A now, it's the same as defining with single quotes. So that's about the strings, multi-line strings, and there is some data type called bytes. So in our last class, we have actually covered little slicing of a list. So if we just quickly review what has been covered so far, we have seen basic data types and complex data types of Python, and then we have seen functions, and then we have seen arithmetic operations and some operations on lists and dictionaries, the differences between tuples, lists, sets, and dictionaries we have seen. Then we have done some arithmetic operations on strings, so multiplying strings, and we have seen logical operators and or not, and how to manipulate Boolean operations with these. And we have seen if conditions, if else conditions, and we have seen for loops and while loops, how they work. Then we have seen, we have defined a function that manipulates these items, these different data types, and we have seen classes just briefly, and we will go in depth into the classes in the future classes. And yeah, we are, and we have seen like floating pointer operations, and just concluded that the floating point numbers are not stored accurately in the storage computer memory, but it's an approximation. But for most of our operations, the approximations are good enough. Then we have seen decimal data type, which is a special data type in Python. So now we'll go into in-depth analysis of more complex data types. So we have seen lists, We have seen string manipulation with format strings. Now we are going to see bytes. Yesterday we stopped at bytes. Let's start from bytes data structure in Python. So let me go into the Python shell. So bytes is a special data type. We can actually define bytes with this function. So this actually is making a byte object with 4 bytes length. So each of these x00 represents 1 byte. So this is hexadecimal representation of bytes. So if you see the prefix b, this means that this stream of characters or this stream of bytes is a bytes object. And each of these x00 represents 1 byte. So let's say I want to, so these byte operations are very useful when we don't know the encoding. Let's say our files that we store. So if I have text file in it, it's a encoded file. So although the data it contains is a binary, so it will be encoded in a specific format, usually in the UTF-8 format. So in Unicode transformation format is what UTF means. So any character, any data that we write in text files is all encoded with that. Let's see how those encodings, if we don't know the encoding, we can actually read the raw data bytes from a file. And if it's a binary file or an executable file that runs on the machine, so we can use bytes directly to read that file. Let's say I will create a new bytes object. So bytes, so we can actually have any kind of string passed to it to convert that into a byte. So I'm going to use a string ABC here, and then I'm going to encode that into UTF-8 format. This actually converts this string into UTF-8 byte string. Also, let's just use a smiley character here. I'm going to put a smiley character. This terminal is not supporting display characters. That's fine. We'll use plain text itself. So if I'm initializing it with a variable name, let's say my byte string. Okay. I'm just going to copy paste some text here. I'm just going to use. Okay, why was this not properly given? Okay, let's forget it. Exit out of this and let's go back to my byte string equals bytes of ABC. And I'm going to encode it in UTF-8 format. Okay. Now if I print my byte string, okay, it's a binary. It's a byte type. If I do the type of byte string, it's a bytes data type. All right. So what if I want to use an array of bytes instead of just the bytes? I can define it through byte array. So this is one type of data structure that I'm just demonstrating. So similar to bytes, we can have byte string, byte array also created with the encoding. Select that. Let's say try to decode, and for me to convert from byte string to string object, I can decode it with UTF-8 again, and it gives me a string. So this is especially useful when we are handling raw files instead of text files. If we have text encoding known previously, we can use plain text read. If not, we have to use byte streams. Okay. Now let's look into some of the list slicing features. So we have seen lists earlier. Let's define a list now. So we can actually have a partial list of items extracted from this list with a special syntax. Let's say if I want to get from the third index to the rest of the string, I can use it through 3 to end of the list. This is a special syntax we can use to extract from the third index 0, 1, 2, 3 till the end of the list. If I want to specify, I can use it this way. So if I want to list from 0th index to 6th index, excluding the 6th index, and if I want to step by 2, so every other character, if every other element, if I want to print the step size, I can specify it as 2, like this. This gives me every other element 1, and then 3, and then 5 till it reaches the higher index. Similar to this, we can actually eliminate the 2 parts, left side part, right side part, and only specify the step size. If I do the same thing here, from the beginning to the end of the list, it's going to print every other element. That's the same as this. So if I want to print the entire list as byte string, the list of numbers, or extract these numbers into a separate list, I can do it this way. So one thing to note here is, let's say I have my list defined here, and I will have another list. I will have another list that is actually initialized back to the same value as my list. This actually means it's not copied. Actually, it's referring to the same thing. Let me demonstrate that. Now, let's say another list dot of, let's say, third element, I'm changing it to A. So print another list. That's fine. This is expected to happen. Let's say print my list. That also got changed. What happened here? So when I'm assigning this list and changing this particular list, it's changing this list also. So one thing to note here is the list assignments. If I'm accessing list variable, it is actually a reference to the same object. So I'm here when I'm assigning this value to a different variable, it's the same reference to this object. So both refer to the same object now. It's not a copy operation, it's a copy reference operation. If I have to do copy operation, there is a special way to do it. Let's say I have a list, my list, 1, 2, 3, 4, 5, and another list I will initialize with my list dot copy. If I copy this, so another list will become a another list. It's a completely different object. So now if I do another list of 3 is equal to A, now print another list. This is same as previous. If I do print my list, it did not change because we are actually copying the entire list into a separate list. So in the earlier scenario, we are actually assigning the same reference to another variable. So that's a subtle difference between reference assignment and copy operations. So similar to this, let's go dive into some special function called range in Python. Range, let's say I will give 5. Range function gives me a list of numbers till this number, excluding that number. So if I convert this into 0, 5 as a list, gives me 0, 1, 2, 3, 4. So that's a very useful operation when we are doing for loops, like just like in other languages, for I in range 0 to 100 or range 100, I can just do. So 0 to 100 means starting index is 0, higher index is 10, let's say 5 to 100. And I can also specify the step number also, how much you want to increment every time. So I will increment by 5, 10, print I. So this range function accepts 3 parameters. One is compulsory. If I give only one, it will go from 0 to that number, excluding that number. And if I give 2 values, the first number will be taken as the starting index, starting number, and n number is the second argument. And if I give a third argument, that will be used as an incremental counter. So next time, every time it loops, every time the iterator will give 5 plus 10, 15. That's what it's given. So same thing if I demonstrate here, range of 5, 100, 10. This gives me a list of numbers starting from 5, ending till 100, incremented by 10. That's about the lists and range functions. Some other thing that we need to do also look at is the negative indexes. Say I have my list. I will initialize this list with a range function. This will have len of my list. If I see this has 100 items in it, 100 items in it. Now, if I want to print every other character, I can do it with the syntax 0 to 4, like this. It gives. If I specify the step number, every 5th item gives like this. Similarly, we can give 15 also. What if I want to print in the reverse order? So I can do it with -1. It returns from the last index first to the end, first index last. Similarly, I can use -10 to give me from the end. Each iteration, it will reduce by 10 and gives me from the last to the first. We already know the append operation. 1, 2, 3, 4. This just covers append of 5. If I do print my list, this is an append operation on the list item. And there is something called insert. So this append operation appends to the end of the list. But what if I want to insert an element in the middle of the list? I can do it with the index number also. So my list dot insert, what index I want to insert at, 0, 1, 2, 3. So third index, meaning 4 will be replaced by, or it will shift by one value. I can put a value here. I just print my list. 4 is shifted, and now the value is inserted in that index, third index. And let's say I want to remove an item. I can do that with just the value. So my list dot remove 4. I'll just remove 4. It has removed the 4th value. Here I'm giving the value of the element, not the index of the element. Similarly, if I give remove a value, and it removes that element also. Let's try removing some element that does not exist. So 4 is already removed. I'm just trying to remove it again, and it gives an error. So let's say my list. Now if I want to, there is another function called pop, which pops from the end of the list, and it gives the value, return value that it popped. So it actually popped 5 out of this list. And if I now print my list, it only has 1, 2, 3. It got popped. So this is especially useful in our programming scenario where we have each item. If I want to do some operation and remove it from the list, I can use pop. While length of my list, let's print or do something on the list items. To print pop, it pops. Now if I just print my list, it's empty because all elements have been popped out of it. Similar to this, we have already seen the copy operation. I'm assigning to a dot append of file, print b. It modified the same object and it's referring to the same object. B and A both refer to the same object. If I do b equals a dot copy, now it refers to the different object. End of 6, if I do print b, doesn't get affected. So print A, it got affected. So now we know the difference between a reference assignment and a copy operation. Okay, now let's look deep into our sets one more time. So I'm defining a set with A, B, and C. What if I want to convert this set into a list? So there is a use case for this. If I have a list of items, A, B, C, and then A, and then D, E. So the easiest way to reduplicate this my list is to convert this into a set and then again back to list. So if I do this operation, list of, I'll just say a set of my list, convert this into a set, and then convert that into again a list. It has converted that. If you see the order did change, but when we are concerned about the order of the elements, we should not do this. When we are only concerned about the deduplication, we can do this operation. So sets may not give the items in the same order that they are defined. So similar to lists, Sets also have a pop function. Let's say I will define a set, my set dot pop. If I do, it gives me an element. It need not be the last element. It can give any element. So order does not matter in set. So if I try to access my set of 0, this will fail because sets do not have any order in it. So you can iterate through the set of items for item and set my set print item, but you cannot access it with index. Whereas in a list, you can actually access by index. And similar to this, we have A in my set. This gives me the operations. If I do B, C, in membership operator works in sets also. And let's say if I want to discard an element, let's say I have a set, I want to discard an element. I can do that with discard. Let's try remove. Then removes C again. It fails. Let's say I will just discard C. Doesn't throw error. So discard, the difference between remove and discard is that remove operation fails if the element does not exist. If you call discard operation, it will ignore if the element does not exist. Then we have tuples also similar to. There is a special use case for tuples. Let's say I will show you that. So I have initialized my tuple with 3 elements. I can access the tuple elements with their index. That's possible. Lists and tuples allow access by index. And let's say the main use case of tuple is one is graphics programming and storing immutable data, and there is another use case. Let's say I have a function that returns multiple values. In other languages, we don't have return having multiple values, return 1, 2, 3. If I'm doing this kind of things we cannot do in C and Java. We should actually wrap this entire thing into an object and only one return value is allowed. Whereas in Python, we can allow multiple returns, but there is a caveat here. If I'm returning 1, 2, 3, let's just try to store that value in here, return multiple values. Now, if I do type of A, it's actually a tuple. If I print A, it's a tuple. So what this actually is returning is a tuple of these 3 items. So by default, if I'm returning multiple, it actually means when I'm defining like this, it actually means this. This is not strictly necessary. The bracket says strictly not necessary. I can just skip the brackets and it gives by default a tuple object as a return value. That's where most of the times we use tuples. Okay, we have seen dictionaries previously. Now there is something called default dictionary. So we'll see that use case as well. Let's say I have a dictionary with some elements. Or just initialize this. we have a simple dictionary here. I access A. Okay, now if I do animals of D, I can actually add a new element to the dictionary with this type of format. Now if I print animals, okay, it's added. If I do again animals of A, antelope, it replaces the previous one. What if I want to store multiple values into animals? A element, my A key might have multiple animals, B might have multiple animals, C might have multiple animals, and so on. So for that, we need to create an array or a list for every item. We need to add an array, a list, and then use that. Let's look into that use case also. But before going there, we will just see some utility functions in dictionary. So if I just try to get access to all the keys of this, I can get that with a dict keys element. So this is not a list item, but we can iterate through item, these keys. For key in animals, that keys. If I just get the type of animals dot keys, it's not a list, it's a dict keys object. I can convert that into a list. Yeah. Similar to this, values also I can get all the values it gives. Okay, now back to the use case of having multiple elements as a single dictionary value. Let's say I'll predefine animals with a new dictionary. This time A is going to be an array of first item. B will have another array. First item is bear. I'll close it right now. So I'll add new elements to it. Animals of A dot append antelope. Now we have two elements in it. Now I want to add a new element called C. Let's just say C. Animals of C. I have to initialize it with an empty array, or I need to say like this. What if there is an element already in C, in the animals dictionary called C? So I need to check if it exists. Then I need, so if it exists, actually, if I do it in this way, if there was a key called C in the dictionary, it will replace the entire value with this value. So for me to properly add it to the end of the list, I need to check if C exists and then add that item. For doing that, we have to see if C exists. If C not in animals, then I need to initialize C with an empty array, and then I can do C dot append of cat. Now this works. There is a better way to do this. Every time if you want to do this check to see if it exists, and then add an empty array and then do this will become too hectic. So for that, we have a functionality in Python called default dictionary. So what it does, I will show you in a few minutes. From collections, I'm just going to import default dictionary. Tick. So the difference between default tick and tick is that, so let's define animals as a default tick. So default tick accepts an argument specifying the default data type of a variable of a key if it does not exist. This actually, we are actually saying here, define a dictionary with the default value as a list. Let's just print animals. It's a default dictionary. Let's try to access an element that does not exist in this. I'm trying to access C, which does not exist in the dictionary, and it gives me an empty array. So instead of trying to check if C exists, if it does not exist, it actually gives an empty array. So similar to that, I will just add animals of C dot append of cat. This time, when I access this, it gives an empty list if it does not exist, and then appends that to the cat to that list. If I print animals now, C has cat in it. Just like that, I can just add one more element, D. This use of default dictionaries. Instead of doing this, default dictionaries and dictionaries are all one and the same, except for this functionality. So we don't have to check every time if an element exists. If the element does not exist, it gives a default value to it based on the type of data type that we defined while initializing default dictionary. Okay. One minute. Okay. Now we have to, yeah, let's define a list. Let me show you an advanced concept in lists. This is a list. Let's say if I want to initialize another list on each of these items. Let's say I have a use case for I in my list. I'll define a new list. So list is empty, and then where item in my list, new list dot print of two into item. I'm just multiplying it by 2. Print new list. Okay, this we have it, and this is very verbose code. What if I want to do that in a simple or efficient format? In simple terms, I can use like this. So this defines what I want to do. For each item in my list, do this and put that in an array or a list. This is called list comprehension. If I do this way, item, sorry, it's a syntax. The value variable name 2 times item for item in this list. For each item in this list, do this. This item value can be X also. It's just a name that I'm giving. Whatever value I'm going to use here, variable name I should use same here in the for loop also. This is a shorter way of specifying this syntax. And this, we can actually do one more thing, filtering on this also. Let's say I have a value, my list. Which has range 100. I'm initializing it with 0 to 100. So for each of the items, I need a list, filtered list. Item for item in my list. And I can put a condition. What's the condition we want to extract? Let's say if item divided by 10 equals 0. It's a modulo. So what if it is divisible by 10? So only include items that are divisible by 10. This statement says we are actually filtering the item which are divisible by 10. So it's going to extract the item from my list if the item is divisible by 10 based on this condition. It's similar to saying in verbose language, if I want to write that, so for item in range, sorry, for item in my list, if item modulo 10 is equal to 0, then result list dot append of item. This is a verbose way of writing the same logic. This and this gives the same result. So it's a shorter syntax. Similar to this, we can actually call functions on specific items also. Let's say I will initialize my string with this is push. I give so if there is some function on strings called split. So if I do split by a character, it will split by that character. So it will split the sentence into this string into 2 sentences, which is divided by the dot. So it will split by dot. So if I don't give any character in split, it will default split by the space character. So this will give a list of words in it. Let's do some simple operation on this. So this word has dot at the end. Let me write a function to clean that. Clean word. I'm defining a function called clean word. Given a word, it returns word dot replace dot with empty string and then replace it. Let's just return from there. So if I do clean word of gives me this. Okay. I want to use this when I'm doing a split operation. Let's just do that. Just using the previous syntax, clean word of word per word in my string dot split. This will call this function on each of the words that are extracted from this sentence. And this did that. All went into lowercase and this got replaced. And let's say I want to filter again on this itself. I can filter if word clean word length of clean word of word is less than 3. So only include the shorter words. This filter is allowable. So it's filtering these words based on the number of characters in it. We can actually nest this logic also. Now we have split by words. Let's do a nested syntax. Now I'll just do clean word or I'll have to nest it like this. Once I type it down, then you'll understand what it is. Clean word of word per word in my sentence. Sentence is not defined yet. I'm just going to define it in some time. The later part of this statement. Clean word by word for each word in sentence. Dot split. So I have a sentence. I'll split by empty spaces. That will extract the words. How do I get the sentence? Is again through a nested logic. For sentence in my string dot split by dot. I'll explain this in a bit. Now what we did, so this entire thing, let's consider this as X. This is X, or let's say sentence. For sentence in my string dot split by character. Now we have extracted sentences. Then I will split by word. Same thing. Instead of this sentence, I'm going to use another comprehension like this. Word per word in sentence. So instead of this variable, I'm using this comprehension. Dot split. Sorry about that. Split by space. If I do this, it's only extracting sentences. If I replace the sentence with word and word dot sentence dot split, this gives me, instead of sentence, I'm going to use another comprehension. That gives me extracted words. In place of sentence, we are actually getting a list of words because we replaced sentence with this comprehension syntax. So this is how we can nest multiple things in parallel. So same logic we can write in plain for loops for sentence in my string dot split by dot per word in sentence dot split by empty print word or append I'll just use this. This is how it is. We can write this verbose syntax also. It's more clear. Just so you know, this is the power of Python. You can use simple logic like this. This is more complex to understand for humans. This is better. I would prefer doing this format rather than this format. But the functionality is available in Python. If you are more advanced, if you know your way around Python, you can use this syntax. So that's about the comprehension logic in list. So we can do the same thing with dictionaries as well. Let's try a simple dictionary, animal list. I'm going to define a list of tuples which have key value pairs in it. This is one item, one more tuple, the list. This is only a list. We are going to convert this list into a dictionary pair, and then add top. We have initialized a list with tuples. We have a list. So I want to convert this into a dictionary. I can do it this way. I would say initialize animals as a dictionary, and I'm going to use it in the comprehension syntax. Item of 0 colon item of 1 for item in animal list. This is how we initialize a dictionary with a list of tuples. I do animals. This gives a dictionary, but that is a better way. Instead of item 0, item 1, I'm going to use key and value. Instead of item here, I can actually have key comma value. Let's see. Yes. So one simple thing is, let's say I have a tuple. So why this syntax works is this is called unpacking tuples. Let's say I have a tuple object a comma artwork. Let's just say k comma v equals a comma artwork. If I just print k, this assigns to the first value and this assigns to the second value. Similar to this, we can have any number of arguments as long as the arguments match. Something else. This works. Even print of w works. Let's just try adding one more element here. This fails because this left index number of items is 4 and the tuple has only 3. And that time it fails. Why this other syntax of the dictionary key values worked is because key value animal list is a tuple object, tuple array. This object is getting unpacked into key and value. Key got assigned with A and value got assigned with artwork. So that's why this syntax works. So that's about the list dictionary comprehension. So similar to this, we can also use items in it. So this syntax, what if I want to change the structure of this into an array? So now I have animals dictionary, which has this. What if I want to extract this into these two items into another dictionary and put it in a list? Let's say I'll just demonstrate, then it will be clear. I can create a dictionary for item in animals dot items. There is a function called items for dictionaries, which gives me tuples. Let's just try to get animals dot items. These are items. Items will come as a list of tuples. Okay. If I just convert into a list, this gives me a tuple list. Same thing that we did. It's a reverse operation. We are going to create a new dictionary array of dictionaries for item in animals dot items. And this item will have letter as key, name as value. So this value and key are not defined yet. So this item is going to be replaced by key comma value. What this gives is a list of tuples. That tuple I'm unpacking into these two values, key and value, and I'm using that as X here. This syntax I'll rewrite in plain logic for key comma value in animals dot items. I'll define a dictionary, present dictionary. Result array. Present list for item or key comma value in animals dot items. Result list dot append of a dictionary which has letter as key and name as value. Print result list. This is the same thing. Same thing, I achieved it with the syntax. I'll write it again. I have this letter as key, name as value for key comma value in animal dot items. This exact thing is what I did with this syntax. And let's look into if-else conditions briefly. That's about the dictionary and list comprehension. Now let's look at a simple use case called FizzBuzz. So the use case is like I have to print 1, 2. If it is divided by 3, I need to print fizz. And then if it is divided by 5, if it's divisible by 5, I need to print buzz. If it's divisible by both 3 and 5, which is divisible by 15, then I need to print fizz buzz. The order will be like fizz 7, 8, and then fizz buzz like this. Let's do that in plain code for n in range 1 to 101, which is starting from 1 and ending at 100. I'm going to iterate through those items. And if it is divisible by 15, that means it is modulo 15 should be 0. That means it's divisible by 15. Let's print space. And then I'll do else. Again, if it is divisible by 3, and print fizz. Else, if n divisible by 5, print plus. Else, print n. It prints. And this logic works. Okay. So this is more verbose. We can actually shorten this a little bit. Same thing if I use else if conditions. If n divisible by 15, print fizz plus, I'll just remove else and put as else if. Elif n divisible by 3, print 0. Print fizz. I'll indent it again. This if condition also I'll put it under elif. It is divisible by 5, print bus. Else, if it is not divisible by any of these, print n directly. It's a shorter syntax. Okay. So let's say this is the advantage of having else if. We can have any number of else if conditions. At the end, we can have else condition. So this is else is not compulsory. Else I can remove. If it is not divisible by any of them, it doesn't print itself. Only it will print fizz and bus. So this if condition, let's say I'll remove this if condition. Try to see if it works. So this if condition is removed. Error. So else if cannot be used without an if condition first. If should be used. Else if comes as a second. We can stack any number of else if conditions, and at the end we can have an optional else condition. If none of these conditions meet, then the else condition gets executed. So the same thing, same logic of this fizzbuzz, I can actually execute within a single statement. Let's try doing that. Let's say I'll define n as 3. So print fizz if n percentage 3 equals 0. This is a conditional operator or ternary operator. We can say we can stack if conditions at the end of the statements. Fizz else also is required. If n is divisible by 3, print else n. This ternary operator should have a true value and a false value. This is the true value and this is the false value. And it gives fizz. Let's say I'll just change the n to 4. I'll again execute this and it gives 4. The syntax of it is I can actually initialize this into a variable also. Fizz if n divisible by 3, else n. This gives 4. If I initialize back to 5, now I'll add one more condition here. If n is divisible by 3, else inside the else, I'll have one more condition here. Instead of returning n, I'll again check bus if n divisible by 5. Else n gives plus. Let's change n to 3 and execute the same thing. Fizz. Let's change n to 4. Let's execute this. It gives 4. N to 5. Execute this. It gives bus. Now let's stack one more condition here. Before this, I'll add fizz bus if n divisible by 15. And then put else to this. Let's initialize n to 15. Fizz bus. Okay, now we have one statement that does all this logic. Let's put this for a loop of n. For all n characters, I'm going to use this logic. Of printing fizz bus for n in range 1,101. Just for all that. So all this logic of for loop has been replaced by one single statement. This is the power of ternary operator, but you need not always use this ternary operator. It's more easier and understandable if we use plain logic rather than stacking up these statements. It's also error prone if you use this. I just showed you this just to demonstrate the power of Python. So let me go into the Python shell again now. So we have chain data structures, list structure, for loops. We've covered till for loops and range functions. Okay, now we have to look into while loops in depth. So there is something called break and continue. So I'm going to demonstrate those things when we are looking into while loops. Let's try using some library called datetime. So there is something called datetime library in Python. By default, it comes with Python. From this, we can actually extract the current date and do date manipulations. From datetime, I'm going to import datetime. Let's just see what this datetime gives. Datetime has a function called now, which gives us the current date in the datetime format. We can actually find out the number of seconds, number of hours, the current hour, current minute, current second, and everything. So let's try to get the seconds, and let's try adding some number to it. Say I'll add 4 seconds to it. The current seconds plus 4, 8. So if I just print current seconds, 4. So by the time I issued this, there are 2 seconds have been passed. So what if there was a second time which comes around 60 or 56 or 57? Now if I added 57 plus 4, it becomes 61. So but I need to make sure that second time seconds is like after 60, it will come from 1 right again. For that, I need to use something called the modulo operator we have seen earlier. Let's just see. Modulo 60. So if it is 61, 61 divided by 60 will give us 1 as a remainder. So that means it will become 1. Now this time, this works for the current second. What is the current second number? Let's use this in a while loop. For now, let's just say, so I'll create a while loop that will wait for like 4 seconds. before coming out of the loop. So let's write a while loop now. Date time now. Dot seconds. Not equal to the seconds. Same thing. I'm going to copy. I'm just going to wait for 4 seconds. This loop will wait for 4 seconds. So this statement, if I use it here, it will loop forever. So, but before that, I should write things like this. Let's say I'll add for 10 seconds here. This will be the like end time, end seconds. The current seconds, number of seconds plus 10 seconds is what the interval I want to run. So I'll write a while loop, date time, but now, but second, while it is not equal to the current 10 seconds, which means 4 seconds or 10 seconds past the current second, it will keep waiting. Let's say I'll print waiting. This thing may not run right now because we have done it keeps on running till it becomes 10 again. If we see while doing this, if I print the second interval, date time dot now dot second, and then I print waiting. Let's see what it prints. 37, 38, 39, 40. It's waiting till that 10 seconds. The loop is running for 10 seconds. The start time was almost 36. So in that, every second, it is actually iterating so many times. That fast the code runs. So this while loop is running in a second this many times. If you see the output here. So that's the speed at which our processor works. So let's say I'll just not print anything and break out of the loop only when the end seconds has moved. I'll just remove this and put a pass statement. Pass actually means nothing. So instead of printing, I can just do one, let's say something like 1 plus 1. It's not a problem, but unnecessarily we'll be calculating things. Yeah, we'll be wasting processor time. So I'll just do a pass statement here, which means no calculation, do nothing. So it waits. If you see this, prompt is not coming. The while loop is still running. This condition is true. Once this becomes true, then it will come out of the loop and comes here. A prompt comes. In another terminal, I can open and see what's the current time. Right? From date time to report. Date time up to now. Second. It's 53. Okay, now it came out. So let's write this logic in a different way. I'll say while true. So while true actually means this is an infinite loop. Unless we break out of this loop, the code will not come automatically out of this loop. It keeps on printing something. Let's say I'll just do a print statement here. Something. break, or I'll not do any break. This code runs forever, keeps on printing, and it uses up all the CPU that we have. So I'm going to cancel that now, cancel it. So this is how we create an infinite loop, but most of the times will not, it's very dangerous to create this kind of loops. While true, I'm going to write, so if I just say break here, this code runs only once, print high, and then break. This code runs and the statement will break out of this loop. It just prints once. This loop runs only once. As soon as the interpreter sees the break statement, it will break out of the immediate loop that is in. So let's write our logic of waiting for the seconds to pass until wait time. If date time dot now dot second is equal to wait time, then break out of the loop. Otherwise, just stay in the loop and not print anything. Wait time. Wait time is okay. This is end time. What did we define it as? Let's define end time one more time. Okay, end seconds is what we defined it as. End seconds. This loop will run till that time. It's still running. Let's go check the second now. 33. So as soon as this condition becomes true, the break statement gets executed. Break actually means come out of this loop. See what's the time? Yeah, it came out of the loop as soon as this seconds interval became equal to the end seconds. So that's the demonstration of break statement. There is something called continue statement. For the same purpose, I'm going to use a simple calculation here. Let's just add a counter here. Instead of using this seconds and break, we'll add a simple counter. Count. I'll initialize a value count as 0 while true. Count plus count equals count plus 1. So one more optimization we can do here is, instead of writing like this, we can actually write it like this: count plus equal to 1. This actually means count is equal to count plus 1. This is a shorthand for writing count plus 1 for count. Now, if count equals 5, or if count is divisible by 2, then continue. Don't print even numbers. This means don't print even numbers. Continue means it will skip whatever lines that we write after this statement and iterates with the next loop, next iteration. Let's try printing n here. count. Now, if this condition is met, the continue statements get executed, and which means that don't continue doing the below statements, just skip them and start from the first line iteration, next iteration. Let's try running this and let's break out of this loop. If count is greater than 100, break. So it goes till 100 and then breaks out of the loop. Now, if we see, it printed only odd numbers because we skipped printing even numbers with the continue statement. Yeah, this is how continue works. Then now we will come back and look at the for loops in depth. Let's say I have a list, my list, 1, 2, 3, 4. For item in my list, print item. This we all know how this works. Let's try doing something similar with a dictionary. I'm initializing this dictionary with A as an array. And below B to pair, C to cat, D to dog. So this is a dictionary. Now I'm going to write a first statement that iterates through this and does nothing. For letter, an animal, an animal lookup, just do nothing. We have seen past statement earlier. This time, sorry. Actually, we should use, if I'm using a dictionary, I need to use dot items. Dictionary is not an iterable or extractable like this. Only the items will be written as. Yeah, once. Yeah, it's array and list are same. My list, if I'm array and list are same. List. I mean, what I meant by array is list. List actually, it's a analogous to C language arrays. So in C language, we call them as arrays. In Python, we call them lists. Somewhat similar, but not same. So if I see animal lookup, this is a dictionary. So array definition is like a list of similar data types, but in Python, it's not strictly necessary to have same set of data types in an array. It's an array is an iterable object, a list of things. Array or list is interchangeable. I'm calling array itself as list in Python. So when you see C and Java, arrays are different. There is list is a different data structure in Java. C arrays are same data types we should use in. If I'm using integer data types in the array, all the elements in an array should be integers in C language. When it comes to Python, we can have any type of element in the list. List is an iterable object. We can iterate through each item. So coming back to the animal lookup. So if I want to print the list of items. I can just iterate through these things. Letter, comma, animals. In animal lookup dot items. This items gives the list of tuples. If I just remove this and try printing animal lookup dot items, it gives a list of tuples with first element as the letter and second element as the list. So that is what I'm going to use in a for loop now. For letter, for each letter, I have a list of animals in animal lookup dot items. So I'm going to do some check here. If length of animals is greater than 1, continue. So this actually means for any letter which has more than one animal in it in its list of values, don't print that animal or letter. If not, print the animal letter and the value. This we have seen earlier. I'll explain one more time. This print statement uses an F string. So F strings can use any Python variable or function inside this curly brackets. When I'm accessing letter, it actually replaces the value, the statement, this entire string will be replaced by the letter value. Even this will print like this. Let's see how this looks. So it's printing B, C, and D, but it is skipping A because the length of animals list is more than 1. This is conditional logic within a loop. So we have seen break statement here. Oh, sorry, the continuous statement here. Let's see the break statement. So on the same loop, if the count, if I just want to extract only 2 items, it can be in any order. So I'm going to initialize a count value, count as 0. Every time I iterate through this, I'm going to increment counter by 1. So this is the first element. If count is greater than 2, break out of the loop. This actually means only extract the first 2 elements or like any 2 elements from the animals list, animals dictionary. Let's try that. So it has given A and B. Only 2 elements it gave us. Any doubts so far? Okay. There is a special scenario called for else loop. So let's try creating a new loop for number in range 2, 100. We have seen range functions. It gives a list of numbers starting from 2 and ending at 99, excluding this 100. Let's try to find if any of these are prime numbers. Let's say we have to find out if this number has any factors that are exactly divisible, that are dividing these exactly. Per factor in range, actually in order to find the prime number, we have to, if a number is prime or not, we have to find out all the factors that are below its square root whether they are dividing this exactly or not. So the same logic, I'm going to write it here, starting from 2 till the numbers root, square root. Okay, before going into this loop, let's try to find out the square root of a number. Let's say I have number 4, number is equal to 4. How do I find out square root of this number? So square root of the number is nothing but power. The power is 1 by 2, half of its power. Let's say 4 square is 16. 4 in raised to the power of 0.5, which is 1 divided by 2, same as 0.5. This gives me the square root of this number. 2 is the square root of this number. Similarly, 3 square root, if I want to find out, this is what it is. Square root of 2 is this. So now I have to find out, I'll just wrap this up into an integer, 2 power 0.5, sorry, 2 power 0.5 is 1.414. Okay, so now I just wrap this into an integer, say 4 already, square root of 4 is 2. So that I'm going to use in this logic. So now for number in range 2, 0, 100. 0, we know that this is all prime numbers start from 2, range till 100. For factor in range 2, the maximum range should be number into 0, power 0.5. This should be converted into an integer because it gives a floating point number. Any division or power operation will give a floating point number because we are actually raising to the power of float, which is 0.5. Now this gives me all the prime factors that are between 2 and to this number, square root of the number. Let's say 4, we have iterated till 4. It gives the number starting from 2 till 2, or like if it is 9, 2 to 3 it will give, but it won't include 3 here because the range function does not include the last element. If I'm saying 2 to 100, it gives only till 99. So this thing will get excluded. So that's why I need to add one more element to it, one greater than the square root of this number. This means it goes till from 2 till the square root of that number, which I'm evaluating whether it is a prime number or not. If I want to check if this number is prime or not, so I need to verify if this factor is dividing this by exactly or not. If the remainder when I divide the number by this factor is 0 or not. If it is divided by this, then it is a prime number. When let's just print this is number is prime number. Number is a prime number. Sorry, is not a prime number. Sorry. If none of the factors can divide this number by divide the number exactly, then it is a prime number. If it is divisible by the factor, then it is not a prime number. See, we can see that we are actually finding all the numbers that are not prime numbers. So remaining ones are the prime numbers. Let's try doing this then. Now, if I want to negate this logic, I just want to say like I'll initialize a value called is prime equals false. Okay, is I'll just initialize it to true. and is prime equals false, break. And here, if is prime, print number. This gives the list of prime numbers till 100. This is fine. So there is one more better way to write this logic. So that's what I'm going to demonstrate here. So instead of writing like this, I can just remove this, and even this I can remove. I'll just write one thing and then I'll explain. Print number. So what this means, else, for else, this is called the for else loop. So if this for happened without any break, this code runs. If the for loop runs without any break, if all the things are run without any break, then this else condition will run. If for loop is breaking out of this loop, the else condition will not run. So actually means if number is divisible by the factor, then it breaks, right? It's breaking means this else condition will not run. So the number will not be printed. If this continues and it did not go into this break statement and this else condition runs, let's try running that and see how it looks. 2, 3, 5, 7. It's giving the correct prime numbers. This is an advanced way to write for else loops. So if for loop runs without any breaks, the else runs. If the for loop breaks for some condition, then this will not run. Either do this or do this is what it is. So if this thing did satisfy a condition and break out of the loop, then this particular statements will not get executed. That is for else statements, for else loops. And that's about the for loops. Let's now take a look at functions. So we have already seen functions. Let's go a little bit deeper into functions. Let me define a function. The definition of a function starts with def. And let's say I will write perform some operation. Functions usually are used for reusable code. Every time if I want to write some similar logic, I don't have to repeat the code and I can write that code in a specific function and then call that function with variable arguments so that I don't have to repeat the code in writing. So let's say I will define a function that does some operation, either a sum operation or multiply operation. Perform an operation on number 1 and number 2. And I will also specify the operation as an optional parameter. As a parameter, yeah. If operation is equal to sum, then return number 1 plus number 2. If operation is equal to multiply, return number 1 multiplied by number 2. And how do I call this function? Is through perform operation of number 3 and number 4. I will add sum as the argument, sum of 3 and 4, and multiply as another call. Okay, this is default definition how we write a function. So there are things that we can do if I want to say what is the default operation that I need to perform, even if somebody is not giving that operation itself in the arguments while calling the function. Let's redefine this with a default argument. So in the operation, I'm going to define the default operation as sum. If somebody is calling this function without providing the third operation parameter or argument, by default it does summation operation. So let's do 3, 4 and skip the operation field itself. So perform operation. Perform operation 3 and 4. It's by default doing a sum operation, returning this statement. I can also specify this statement. If I provide operation as multiply, it does multiply operation. And now, what if I want to have one more argument? Let's define this to have one more argument. The significance of it, I will explain. Message equals some message. Now I'm going to print that message here. Message. Print. Sorry. I'm going to call the multiply operation. It's printing some message. Okay. Now I want to customize the message also. I can pass it another message like this. So this is one way to call this function. So there is another way, explicitly mentioning the parameter name also. Let's say operation is equal to multiply and message is equal to another message. Okay, so good. So what if I switch these things? Another operation. If I want to change the order, I can do that when I'm specifying the operand argument name. I can actually switch these, or in any order I can pass, as long as I'm giving the correct argument name. I can pass the message in any order. So message, I can pass it as pre-ordered message. So usually num1 will be 3, num2 will be 4, because I'm passing these as keywordless arguments. This is the keyword arguments, which means there is a name to it and a default value assigned to it. If I define it like this, I can pass it in any order I want. This is for like long functions which have multiple keyword arguments. It doesn't matter which order you pass it in, as long as you are passing in the name of the argument and the value of the argument like this. Now, if I call this function, it does the same thing. So order does not matter. When we are not specifying the default keyword and value, then the order matters. So we have to pass the arguments in the same order that they are defined. So let's say now I have a function. Let's define a function that has multiple arguments of it. Perform operation of arguments. I'm just giving a name as arguments and just print arguments. So if I just want to pass multiple parameters, 1, 2, 3, 4, 5, doesn't allow. So there is one way to handle this. Instead of args, if I define this as star args, this means this function can accept any number of arguments. Let's try running that now. Perform operation with 1, 2, 3, 4, 5. Like 5, it can be like 6, 7, and any number you can pass. That all those things will become a tuple in the args object. So there is one more similar to this about the keyword arguments. How do I pass keyword arguments? That is through KW-args. I define ** KW-args. I'll just print kwargs also here. Let's try calling this. Okay, kwargs is empty because these are named. Kwargs will receive named parameters. Let's try giving names. My argument 1, named argument 1. Oops, I or 2, something else. For now, call this function, and this named arguments will become a dictionary. kwargs will receive a list of a dictionary of named arguments as key value pairs. Each key of the named argument key will come as the key, and the value will come as the value. So this is how we pass multiple unknown number of arguments and unknown number of named parameters. Any number of named parameters we can pass, and if it is found in kwargs, we can do some operation. So let's rewrite our mathematical calculation logic with this star args method. It can accept any number and it will sum all that up. If it is multiply, it will do a product of all that. So for that, I'll just import math library. This math.prod accepts a list of numbers, and it will give me the product of all those numbers. So those two arguments. Okay. So if you need help, we can list the help of math library. You can see all the functions it supports. So I have seen earlier prod iterable object, and it accepts list also. So if you pass it as a list, it will work. So earlier I was passing it as numbers. I should now pass it as list of numbers. It gives me the product of all the numbers that have been passed in that list. Okay, nice. Let's use that math function. Math. So let's define a function called perform operation, and I'll define arguments. I'll define operation as sum as a default. If operation is equal to sum, there is a default function in Python which is available on the global scope, which is called sum function. I can perform this sum function on these arguments. If operation is multiply, I can make use of the math library, return math.prod of args. Args is already a tuple or a list, so that's going to be fine. Let's do a perform operation on list of arguments 1, 2, 3, 4, and operation I'm going to give sum. Yeah, this is working correctly. And then if I just change this to multiply, let's run this, and it gives me the right answer. All right. Okay. So now we have to look into the scope of these functions. So there are args and kwargs we have defined earlier. And now let's rewrite that code. Perform operation like args and kwargs. kwargs will have to have 2 stars. 2 stars means it's a dictionary. 1 star means it's a list. In args print marks. So while doing this, let's also print the locals. And there is something called locals function, which gives all the local variables of this particular function. Within this scope of this function, what are all the variables available to it. And let's do that, call that operation, perform operation, increment to sum. And local variables, locals is getting printed like this. So arguments is available, kwrx is available to it. So all the local variables within this scope are printed. Now there is something called globals also, which prints all the available variables and values in the entire context of this program. Let's try running that. And these many are there. So there are default global values which will be used in the future. So the name of the file that it shows, main function, it's actually the name is main here. So in usual scenarios, when we are writing code in text editors, we define functions like this, and then we will use something like if underscore name equals main, call some function. This is mostly used in production. So when we define all the functions like this, and then call the functions if this file is being run as a main function. So this will go in depth into later. So just to know the global context, what all variables will be available in global context, we can print globals, we can call globals method or function, and we can see all this. Let's see if this has any function definitions. And this has source files and everything. So there is a way to get the source of the current file that we are running also. So we'll go into that in a few minutes. And let's define a global value. Let's say I have a message. This is defined globally in the entire Python context. Some global value, message. And I'm going to define a function or I'll define a variable A with value 2. This is all defined globally, not within a function. Let's go define a function called function1, variable A, variable B. And this var A and this var A are different. I'll demonstrate that now. So I'll define another message here. Within this function, some local data. This message and this message are different. So this is globally defined, and this is defined within this function, and this is also, these two also are within this function. The scope of it, I'm going to demonstrate which one is available where. If I print var A, and print message, and then print locals, this gives a list. I'm going to call that in a few minutes. Let's define another function called function pool with variable C and variable P. And print var A here, which is not defined locally. This var A is actually going to be this value. I'll show you in a few minutes. Let's print message also. It's not written, that message is not defined here in this function. So this is going to access this message. And let's print locals. Now let's call function 1. Sorry, function 1 with arguments 1, 2. So it has printed var a, which is variable a is 1, message is some local data, this message, not this message. This message has overridden this scope. So while this variable is found within this scope, it won't go access the global scope. If the function does not have that value, then it will access the global scope. If there is something locally defined, it will use the local variable itself. So if I see the locals here, var a is defined, var b is defined, and message is defined. Var a, var b, and message. If I do the same thing with function 2, I'm going to pass 1 and 2, same values, while this accessed var a is not defined in this scope, only var b and var c is defined. So if you see here, var c is local. If you see, this statement has printed this. Var c is available, var b is available, which is 1 and 2 respectively. And message is not defined locally. It is actually available from the global definition of this message. So it's accessing the message from here, not from anywhere else. So if there was a message defined over here like this, it would have accessed the message from here. And var a is not defined within this function, so it tries to access from the global scope, which is value is 2. So that's how the scope works. Is that clear?
Yes, sir.
Sir, once again explain, sir.
Okay. So function 1, I'm defining a value called message and var a as 2. If I define a function, let's remove all the statements. Let's try printing message here. Function 1 and comma 2 I'm passing. And this prints message from global scope. Let's try redefining the function with some message over here. Same variable name I'm going to use and some other message I'm going to use. This is local message. Okay, now call function 1 with 1, 2. Function I defined and I did not print it. So define this and print message. Let's call the function 1, 2. So this actually printed the message from here. It did not access the message object from here. Which is globally defined. So if a variable is defined within a function, it will access that variable itself. It won't access the global variable. Understood?
Yes, sir.
Yeah. And there is something called globals function, which gives us the entire global context of this Python script. The entire shell has these values in it, default values. And if inside a function, if I do locals, print a locals, print locals, it gives all the local values, local variables. When calling that function, local variables are these. Var a and var b are local variables. So let's demonstrate that even further. Now let's define a new function. Function 1, same thing, var a, var b. And message I'm defining as some local message. And print of var a. And I'm defining another function within this function. It's possible to have nested functions also. I'm defining another function called inner function, like this. It accepts var A, var B. This var A and this var A are different. It's not the same. This is to demonstrate the preference of the scope. So which will be preferred? If I just print something here, some f string values, inner function gives me within the inner function scope, the values are like this, locals. And out of this, print locals. So this local statement is not part of the inner function. This is part of the function one. So based on the indentation level, this scope changes. So I'll call inner function from here. So this doesn't get called unless we call this function. When we call this function, this goes through these statements and defines this function in the runtime and calls that function at the end. Let's try running that. Function 1, 2. And here we forgot to call the function with the arguments. So we have to give some set of arguments to var A and var B here. That was a mistake. 1, 2, 3, 4, 5, 6. I'm going to use. Let's run this function. And when we are seeing here, in the function one context, in the inner function context, this is the statement. In the print locals in function one, this is what it had. So if you see here, var A is defined, var B is defined, message is defined, inner function is also defined. So inner function also is a variable for function one's locals. If I see locals, it includes both variables and functions defined in that scope. This gives us a concept now. The variables can also be a function. Let's do that in a few minutes. Let's look into this logic in a few minutes, but the scope, if we understand better, then it's easier in the future. So if I try to run this inner function here, 1, 2, 3, 4, 5, 6, I cannot run it because the scope of it is defined within this function. So this function, inner function, is available only to the code that is written within this function, not outside of this function. So the scope of this thing is not visible outside of this function because we have written the definition of it within this function. So now let's look at this specific statement. So why is this inner function coming as a variable within this locals object? Let's see this. Now I have a variable called x equal to 5. I can also have 5. I can have a function defined, but it need not have a specific name to it. That we will do next. Let's say I define a function called x that says return 5. X, if I call, this gives 5. That's good. Can I store this function in a value or a variable? We can. If I say something like, let's define some set of functions here. Have function 1. For demonstrating that, I'll just show you a list of functions you can write. Print 1. The function 2. that prints 2, function 3 prints 3. Now I can have a variable list of functions equals an array. I can have function 1, function 2, function 3. What I just did is I'm just adding all these functions into an array. So this list, sorry, array or list, this is a list. So if I just print list of functions, this is a list. So this is actually assigning the value. This value is the address of this function. We will go in depth into addresses and references later, but just this representation gives us the list of function addresses. If I want to call these functions one by one, I can just iterate through this list of functions for func and list of functions. This is just a name I've given to the value. This can be I or A or B or C. This F or A, B, C, anything it can be. For each function in list of functions, I'm going to call that function like this. Let's see. It's calling function 1, function 2, and function 3, which is in turn performing these print operations of 1, 2, and 3. This is how we can store functions also into variables. Let's say I define a function. I'll define some function print this is some text. Now I can store that function in a value, in a variable like this, x equal to some function. Now if I call x, it's going to call that function. If I call some function, it's going to call that function. So what I'm doing here is I'm just assigning the reference of this function. By default, the function's reference will be stored in its function name. So what I'm doing here by assigning some function to x is the reference to this function I'm assigning to x, which is equivalent to assigning the same address to x. So if let's say I'm defining a variable called y equals 5. So this actually is storing value 5 in some address in memory. I'm assigning that address into y. So if I'm trying to print y, so what the interpreter is doing is it's reading the address of y and reading the data from that particular address. If address of y was like 1002 or 1003 in memory locations, so it's reading from that location and printing it. If I do x equal to function 1, what this is doing is the address of function 1 I'm assigning to x. If I'm doing x operation, what interpreter is doing is it's extracting the address and extracting the code within that address and running that code here. Okay. So the variables can also have functions referring to it. So there is a simple another way to define functions. Traditionally we do with function 1 and comma 2 comma variable v1 equal and v1. We do it like this, right? So there is another way to define functions in a shorthand operation. If it accepts only specific arguments and returns only one value, we can do it like using lambda functions. So we are defining always a name to a function. We now need not define a name. So this is the format to define a function on the fly. Something called lambda functions. This is called lambda functions, the definition of which I'm going to demonstrate now. So it should start with lambda. and some number of arguments. So I'm going to use X as a, or like V1, V2 as arguments, and colon V1 plus V2. So this is the result, return value, and this is the list of arguments. Let's try running this. We should put the brackets in it. Sorry. X colon missing two required position arguments. Let's define that like this. Lambda, I'm defining lambda X returns X plus 1 into 4. Okay, the problem was this. Okay, I defined a function called lambda. I'm giving value 1, value 2. I'm returning value 1, sorry, value 1 plus value 2. And I'm calling this function, but not providing the values for V1 and V2. That's the reason it failed. So let's pass something 1, 2, 3, 4, 5, 6. Perhaps we forgot a comma. Okay, I think we should put brackets here. Let's syntax. AMBDA, sorry, there was a spelling error. Let's try running this like this. Okay, now it works. So the way to define it is LAMPDA and the list of arguments that we want to pass to the function, an equivalent of def function 1, V1, V2, return V1 plus V2. The same function, I can define it like this: lambda, LAMPDA, lambda, V1 comma V2, colon, V1 plus V2. This can only have one statement in it. We cannot have multiple statements, only one statement here, which is the return value. So in order to call this lambda function, I can call it like this. And with values 1, 2. The arguments V1 and V2 should be passed like this. And this gives me 1 plus 2. So here, actually what I'm doing, I'm defining the function on the fly and calling that function on the fly in one statement. Instead of writing a definition again and then calling that definition of the function, I'm writing a lambda function, which is one line of code to do simple operations. These are called lambda functions. And now let's look into classes. So we have seen the dog class earlier. Now we'll look into the inheritance of classes. Classes can have subclasses. Let's define the dog class that we had seen earlier. Def init. Init is a constructor which accepts self as a default argument. First argument in a function, in a class function, should have self in it. Self means the reference to the current object it's going to pass every time. So I'm defining a name, giving a name, and I'll assign self.name as name, self.legs 4, and I'm going to define another method within it called speak, which also accepts self. These are called instance methods. So there are static methods also available. I'll go into that in a few minutes. What is static methods and what is instance methods? These are actually instance methods. These instance methods will always have self variable as the first argument. And this one, let's print self.name says path. So let's define a dog object like this. I'm going to give the name as Rex, dog dot speak. Okay, now we have a dog object. So we have seen the instance variables here. Let's define the same thing with static variables. What do we mean by static variables? So if a specific property belongs to an instance of the class, so the name actually belongs to a specific dog. It's not in general, not all dogs will have the same name, but usually all dogs will have 4 legs. Those kind of properties we can put under the class as a static variable rather than as a dynamic instance variable. So I'll just remove this legs from the stack instance variables list, remove from here and add it over here, legs as 4. So by default, all dogs will have 4 legs. That's what this means. Now, same thing I can do, dog of legs. Dog dot legs, if I try to access, it gives 4. So in the earlier scenario also the same thing happened, but it was accessing an instance variable. Let's just try to see, create one more dog item. Dog, new dog, dog of new dog. Now let's try to manipulate the legs object over here. Legs 2, 3 I will make. Let's try dog dot legs. But still the dog dot legs is 4. When I did through this new dog object, it only changed the instance variable of it and not the static variable of it. So when I'm defining legs here, it's a static variable. If I access the variable with class name, it will always access the static variables defined over here. If I access with the instance name, instance object, it will access the instance variables. So new dog dot name, if I do, this is new dog. Dog dot name, if I access, this will give me the legs, which is this. And if I try to do the same thing with dog, if I do, so as I've changed new dog dot legs here, let's try changing the class legs. Dog dot legs is equal to 6. Here I'm actually manipulating the static variable within this class, which means it's globally for all the dogs. Now let's say if I change or create a new dog, third dog, dog 3, and create a dog object with name as AA, and dog 3 dot legs, if I try to access, it gives 6 because we have changed the global static value of this dog class. The global property of this dog is that it has 4 legs. Now we have changed that property to have 6 legs. Now by default, all dogs will have 6 legs. That's the kind of logic how it is. So the global values defined within the class will take preference if there is no local instance values specified. Similarly, if I have, let's say, this object is there and I'm creating my dog, this dog as legs, my dog dot legs, if I access, I haven't changed anything over here now. It still has 4 legs. Now if I set the legs to 4 or 5, if I now access my dot legs, it gives 5 because it's an instance variable. We haven't changed the class static values. This actually means when I'm trying to do this way, what it actually means is it's like assigning self dot legs equals 5. That's what it is doing. When I'm changing the value with the instance object, it changes only for that particular instance, not for the entire class. When I'm doing it with a class name, it does for the entire class. Whenever new objects get created from this dog class, all those objects will have default lex as 6. So that's the difference between accessing values from instance objects versus accessing values from the class objects. So this is kind of a dangerous operation. Like default properties, nobody should be able to touch these default properties. So a convention in Python is to define values that are not modifiable as starting with underscore. This is only a guideline, but the users can actually change these or overwrite these. So this actually means that nobody should change legs value directly. So they can do operations on instances, but not on class variables. So now if I want to give them a wrapper function to access this value, let's define another function, get legs. This I can do it with an instance, do it as an instance function. And this can access self dot return self dot underscore legs. This is perfectly valid. Now if I define a dog, dot get legs, it gives me 4. Fine. Now let's define one more class to demonstrate static methods. Now we have seen only the instance methods which accept self in it, but we haven't seen static methods yet. So let's define a class which has static methods in it. Let's write a class called word set, which has constructor initialization, which accepts self as a default argument. Any constructor, or this is called a constructor. Init function is a constructor for every class. So I have defined an instance variable called words. Within that instance, self.words, I'm defining it as a set. Set by default has empty set. And sorry, I'll define another function. So definitely add text to the word set, which accepts self as a default argument, first argument, and also one more thing, text on one pass. This does something like text equals self dot clean text. So clean text is not defined yet. I'm going to define that in a few minutes. And after the cleaning of the text, for each word in the text, we have already seen this. For word in text dot split. Split by default splits a sentence by spaces. If each word will, if there is a space, it will divide the sentence by space. So all the words will be coming as a list if I do text dot split on a sentence. Let's do self dot words dot add of word. So this add function is a default property or a default provision of the set data type. So words is a set data structure. We can call add function to add a specific word to that particular set. That's what we are doing here. Now let's define another function which we have defined here, called here clean text, which removes all punctuation and everything. This is also a instance function. That's why we are passing self to it. And then let's do text replace. Replace all the punctuation characters, exclamations by empty strings, and then replace. This is called chaining of functions. We can call functions on this, returns a text object which removes the exclamations, and then on top of it we are calling one more replace all the dots with empty strings, and then replace all the things starting with the comma, empty strings. Yeah, that should be enough for now. After doing that, return text dot lower. So I'm done placing all the letters into small letters. That's about this function. Let's try running this. Create a word set object. It's an instance of word set. I'm going to call word set dot add text. Hello world. This is some sample text. Let's try printing word set. Words. Okay, this gives me all the list of words. So the thing here is this add text has to have instance variable self because it's accessing self.words. And this clean text is a generic function. It doesn't access any of the values or variables or methods from this self function. Now we can make this thing as a class method rather than an instance method. Let's redefine this class and remove the self value from this. Now this is a static method. This is a class method or a static method. Both are one and the same. And whichever function has self as an argument is an instance method. So we can call this method only on instances, while this method can be called only on class objects. Now let's try running this and see if there is an error. So we are trying to access this clean text method with the self context, which is on the self instance variable. Let's try running this with create a new word set and then add the same text. Now if I do the add text, it's trying to call clean text, takes one position argument, but two were given. When we were trying to access legs from the self instance value, it did not fail. When we are calling the static methods with the self instance variable, it will throw this error. So for that, we need to replace this with the class object itself. Word set. Instead of self, I'm going to use word set. This is how we call class methods. Class methods are static methods of a class. This is the class method. Let's try doing this one more time. This time with word set, then add text. It works. Now print word set dot words. Now this works. So all the utility methods can be made as class methods or static methods. So any method which doesn't have self as a first argument is a class method and can only be accessed with the class name, not with the instance name. So if I try to do clean text on an instance, let's say word set dot clean text of this text, this doesn't work. When I do the same thing with capital W word set actually is the class name. This will work. This gives me the clean text. So any class method or static method can be accessed only with the class name. That's what we have to know from here. And that's about classes. And one small concept we are going to introduce here. Classes can inherit from parent classes. This is a very important concept in object-oriented programming. Now we have seen dog class. Let's go redefine dog class. Here we have a class, dog class. Redefined it now. So let's say I want to have a small dog which doesn't bark. So I can extend from that same class and I can define a class called small dog. And I can inherit all the properties, all the methods from dog class. The way to do that is through this way. Small dog, it extends dog. And I'm not going to write anything over here for now. I'm just going to put pass, which means do nothing. Now I'm going to define a small dog. Small dog equals small dog. This is called inheritance. Name it should accept. It's trying to call init object, init function with a name. So I'm going to give a name as my small dog. Call that. Now st dot get legs gives me 4. st dot speak says my small dog says bark. Okay, now so I don't want the small dog to bark, and I want this to say like I can't bark. Let's override the functions. Instead of defining small dog with pass, I'm going to override the definition of speak over here. Self, and then print self.name plus says I cannot bark. And that's the only method I'm going to override. So now if I initialize an object, small dog equals small dog. I'm giving a name as small dog. And if I call small dog dot speak, gives me small dog says I cannot bark. And if I try to access one more method, get legs on this small dog, it gives 4. This method is getting, this small dog is getting this method from the parent class, which is dog class. So all the properties and functions, methods of the parent class will be inherited by the small dog, which is a subclass of this. This is called a subclass. When I'm inheriting from a parent class, this becomes a subclass of this parent class. So all the properties, attributes, methods will be inherited in the small dog. And if I want to override a specific functionality, I can override only that specific functionality over here. That is what we have done here. This is about inheritance. We'll go in depth into object-oriented programming, extending the built-in classes and everything in the later classes. Till now, we have been using the Python shell directly so far. So we have defined a class called dog yesterday, last time. So this time I'm going to use text editors and then execute the Python scripts from the shell. So I'm not going to use the Python shell directly. Let's go back to where we left off last time. So we have seen data types. The last topic that we discussed was the classes and inheritance. Let me go. Okay. So this time I'm going to repeat what we discussed in the class inheritance. Let me create a new file, main.py. So here, last time we have declared a class called dog, and this was a parent class. We didn't have any superclass for this, and we had defined another small dog class. But before that, I'm going to explain this one more time so that it's clear. So dog class, I'm going to declare a class attribute called legs. So usually how we define class attributes is directly under the class. And if I define something like init, so this is actually called a constructor. Init is called a constructor. This is a method inside a class. So inside the class, if I write any function, it's called a method. So here, if I declare a variable with name, this will become an instance variable. So this means any instance of a dog will have its own copy of this name, whereas this variable is at the class level rather than at the instance level, because all dogs will have 4 legs. That's a default property of a dog. So each dog might have a different name. That is why we have defined it as an instance variable. Let's write something, and if I have to configure this, if I have to accept it as a parameter and use a dynamic name, so I need to also accept a parameter or argument for this constructor method. So whatever I use here as arguments, those things need to be passed while constructing an instance of this object. Let's say I'll use the name here. So when I'm actually creating a dog object, so dog equals dog, the name parameter has to be passed from here, Rex. So I can actually name it like name equals Rex. This is also allowed. You can explicitly mention which argument are we passing. And if it is not named, it depends on the order we pass. Let's say I have another thing called age. I can say like another parameter like this. So this depends on the order. So if I'm not using the named parameter format, it depends on the order that we are passing. If I'm not using this order, I can just use age as 5, name as Rex. This is perfectly valid. If I'm not using the named parameters, I need to pass them in order. Age as 5. So sub.age, age. So I have also defined a method called speak. Under this, every method in an instance will accept a default first parameter as self. Self means this instance of the object. It refers to itself. So self. So we also have discussed the F strings. I'm going to use an F string here. By default, I can use single quotes or double quotes. If I'm using single quotes, when I'm typing down inside here, if I have to use double quotes, I can use it directly. If I'm using double quotes, if I type it down here, I cannot use double quotes inside it. If I have to use double quotes, I have to escape these quotes with backslash character, like this. Similarly, if I'm using single quotes, if I have to use double quotes in the middle, I can perfectly use it. If I have to use single quotes again, I still have to escape these. So as you can see, this color is different because the string starts here, ends here. If I am using a single quote, starts here, ends here. So if I have to escape, this is how I need to include these quotes inside the another string, another quoted string. So I'm going to use F strings. The advantage with F strings is I can actually use any expression, any Python expression within this F string, within this opening and closing brackets. Self dot name says bye. So this gets replaced by this particular name. Okay. Now, if I do dom.speak, I've written simple code, simple Python file here. So how do I execute this file? Is I should call Python and with the file name main.py. So it executes. These are the lines that it executed. So if I just keep this declaration and don't have these commented out, let's have these commented out. Even when I execute something like Python main.py, it doesn't do anything. We are just declaring a class and implementation details I'm giving. So I'm not initializing that object or executing anything. So this still is executed, but actually it doesn't have anything to print because we haven't instantiated any object of dog type and we haven't called any method on it. So this calls the constructor. So when I'm passing two arguments, this calls the constructor. Okay. So this part is clear, right? When we are instantiating, we are actually calling the constructor method. This init is called the constructor. So we have initially instantiated, and that's about declaring a class or an object. So this is a class, and an instance of a class is called the object. Dog is now an object. Okay. Last time we have already also seen the inheritance mechanism. Let's demonstrate that one more time now. So I'm going to create a small dog that extends the functionality of the dog. So how do I declare it? It's like this. If I'm putting this, any object or any class inside the parenthesis of another class, this class inherits from the one that is passed in the brackets. So without having any implementation details, I can inherit all these properties on the small dog. So I'll just create an instance of small dog. Say I will just say Lipsel. It's 2 years old. Just going to call the same method. It can be anything, but my ESLint is showing some weird messages. That's why I renamed it. So you can use any variable name. That's no problem. So let me execute the script again. This is a Spark. So small dog inherited all the methods and constructors from the parent class, which is dog. If I add one more, let's say if I want to print age, self dot age, I am self dot age years old. So this depends on the implementation. So this, I'm just initializing the attribute, but I'm not printing it when I'm doing a speak call. So now it will print. If I do that one more time, I'm doing this old. If I have to extend this functionality, instead of putting it here, let's just remove this from here to demonstrate the inheritance mechanism. So I don't have the implementation of printing the age in the parent class. So I can override this functionality in this subclass. This is called a subclass or a child class. This is the parent class. And I'm going to re-implement this functionality and have that do something else. So instead of printing like this, I'll just print I am self.age years old. Print I cannot work. Now, when I call small dogs or speak, it doesn't call this function, but it actually calls this function because this object is an instance of small dog. So I did a fronting class. Let's remove this and just put a pass here. I don't have implemented this, it's commented out. Even when I do small dog execution, this gets called. So same implementation, fine. Now I'll have a custom implementation which does also print the age for small dog. Let's do that now. So I'm 2 years old, I cannot bark. So instead of this, if I just call this dog, it doesn't print this because it is an object of dog type, not small dog type. Let's say Spark. Okay. So I'll just uncomment both these lines and execute now. Rex says Spark, and this says I'm 2 years old. Let me put the prefix self.name here. Okay, clear. Rex says Spark. Lucy says I'm 2 years old. Lucy says I cannot bark. So when we have the same method implemented, it overrides the previous parent class's method. Let's say I have another method implemented. Let's say print my what's your age. This line, I'm going to move it outside of here and put it under this. And it's called small dog storage. Let me execute. Lisa says I'm 2 years old. Okay, if I do the same thing on dog object, let's see. Dog dot what's your name? Dog object has no attribute what's your age. Because this class doesn't have that implementation. So when I'm inheriting a superclass, this is called the superclass or a parent class. This is a subclass or a child class. So when I'm inheriting from a class, this gets all the attributes, all the methods from the parent class. Whatever custom implementations I can do on the child class, I can do it. So the whatever implementation we did in child class will not propagate back to the parent class. So it's only up to this. Let's just create one more class called tiny dog, which extends small dog. This tiny dog will inherit from small dog. Small dog will inherit from dog. So let's say I will instantiate a new object called tiny dog. Instantiate tiny dog. Tiny. Tiny dog speak. I should comment out this because it will error out if there is any error. Okay. Text says bark. Lucy says I cannot bark. I'm 2 years old. Tiny says I cannot bark and I am on air. What's happening here is tiny dog is inheriting from small dog. So all the properties of, we haven't declared age or name or even legs in any of these subclasses. Legs is getting inherited from dogs. Name, age is getting inherited from dog class. And speak is inherited from small dog for tiny dog. So this is how inheritance works. It's like down the hierarchy. The children will get all the properties of the parents. Whatever the children has implementation details, it will not propagate back to the parent class. Okay, this is a simple implementation of class hierarchy. Let's have custom data types. Let's say I want to inherit from a parent class, which is actually a built-in class. So if you see Python, if you go into Python, if you do type of int, it is actually a class. If I say a equals 5, type of 5, it's actually a class int. So if I want to extend existing built-in types, let's go try list, a as a list. Type of a is the class called list. I can actually extend this list functionality within my own custom list function, custom list. Let's say I'll implement a unique list functionality. So I will extend from built-in data type called list. List itself is a class. I can extend from list. So if I want to implement something like a set unique list, I can declare it and I can inherit all the properties of a list by putting the list as the parent class for this. Now if I do unique list, let's print unique list. It's the same thing. So now I'm going to override the functionality to append the new elements. Let's say definition of append. So we have already seen that list objects have append function. A dot append of 3. And if I print A, it actually appends the item to it. If I do one more time append, it will add a duplicate. So now with the unique list, I'm going to eliminate this duplicate. This functionality is already available with sets data types, but I'm going to repeat that with extending the class. I'm just trying to re-implement the same set functionality with my own custom class. So let's do a define of append function item. If actually this has to accept self as a parameter. If self, okay. There is one concept we need to introduce here. Before actually initializing this, all the previous functionality of list also has to be initialized. So I'm going to override the constructor here. So it also should call the previous list's initializations. List, when I'm instantiating a list, it does recalculate some attributes and stores them in memory. So that functionality, if I have to get it inherited, and whenever I construct a unique list object, that also has to get called. So how do I call the parent class's constructor is like this. Super will give us the parent class's function, parent class, and then I can call the same constructor on the parent class like this. So when I'm constructing a unique list object, I also need to have the same functionality of the parent class, which is the list. So I need to do that through this way. If I don't override this, by default, the constructor comes from the list itself. This is perfectly okay not to extend or override the initialization. Let's do this way. We will override the constructor in a little bit more detailed fashion. For now, let's just override append functionality. It accepts a self as a default argument, and I need to add an item to it. So I need to check if the item is already existing in the current list or not. If item in self turn. Self actually refers to the current object. So what we have seen in the list is that this is a membership operator, and this membership operator works on the list. List is an iterable data type, so membership operators will work on the list objects. Self actually is the type, is of type list. Let's just try to do something like this. If I just print type of list or type of self, it is going to print list. So actually it's going to print unique list. Let's just call that function unique list dot append. I'm just going to pass one random thing, but it doesn't do anything. Let's write. So this actually printed the type of the self as unique list. So, but all the properties of a list will be propagated from the parent class. That's why I can actually use in membership operator. If item in self This means it checks if the item is already there in my list of objects. Return, just don't do anything. Don't add anything. Otherwise, super dot append item. So if it is there, don't add it. If it is not there, call the super. Super means the parent class lists append method with the same argument. But if the item was there, add it. If not, do the default functionality that the parent class gives. So now if I do here, it's printed. If I add one more time, the same thing. More. Let's see. Better. Okay. Now if I execute this, and it only gives the unique values. When I appended one more key, it did not add it to the list, but only return from it. So this is one way to override construct. Now let's override an extra parameter. Let's say add some extra argument or attribute to this particular instance. So how do I do that? Is through overriding its constructor. Something like a message. I'm going to add some simple message to it. Self dot. So when I'm overriding the constructor of a default data type, I need the data types functionality also. So same thing has to be called from the initialization. Otherwise, we will miss on the functionality or initializations that happen by default by the built-in data types. So this is how we call superclasses constructor. Now let's say with this message, I'm going to have another property and then list self dot message. If I do the same thing, let's print start message. Actually, we should pass a message to this. So if I'm overriding this, the message also needs to be passed. Message some custom message. Okay, now it's printed. We have extended the functionality of list, and we have made it as unique, and then also added a extra attribute that the list doesn't do by default. This is how we override built-in data types also. So let's see another example of parent and child classes. So let's say I will have a class called shapes, or file called shapes. So I'll create a class called shape, which does have some property called width. I'll initialize to 5, height 5, print character. So it's just a character that I use to print on the console. And I'll show you where I use it. So let's say I have one function print for self comma I, which means it prints items. Let's do a pass here. Later we will implement that. So if I want to print this shape, Let's just do I right. Okay. So I'll implement this and then explore how this works. So this one, let's just print something. This actually prints a particular line. If I'm drawing a square or a triangle, it prints one line on the console. So this functionality has to be implemented by, let's say I have a class called square that extends shape. The print row functionality has to be implemented by this guy, this particular class, subclass. Similarly, if I'm implementing a class called triangle, that also extends from shape, has width and height, and it has to extend the functionality for print row. The common thing here is every shape should implement its own print functionality, print row functionality. So it can share all the print functionality can be shared across all shapes. For each row, it's going to call print row function. So this print row method is not implemented in shape class. So if somebody tries to call this shapes print row, we need to raise something called an exception. I'll go and get into exceptions in a bit. Not implemented. Thank you. Implement code. It's not class, but so if I try to access print row functionality, let's try to instantiate an object called shape. By default, the width and height will be set to 5. Let's then try. That's it's called shape. Close measure. Shapes. Because it will be implemented in the child class. Because this is not implemented, and we are raising this particular method whenever somebody tries to call it on the base class or the parent class. So now let's implement the same functionality in the print row, how to print the row in a square. So for each of the rows, let's say height is 5 square foot or 5 inches. For each inch, it has to print one line. Let's do that. So the functionality of printing, calling the print row functionality is already here. We just need to override this. So I will just print self dot print character into which one is sorry, not to be self dot width. So square means it's even. So remember, if I do remember, it will create a square triangle. Let's do this. Create an object called square. Square dot then. Let's try printing that. So it has created a square. I can then 5 characters on 5 rows down. So this actually is like a rectangle, but it's considered as 5 into 5. That is what it has printed. For each line, it's printed 5 characters. So let's implement the same thing in triangle. How do we print a triangle here? is for every row and character into 9 plus 1. Will it give us for the first row 0 actually means, so it starts from 0, right? Every time. So first row should have one character printed, second row should have 2 characters, and so on. Let's try doing that. Let's triangle. So first thing we printed a square, and then second time we printed a triangle. So what if I found to print this triangle not as a right angle triangle and a symmetric one? Let's say like this. Like this. Let's do that. Symmetric triangle. Let's implement a new triangle class. Symmetric. That extends from triangle. Print row, I'm going to override the print row. I'm just going to override height and width also. Because height is fine. And width should be 2 because so if I have to leave spaces, if the width is 5, if it is 1, and the first 2 spaces and right 2 spaces I should leave and put only here. So the character only here. The total width will become 2 times the length of it, 2 times the height of it. Sorry. Width it becomes 2 times the height. So for this, print for each row, we have to calculate triangle width. It will be 2 times the row. First row means I have to leave 2 spaces in the front and 2 spaces in the back. That's why it will become the number 2 plus 4. Because I starts from 0, that's why we need to add. Adding, I need to count width of it. Whole thing. And this will give us the height, which is the front, how many we should leave, behind how many we should leave. Characters to the right as well. I'll explain the logic of printing. So now I have to first print the spaces into the padding length, and then print the character of the triangle. Symmetric. And let's try printing this. Okay. Now, the first row has actually occupied this much, which means 1, 2, 3, 4, 5, 6, 7, 9. This many characters, 9, and there is 1 actually left on the right. Just 1 space is left on the right. This is actually 10 characters in here. The first row and the last row prints nine characters. The next one, 7, and then 5, and then 3, and then 1. So this is like this pattern and how to print these characters. This calculation we have done based on the total length of characters and then what is the padding we found out. And in the middle, we have to print the character that we had. I have to print 3. So I need to leave behind 3 characters and then 3 characters for that in order to align. That's what this calculation is all about. It's just a simple example. This calculation need not be learn on your own based on what type of formatting we can actually print face or something. There are libraries that allow us to print these type of patterns. We'll go into that in some time. So it's about just to demonstrate the extendability of the functionality of whichever class. Next concept, we have to look into something called exceptions. Let's say I divide by 0, something like 1 by 0. Let's try telling that. And Python is giving an error called zero division error. So we can't actually compute 1 divided by 0 because 1 divided by 0 is an infinite number. And computers cannot calculate these large numbers. I mean, infinite numbers, it cannot. So it throws an error whenever we try to do invalid calculations. So in our code, if we have to handle this kind of errors, let's see how this works. I'm defining a function that does this, and when I did plainly in one line, and it gave me this error. Let's call this function. There is something called stack trace in Python. I want to demonstrate that. So this has given 2 lines here. So earlier it gave me one instance where it failed. And here trace back it has given me. So we are called 1 divided by 0 on so on. And that is actually called from this function on so on. So this is called the stack trace of an error. Let's add one more. So as we add more elements to it, the stack trace increases. On it, we should call one cause errors. If I have methods calling functions calling another function and another function calling another function, and wherever the issue happened, it will print the entire stack trace of which method called which method and where exactly the error occurred. So if we have to gracefully handle these errors, we need to put these in try catch blocks. So there is something called let's remove this. I'm just going to remove this also. There's something called try and then do something where. There's something called catch. So every try has to have its own catch. So you cannot catch except. And let's just try 1 divided by 0 here. If I do it this way, let's Division by 0. So actually the error has been raised. If I don't handle this, it prints it like this. This is kind of a crashing of the script. Yeah, entire execution halts, and then you won't have any way to resume the program. So if I gracefully handle it in exceptions like this, I can actually have some code written here or some code here. Let's say I'll just print here. And just as soon as this gets executed, this the entire program after this will not get executed. If I run it now, our statement did not get executed. We'll just comment out this part. Even though we are having the problem here, we are actually handling this in the except block and gracefully continuing the program. Let's do that now. Here. So division by 0, it has printed the error and it continued execution. In our server programs, every time we encounter an issue, it should not crash the server, it should continue execution and continue with the other requests. So that is where our try except blocks help. So if I just try to see what's the type of this exception, it's printed. This is actually a 0 division error. Let's say now as I'm using the exception class here, what is the exception we are unable to get? If I don't need that information, I can actually eliminate this part as E. I can remove just trying to print some error. If I'm not interested in what the error is, I can actually remove that E. And there is one way to handle specific type of errors. So we have this is exception is the parent class of all exceptions. So there is a specific type called 0 division error that is being thrown when we are executing this statement. So I can actually handle that error here. And in the order that they are handled is important. Fourth, 0 division error. And if I do execute this block got executed because it's matching the error that we are getting. So if I do this changing the order, if I change the order, so order actually matters. If a generic exception is handled first, only always this matches this exception. Because 0 division error is a subclass of exception, and if except block has a generic type in the first, it always goes into that block and everything else will get ignored. So while handling exceptions, you should always handle the more specific one first and then the more generalized one in the end. So let's say if I have some other exception introduced, I'm trying to add 1 and 8, which is a type error. Let's try executing this. So let's remove this one layer by 0. Some error occurred. I don't know which error. Let's try getting the error type. I'll just print that's the error type. This is the message that we got. Actually, I'm interested in the type of this error. This is called the type error. So if I now handle accept type error, then type error. This gets matched first before this type error. So different types of exceptions can be handled like this. The exceptions are a way to gracefully handle program execution if some error happens. And there is actually one better way to do this. Let's put this in a function. Let's say cause error. Let's just put this in a function and call this cause error from let's just I'll put it in separate block. Just comment out this tag so that it's useful as a reference. I'm going to implement this function cause error that does from A and cause error. So we have also seen decorators. We just had an introduction to decorators, but we haven't seen how the decorators are implemented. If I have to handle this entire thing in every function that I implement, that becomes more and more difficult. So that's why we are going to use decorators, implement our own decorator and use decorator. We have seen decorators something like this handle exception. And this decorator has not been implemented yet. So we're going to implement this handle exceptions decorator now. So for this, I'm going to implement a function called handle exceptions that accepts a function parameter and then implement a wrapper function here. Wrapper try function in this entire block of exception handling. I'm going to put inside here. What this is going to do is, so at the end, I'm going to return the wrapper function. So this is actually a decorator, a function that calls another function that accepts a function as an argument, as we have seen earlier. Functions also can be stored into variables. Say handle exception. Also, this also can be used. This way also we can A now refers to handle function exceptions. Function. That's how we are actually, whenever we are declaring handle exceptions, this entire function is getting passed as an argument to this decorator. Whenever we are declaring this decorator, that means we're actually passing this entire function as an argument to this decorator function. So what I have done, I have declared another wrapper function inside it that calls this particular function and handles it. And the wrapper function I'm returning from the decorator function. So this is how we implement a decorator. Let's try running this code. Now I'm calling cause error, which is wrapped under a decorator. By default, it handles all the exceptions that we have discussed so far. Let's try exceptions. Type error because we haven't done any handling of exceptions in this particular function, but we have handled it inside this decorator. What if I have arguments here? Cause error. Fine. Let's say I will implement a function that only accepts integers. So I have an character. this if n character is n argument is a letter, let's just use n here. Cause error of a if I do it. Multiple times I will use it. One time I'll use an integer, one time I'll use a float. And so on. So whenever exception occurs, this has to get executed, just decorate it. But we're not actually passing any argument. Let's try and run this as it is. And cause error, handle exception takes 0 position occurrence, but 1 was given. But basically, this is not accepting any arguments. We have to accept arguments in order to make it work for all the functions which have any number of arguments. So for that, I'm going to use arms here. Same thing I'm going to use here. Pass this functions. So now, when I'm wrapping this function inside a decorator, all the arguments that I'm passing is going to get passed to this as args parameter. Let's try running that. And this works. Type third. Set type error. Let's just comment on these last words. It's passing actually a list. So we should unwrap the list with star box, which will unwrap all the list of items. How it works. Let's try with A. Let's print actually the result. So when I passed 1, it printed. So it has handled the exception or I'm passing 1. So it did not halt the program. It did execute, gracefully handled all these. So 2 is returning to because always the non-zero number is always going to result in 2. And 2 actually the value of 2 is wrapped as 1. So if I can show you, and if I wrap this integer, it returns 1. 2 is considered as value 1 when I'm having 1 plus 2 plus because 2 choose value will be 1. So that's about handling exceptions and decorators to use functionality. And similar to this, I can actually have custom exceptions. Let me implement a new class called custom exception. This has to extend from default exception class, which is provided by. But just cause define a class called cause error. Inside here, I'm going to phrase the exception called custom exception. Let's call it cause error. Let's see what this is. Okay, it has printed custom exception and with the factors, that's fine. But it doesn't give me any information what the error is all about. So if I have to print something here, I need to pass some message in the exception. This is custom. Let's execute that. Yeah. and custom exception. Now it's giving that message for the task. Let's implement something similar in a more detailed fashion. Let's say I have a HTTP exception whenever a web server is having difficulty or having issues. It's going to throw an error that is a subclass of HTTP exception. So by default, gives a inherits from exception. I will have one property or attribute inside this status code minus and initialize to have message ID as this is a variable class. Let's initialize this with a constructor that calls parent class is constructed, all the functionality I need. Whenever keep in note that whenever we are extending a default base implementation of any built-in types, we need to call the superclasses constructor whenever we are overriding the constructor. If you're not overriding this, by default, whenever you instantiate this object, it automatically calls previous superclasses constructor. If you are overriding it, it won't. So when we are overriding it, if we want to have the parent class's functionality, we have to call the parent class in the constructor like this. And the same thing, this accepts string as a message. Self.status code status code in this message. It is message. Now we have overridden the constructor. Let's extend this functionality with 404 not found error. Not found error, but some page is accessed and we don't have that page in the website. We can I'm going to extend HTTP exception as a parent class. And I'm going to use status code as 404. That's the status code for HTTP not found. The message is the source not found. Now, on this one, we don't need to extend constructor. By default, it's inherited from the parent class HTTP exception. Let's say another error, server error. That extends the same HTTP exception. So usually status code will find for internal server errors a message I can put in server. Let's create a function, trace server error. Trace server error. We don't need to override anything message or anything. I can just trace server error like this. External custom exceptions. Status code. This one. Yeah, this has thrown an error. Exception called server error. Status code it's printed from this because we are initialized it and extended it from exception class. That's how we extend classes. And next topic we have to discuss about is multi-threading and multi-processing. So far we have been executing these code one by one. So if I have to, let's say, just add one. I have, let's say, I will create a definition of function long square. Yeah. That returns n square. But when calculating this, I'm going to sleep for 2 seconds. Time was at 2 seconds. This is just to simulate a long process. What we time margin from default library. Let's say I will execute a list current. Long square of n, but n in range 0, 10. This actually prints all squares of 0 till 10. Each of them will take like 2 seconds. Let's try running this. Start waiting like this. Let's just print. So, first, calculator. Every 2 seconds, it calculates 1 line for 0. 1. So, okay, this is a simulation of the functionality of a long process. Let's say some function executes does so many calculations, and we want that function executed every time. For every large number of times if we have to call that. So waiting for that is not a good idea. So far we have been executing or calculating these things one at a time. So what if we want to accelerate this process? And the processor is much more powerful than one single calculation. It can do multiple calculations at once. So this really can just make use of this powerful CPU. We can have multiple threads running. Each thread actually means it's a parallelization mechanism for us to execute multiple calculations at once. So if this long square process or a function needs to be executed multiple times for multiple different values, we can make use of multi-threading. So we can parallelly trigger this function calculation for multiple values at once. So in this particular case, we are actually calling this function for every value and in sequential order. We're not parallelly triggering the calculation mechanism and then collecting the things. No. We're actually calling this every time. Once the first 0 value is calculated, square of 0 is calculated, we are again calling for 1 and then for 2 and then for 3. So the use case of multi-threading, we can call this function for 1, 2, 3, all in parallel. Let's see that tomorrow. Multi-threading, if we discuss now, it will be too much confusing. Let's see how this multi-threading works. Till now, we have seen basic data types, complex data types, and we had a brief introduction to classes as well. So far we have been using Python shell here. So from this class onwards, we are going to use the text editor. As our programs get more and more complex, we can't do everything in the shell directly. We'll have to repeat the code so many times. So it's better to switch to the text editor. Let me create a new file. So let's where we left off, we have actually created a class called dog, and we created okay, let's say we have a class dog. So today we are going to look at how to do extension of this class inheritance and object-oriented programming a little bit. We'll dig into deep into the decorators, how the decorators are made, and what is a decorator and everything. So let's say I'll just briefly review what's already happened, revisit what's already discussed so that it's more clear. So a class is a template for an object. So class can have instance variables as well as class variables. Let's say a dog may have 4 legs. All dogs will have 4 legs. All the common properties we will put under the class, and any instance attributes. These are like, this is class variable, and there is something called instance variable, which we will declare inside a constructor. So what is a constructor? Whenever I'm creating an object like this, so this call actually is going to call a function inside this class. Basically, inside classes, the definition of a function is called a method. So let's say init is a default method, which is a constructor. So basically what this init does is it's going to create a new object of type dog. So when I'm defining this constructor, so it accepts self as a default parameter. Self actually refers to the current instance of the object. Let's say this dog object, when I'm creating, whenever I'm referring self, that actually means this dog object. Let's say I have another dog, dog 2, so this is another instance. When I'm accessing self, that actually in this particular instance is going to be dog 2. So let's say I need a name for a specific dog. Let's say all dogs will have 4 legs, and each dog will have its own name. So that will be accepted as an argument for this constructor. And how do I define an instance level variable or instance level attribute? Is like this: self.name equals name. This actually is going to define an instance variable or an instance attribute called name, and assigns the value that we pass in the name in name. So this name has to be passed from here. Let's say this is something called class. The name of this card is X. Let's say I would name something for this. This one has this. So this accepts name as an argument. So this card, let's just try printing dot name. Let's print dot name. Use both to differ. So let's say, how do I call this script? That is while in Python, and the name of the script, animal start. So when I call this declaration is being instantiated by this dog X looks like in this. So let's say I run another attribute or another method. Let's define another method called speak. Every instance method will accept self parameter as the first argument. Here I'm going to define an F string. So if we had already seen F strings, I'll just briefly review what F string is. F string allows us to format text. So inside the F string starts with F and then double quotes or single quotes. Within this, I can use any Python expression. Self dot name says. So now let's call the self dot speak. function. So inside classes, we call functions as methods. So talk.speak is a method. Talk.speak. Let's run this now. X is bound. This is bound. After that, we have a basic class equation. Let's print how many legs dot2.name, dot1.name will print its own names. Instance variable. It's going to access the instance variable, whereas legs is a class variable. Let's begin dot legs. So dot legs. So when I'm accessing dot it's accessing class variable, whereas dot.name it's accessing the instance variable. So similarly, I'm calling a function or a method in classes, we call this as methods. So talk.speak actually uses its own instance name, instance attribute called name, and talk.speak also uses its own instance variable called name. So that's why using use this bar, that's this bar. Even if we add name attribute common name, it doesn't access this name. Actually access this name because we are referring them with self. Let's try to run this. So if I have to do something like dog, let's access dog, name as printed common name. Let's just say we don't do this and then just pass. Pass means do not. So when I'm accessing self.name, and if I don't have an instance variable called name, it's going to use this name. That's printed. So even dog1 has the same name, dog2 has the same name, because we have commented this out. There is no instance variable called name. So it's going to use the class variable itself. If I have instance variable with the same name, it will use that name instead. So in general, we declare the class variables which do not usually change. And for instance variables, we put those things that change based on the object. Similar type of objects will have different names. Common properties, they will put in a class attribute like this. So next thing we are going to discuss about inheritance. Now we have seen one small implementation of an object-oriented program. Let's define another class called small dog, which extends dog. So all the functionality of a dog exists for this small dog also, except that it cannot bark. So this part will go back. Let's just create an instance of I'll comment like this part. Small dog puts small dog, and I have to pass name to it. And so let's call it small dog dot. We haven't defined any functions, any methods or attributes here. All the things are getting inherited from parent dog class. From this file, where says even though we haven't done any code here, it's actually using this code from the parent class. Now let's say this is a small dog and I don't want to start the dog. And the implementation detail, we can do override this specific function in this small dog class. Let's define a function. Method spook, and every instance method ends itself as a default first argument. And I'm going to use string self dot main source. And now let's execute this. What we'll say is I can import. So any functionality that we want to override, we can extend that on the subclass. If you want to use existing functionality, I can use this. Let's just say we need another extra functionality. Right. Okay. And it's not dot name. Let's run this. So it says it's not back. And let's call that sheet. That's on the top, and that is not. So this method is implemented only in the subclass, and this is called the subclass of dog. This can be called as a child class or a subclass, and dog can be called as a parent class or superclass. Superclass or parent class are common language, and subclass or child class are common language. So if I do the same thing with the dog object, then we get that dog object, dog that's speak, dog. And this is a subclass or child class. Dog is a superclass or parent class. So what we have done here, we have declared two class attributes, legs and name. This is the common name. We don't need this. Let's drop this part. So all the dogs will have 4 legs. That's a common prompt. That's why we have defined it inside dog class itself as a class attribute, not as an instance attribute. So the instance attributes or instance variables, analogous, both are analogous. Instance variables or instance attributes belong only to the instance of this object, this class. So that's why we use self here. So this will vary based on the object. Each object will have its own instance attributes, whereas all objects will have same class attributes. So all classes, all dog objects will have the same number of legs, and each dog will have its own set of name, age, and everything. So this is about instance variables and class variables. So whereas here we have inherited all the things, all the properties, all the attributes, all the methods from the dog class, which is called the super class. Then I'm declaring like this. The super class will go inside the parenthesis. And small dog is an extension of the previous class, which is dog. It's also a dog, but it is a small one. And it has a set of custom functionality or custom features. It cannot bark and it can wag tail. So these two functionalities we added this small dog. So when I instantiated, this is called instantiation. So meaning it's creating a new object of type small dog. So I can call speak functionality or speak method in it, which does execute this code. When I call this method, wagtail method, it executes this code. So if I do the same thing on a superclass called dog, the same thing I'm doing, speak and wagtail. Let's run this code and see if that works. Dog dot wagtail, wagtail. Dog object has no attribute wagtail because we declared this method only in the small dog class, not in the dog class. So the inheritance works only in one way. So let's say here, small dog is inheriting from dog. It's not the other way around. If I declare something here, it does not propagate back to the superclass. All the things, all the properties, everything, methods, attributes from the superclass will be available in the subclass called small dog. But what we define here in the subclass will not propagate back to the superclass. That's the difference. Inheritance works only in one direction. If somebody earns money and gives it to their children, it belongs to the children. When the child or the son of any children earn money, it doesn't go back to their parents. That's how inheritance in objects in our day-to-day life also is similar to that. So the wagtail function or method is not going to propagate to dog class. If I use dog class value, for instance, and call wagtail, it doesn't work. So this cannot be called. Whereas a small dog, it works because it's part of the small dog class implementations. So these two are other custom classes. Similarly, we can actually extend existing built-in classes. We have seen earlier by going into the Python shell. And if I type of 4, it is integer and it is actually a class. You see here, this is a class. This is a built-in class in Python. You can actually extend these classes and use them. Similarly, if I do type of 1, 2, 3, 4, this is a type list type of list. List is also a class. So I'm going to extend the list class and implement a custom implementation for the list class for a unique list. So unique list of functionalities is given by the data type set. Sets also do the same thing, but I want to implement it with the list class so that you can understand better to override the functionalities or to override built-in classes also. So this time I'm going to use a class called unique list. This is not existing the built-in types, and I'm going to extend the built-in data type called list. So list is again a class. List is also a class. Here I'm going to do class. Means nothing, no implementation at all. All the things, all the properties, attributes, methods, everything gets inherited from list class. Let's try unique list at once. List. Unique list dot append of G. Then print in list. As of now, I haven't done any modifications to the implementation. It's just want to use a totally typed class gives. Let's try executing this code. And let's okay. This from I think you can write this another fact. Yes. Back to the fact. Remove this entire code. And yes, that's exclude this part again. Okay, it has added 3, 4, 5, 8. So I don't want these two duplicates to be added. So if I add 3, 4, again 4, it should not add 8. Let's do that. No. So doing this, let's modify this code called append function. We're actually calling append method of the superclass list. So in this class, I'm going to override this. So by default, any method, instance method accepts the cell that should not forget. This time, whenever I'm passing a value here, it's going to come as an argument. So I can put any value, any variable in here. This actually comes as an argument. Apart from self, whatever they pass here will come as arguments. So this item I'm going to use to see if this item exists in the current list item. If item in self. So if you see here, self actually refers to current instance of this list or unique list. So as list is an iterable object, we can use membership operator called in to check whether a particular item exists in the list or not. As we are inheriting from list, all the functionality, all the properties will be inherited by unique list also. So we can do the same in membership operator on the current object, which is self. So this works. If item in self, then don't do anything. Don't add a new item. Otherwise, you have to add the new item to the data structure or into the memory. So that adding the fresh item into the memory or into the list object is all taken care of by the list class. We don't have to re-implement that logic here. We can just call the list functionality to add this new item to the memory. So how do I call the append method of list? Yeah. For that, I need to use a keyword called super. So when I'm accessing super, this actually refers to the same functionality that is implemented in this super object, super class. This is a subclass. This is a superclass. Analogous to this is child and this is parent. Super actually is going to refer to the superclass, which is list, and then I'm going to add the function append item. What this does is it first gets the object reference of superclass and then calls the method append and passes the item to it. Just like this method, list also has the append method. It's just we are trying to override the items, the list's append method. So now we just checked if the item is there. If it is there, don't do anything. If it is not there, when I do return, it doesn't continue executing into the next lines. From here, the control actually goes back to here. So return means don't go any further, just return from here. So when I'm finding this element in the list, I'm just returning it. Don't return, don't add, we're not adding anything. If it is not one, this by default actually means else. Don't have to write an else condition here, else statement here, because this control actually will not execute if I'm returning from here. This is unnecessary. I don't need this else. I can just use it like this. So what we did here, we call the superclasses append method with the same argument. So this is just a intermediary that we are checking and adding in. Let's try running this code. Now we have eliminated the duplicates. So in the previous case, we did add duplicates because we are not doing this checks. And list allows us to add duplicates. And in this unique list, we are not allowing duplicates by checking this. If the element exists already, then add it. And so we just extended the append functionality. What if I want some more properties of this unique list? Let's say I want to have name for this list. So list does not allow us to store any name to it here. So for that, I need to extend the constructor to have instance attributes. So let's just extend the constructor or override the constructor. Constructor also accepts the first parameter as self. And I want to give a name to this list. And I need to pass that name in the constructor as an argument. Name. That name I'm going to use here as an instance variable for unique class. This name I can print as I will have another method self name. This method does not exist in the list class. It exists only in our unique list class, which is a subclass of list. All the functionality from list we are extending or inheriting. We are inheriting all the functionality from list, and we are extending the functionality or overriding append functionality and adding new functionality to print the name and have a name to the list. Let's now print make list and then print before this. I'll just print start print name. I'm going to call this method and then print the list. So while constructing the object, it expects the name also. This I'm going to do that as my this run this code. My unique list. So this is one coming from. Okay, this is actually printing, and we are not returning the. We don't even need to just put print instead of print. What happened earlier? I'll just show. Print of like the start print name. This is actually printing the value, and the return value of print name is none. By default, it actually returns none. This means even though this line is not there, it actually means it's returning none. And as it returns none, that value is getting printed by this print statement. That's why we are seeing this none. I'll just remove this print statement and just call print name after now execute my unique list. is this. This is how we extend the built-in classes. You can do the same thing with dictionaries or any other data type. So to demonstrate even further in inheritance mechanism, let's take another example. Let's say I have shape stuff, right? I have a class called shape, and shape has two attributes. Right? Let's say initialize of 5, right? It's 5. Let's print, define a function called print, which accepts self as the first argument. And what I want to do here is for every line, for every width, for every height, meaning let's say 5 square feet by 5 square feet, I want to print a specific character in the terminal. Let's say 5 rows and 5 columns. I want to print a star 5 times on one row, and I want to print 5 rows with 5 stars. That becomes a square. And for triangle, so first line will have 1 star, second line will have 2 stars, third line will have 3 stars. That becomes a triangle. If I print and show you, that will be evident. So we'll just assume that. But now let's implement it, and then we will revisit this. But if I want to print a shape, what I have to do is the height of the shape is, let's say, height 5. For each line, till the height becomes height, I want to print a character, print row of height. Self, I haven't implemented this method yet. So for each unit in height, I want to print one line. Let's say height is 5. I want to print 5 lines. 5 lines with stars. How to print the stars is handled by print row. Let's implement that also. Print row. This also accepts self as the first argument, and row number as I accepts. And then I have to print a row based on the shape of the object. So now I can't do this here because I don't know the shape of the object. If I have to print a square, I should do the all how many stars I need to print is evident. The same number of stars as the width. So height we know. For square or for triangle, the height we know. The width of the characters can know. That will be part of the child class. So let's say this, I'll raise an exception. If somebody calls this exceptions, I will discuss in a bit. So for now, this is not implemented. Not implemented exception on the so if somebody calls this method on the base class call shape, not implemented error. This implemented solid class. This is the base class. We have attributes, one common method which will get called for printing. In print row, how to print based on shape of the object, how to print will be decided in the subclass. So let's define another subclass called square that extends shape. So this class only implements print row. Everything else will come from the shape object itself. Print row, how to define yes, self and I. Which row I want to print? For each row I want to print a character. Let's say it is star character. I want to correct and I'll just use hash. How many times I want to print is self width. Based on the width, I want to print this. Let's say this hash character also we will just move it to the parent class. And add as a print character as hash. And I'm going to use that itself here. So that print character to self output. That means it's going to print hash symbol 5 times if the width is 5. For each row, if it prints 5 times, second row 5 times, third row 5 times, fourth row 5 times, fifth row 5 times, that will become 5 by 5 matrix, which is like a square. So that's all about this shape. Let's just execute and see this square. This square. Square. Run this flow like that. Shape stack v1. It's painting 5 by 5. Although it looks like a rectangle, but it's actually a square. 5 rows and 5 columns. 5 rows and 5 columns. Let's implement one more class called triangle similarly. And it also extends shape. So same thing, I'm going to override print 4, but this time it's going to print first line 1 character, second line 2 characters, third line 3 characters, and so on. So based on line number, so right. So that character into I plus 1 because I starts from 0. Here, if you see here, the range function 5 look range 100 5 to I'll just convert this into a list. It starts from 0 till 99. So when I'm referring to the height, it's actually starting from 0, line number 0 to line number 4, as the height is 5. So that's why I need to do a plus 1 here. How many times? First row, which is 0th index, you should have 1 character. So do the same thing with this triangle. Triangle. Then shapes back. This got it. It's coming to this once. So confusing. It's cute. It's not going to be a right angle triangle. So this is not a triangle. Let's do one more example. Instead of right angle triangle, I want a symmetric triangle. So this one is 1. And second row will become 3, left side 1, right side 1, middle 1, 3, 5, 7, 9. So let's write that code for a symmetric triangle. This also extends from shape. Print row. This has self as the first argument and line number as the second argument. That line number starts from 0. I start from 0. So I'm just going to pass. So for symmetric triangle, the height has to be same. 5 is 5. So if I have to print a symmetric triangle, it comes from this way and right side this way. So the bottom line will have 10 items or 9 items. So we need double the size of the height. So that's why I'm going to override the properties in the class itself. So width we have, height we have 5. That is coming, no problem. Width is going to change as we are going to scale from here to here and here to here. The width of the bottom one will be changing and each row's width also will change. So if I take the matrix of 10 by 10, then I can fit the track. Let's solve it. So I'm just going to initialize this with 2 times 5, which is the height, 2 times the height. Okay. So for each row, I'm going to find out the width that it occupies, a specific row, how much it occupies. I'm going to initialize a variable called row width. Row width is going to be first line, it will be 1, 2, 3. Or with character. That's character. So first line is going to have one item. That's fine. Second row will have 3 items, 3 hash symbols. Third row will have 5 hash symbols. Fourth row will have 7. Fifth row will have 9. And so on. This is actually an odd number, right? We are increasing by 2. So for generating the odd numbers, I'm going to use the number into 2 plus 1. So when I is 0, it will be 1. When I is 1, it will be 3. When I is 2, it will be 5. When I is 7, I is 4, 3, it will be 7. When I is 4, it will be 9. So that way, character width will be calculated correct. So first row will have 1, second row will have 2 and so on. So for printing this character like this, there should be a padding before the print. Hash symbol should be printed in the middle of the triangle. First row, as we are going to share from here to here and here to here. So I need to find the padding. How many offset I need to add? Padding, I'm going to use self dot width. So because its overall total is 10 by 10 matrix, width divided by half. If I do this, it will fit for 1 character. If I am fitting 3 characters in the second line, that's going to that's not going to be correct. So for that, I have to actually reduce the width by how many characters we are printing. Character width. This entire thing has to be divided by 2. So when I calculate total number of characters by characters it will allow divided by 2, the left side that much I should leave and the right side that much I should leave. So that is 1 divided by 2. So I'm going to convert this entire thing into an integer because by default, if I do divided by, it will generate a floating point number. So now I will do the print statement. So the padding, I should give spaces. How much padding I need to give is this. I will print this many number of spaces. And then I will print the character. Print characters. So print characters. And how many times I need to print this character. The first row, I need to print 1 character. Second row, I need to print 3 characters. The offset will be the total width minus the number of characters I need to print divided by 2 because that is the number of characters I need to shift from the left. When I run this code, now I'm going to visualize metric from the let's run this code. Now it's printing a symmetric triangle. If you see here, this is almost 10 characters, 9 characters, 1 letter back. So this is a symmetric triangle. This is how we take this calculation. Any doubts so far? So next thing we have to discuss is the exceptions. Let's try doing this 1 divided by 0. Python exceptions, and it will through an error, 0 division error. So by default, this is mathematically impossible. 1 divided by 0 will be infinity, and computer does not allow these operations to be done in the CPU. So that's why we return an error, divided by 0 error. This is a common error. So this gives us the stack trace. This is called the stack trace. How or when this is called and from where this is called. It says that exception stack provide line number 1. We have called this, and this caused a 0 division error, division by 0. The explanation of that error is given. Interpreter is given. So what if I have this inside a function as error? This line error as error from input. When I execute, there is 2 stack traces. On one stack trace, 2 lines. So we have called cause error on line 4, and it resulted in 1 divided by 0. So division error. Earlier we had only this error. And if I have another called cause error, another redirection, instead of this, let's call times error again. There'll be 3 stack traces, 3 lines. So what's the stack trace? Like from which code are we calling this particular error? So how will this error happen? And from where the code is getting called? This is the system stack trace. So that's about exceptions, by default exceptions in Python. So when this happens, when any exception happens, the program halts. Halt means wherever it was executing, it will stop executing there itself. Doesn't continue. So there is a way to gracefully handle these errors. If any error happens, a program will crash, and the server, let's say, if a server got into some kind of issue, it won't recover. It will crash the server and it will shut down the process. That is not what we need to do. We need to gracefully handle these errors. If any unknown errors happen, how do we gracefully proceed with the code so that it doesn't fall down? So for handling that kind of error scenarios, we use a special statement called try and except. Some error happened. If I call it this way, this doesn't work. Program doesn't crash. The exception occurs, and the problem will be this statement will be printed, and program still executes. Let's try again. Before implementing this, let's just remove this code internally. This is after exception. So when this exception happens, and this line does not get executed because it comes out of the program logic. So that statement doesn't get printed. So what if I have tried and except block here, exception. So when it will happen, and this statement also gets executed after handling. So because some error happened in this call and this statement got printed, and program continued execution with the next statements. This is how we gracefully handle these errors. Suppose we have this exception. What if I want to execute some code whether or not exception happened or not? So with that code, I will put in a finally block. This code always looks so when an exception happens, the statement gets executed. If there is no exception, this statement doesn't get executed. Whether there is an exception or not, this statement is always going to get executed. Let's try to do that. So exception happened, and this statement got executed, and this also got executed. This code always gets executed. Let's just do something like 1 divided by 1. Now 1 divided by 1 will not cause any error. Let's run it. And it did not cause any error, so this statement did not get executed. And this statement got executed because it is finally blocked. No matter what, no matter whether exception happened or not, this will always should get executed. And then the program continued. So that is one. Now I have, let's say, if I want to know what type of error I'm getting, I can just say exception as free. This can be emulated or any variable. I just catching the exception in this variable. And I want to print the type of exception. The type. It type here. This actually going to print this exception 0. So some error happened, the class of 0 division error. So I can handle specific. This is a generic exception handler. So I can handle specific type of errors. Let's say I have this one. Yes, this is another type of exception. Let's try executing. This is a type error. So this code can get into any type of issue. Let's just say n. So this, let's add this code as 1 divided by n and 1 plus. Let's write this code above this n. 1 plus n 1 divided by n. So this n can be anything. We cannot trust who is calling this function, and n can be 0 or n can be a character or anything. So I need to handle type errors, which happens when n is a character. I need to handle 0 division error when this happens when n is 0. So let's handle those specifically. So any specific exceptions we need to write before this generic exception. Let's write except 0 division error. and 0 should never happened. Similarly, write another block that handles type error. Type error. Okay. If none of these things match, the last one, exception generic handler, will get triggered, and always the final block gets executed. Now I'm going to call this cause error with, let's say, 0. Pseudo division error happened. Okay, I'm going to now call it B. Type error. So this is how we have different types of errors in runtime. So now, so every time if we have to handle these type of errors for every function call, that becomes a tedious job. And there is an easy way to implement a common functionality that we can wrap this entire thing into one decorator. So decorator is a special function. The decorators are used like this. Handle exceptions. This is a decorator here. So a decorator starts with @ symbol and the name of it. So this decorator is not yet defined. This is a custom decorator that we are going to implement. So how do I implement this decorator? It's like this. Def. This is another function itself. This accepts a function argument function and has another function inside it defined, something called wrapper. This can be any name. For now, I'm just going to do a class here and then return wrapper. This is all we have to do about a function wrapper. So decorator. So inside this wrapper, we are actually going to call this function. This is all we need to do to handle exceptions. Let's we'll implement that. This is all we need to do for declaring a decorator. So this is throwing an error because as Python is a step-by-step procedural language, we should actually define this above this line. So till this is defined, this code cannot access this particular code. So now as I move this decorator outside or above this line of code, so now the error is gone. Okay. Now this entire functionality of exception handling, I'm going to move this thing inside the handle like this. So I accept what I'm going to use this entire thing from here to here. Let's do this. I'm going to use that here. Now when I call this cause error, I'm just going to use cause error directly. Stuff here, I'm going to move this to cause error. I'm just doing this one. So let's move the around. Now I'm going to call directly this cause error. Okay, we have this administrative exceptions. We call cause error. Now, if I do this, I will get by default. All that exception handling will be handled by this guy. When I'm handling exceptions inside the decorator, I can call it, and all the exception handling code is inside the decorator. And I don't have to repeat for every function. Any function that needs to handle all these exceptions can be wrapped under this decorator under exceptions. Okay, that's one thing. So now let's say I'm going to call cause error directly instead of calling this. I'm going to use handle exceptions here also. But cause error actually accepts an argument, and we are calling that function without an argument. There is found cause error exception. Showing an error. Let's execute on second. So cause error invalid syntax. One sec. Cause error. Okay, so the cause error is not defined. We are actually calling the function, not the definition. So let's move this cause error also up below. And same thing I'm going to use exceptions on the cause error tab instead of this. Now I'm calling cause error with view as an object. Let's try it on this. Handle exceptions takes 0 position arguments, but 1 was given. This is because we are passing u as an argument and as an argument to cause error. So when in this annotation or the decorator, we are passing a function and we are not passing an argument here. So we should actually pass the arguments also. To get away with this problem, we have to pass in the arguments as args. The function that pass args. This works. Let's try run this. Type error happened. And this is able to handle the exceptions. This is how we write custom annotations. Annotations in the sense decorators. Decorators and annotations are on the same. Yeah, that's about decorators. So exceptions were discussed yesterday. These examples, let me create a new file and then repeat them. Basically, so if any error happens in a program, let's say a divide by 0, the computer cannot compute 1 divided by 0 because it's going to be an infinity. And in our programs, we write, we might get into so many problems or error scenarios. So the way it does programs execute is, let's say I have a print statement hello. After the error statement. So this is definitely going to have a problem. So this, as soon as this calculation is done in the CPU, it will exit the program, it will error out, and this is not computable. And whatever statements that we write out of it or after it will not get executed. So in situations where we are running some kind of service, if a client request fails due to an error, server should not come out or exit. So in that type of scenarios, we could have to handle these errors gracefully and return the error to the client and continue serving to other clients. So let's try to execute this file. So start file. So as soon as this 1.0 error is happening and it's not continuing to print this statement, it's coming out of this execution loop. So in order to handle these type of issues gracefully, we use blocks called try except blocks. So this except accepts a type of exception. So exception is a parent class of all exceptions. So basically, this is a generic error handler for us to handle all types of errors. Anything that breaks can be a divide by zero. This is especially a divide by zero error. So either it is a divide by zero error or key error, whatever it is, this exception class is called to catch it. And we are actually saying that if any error happens, just do this and continue executing the code. Let's run this. So this statement got executed because we had a zero division error here introduced, and it continued execution. So if I want to see what is the exception is all about, what type of exception happened, so I can accept that as a parameter as x, or I can just put it as b. So any variable in the case. So I can print this ex here. What's this? Ex is over there. If I print this, I have to use an exception. How do we use this syntax? So it has printed division by zero error. Basically, what it's saying is if I just do print type x, it will give me what is the actual class type of this error. If zero division error. If I don't handle this at plus, it's just put this block and plus one can try to do this error. So and by default, Python prints the error type along with the description of that error. So the description is a string representation of this error, division by zero. When we tried printing that error object here with this, we actually got division by zero. This is the string representation of the error or exception. So error and exception are one and the same. Some error happen, and the description of the error is printed as x. And the type of the error is division by zero division error. Suppose I have few other lines. Let's say I'll come into this and I'll do one operation that is add a number and a string. Let's see what the type of error is. So if the type of error is type error, and the message that it is giving is the error message is unsupported operand types plus integer and string. So basically, we can handle different types of errors based on each type of error. We have custom logic to execute that can be done with multiple except statements. Let's just add those except statements. Except zero division error. Something. And similarly, if I encounter a type error, In general, if apart from these two exceptions, if any other exception happens, this block gets executed. So this is a generic handler for all types of exceptions. And the more specific exception types should be put before this except block. So the generic exception type, if we use in the first, this when program is getting executed, it will see if there is an error. It will first check what's the first exception that we're having. Okay, this is not matching zero division error, so I go to the next one. Is it matching type error? So then execute this logic, this block of code. If not, then check this. So exception, if I'm using exception as the handler, it matches all the error types because it's a parent class of all the exceptions. Zero division error, type error, all these inherit from exception class. So this exactly matches this. So if I put this condition here, no matter what the exception is, it always executes this code because this is the first statement and it is matching this exception that we generated. So I need to always put this exception block at the end of all the more specific exceptions. Okay. So now I'm handling zero division error, type error, exception in general. So let's just put this code in a function then. So I have a function cause error. Let's just say I will pass an argument called n. I'll just do this n. I'm just going to call this cause error. This is not going to cause any error. If I call this with 0, this is going to have a zero division error with this line of code. Let's run this. So now we are getting zero division error. Let's say I have some other functions which will have these kind of errors generated. Let's say every time I have to handle this in any part of the code, I will have to repeat this try and then except block entirely. There is a better way to do this. Instead of wrapping this entire thing in every time we want to handle, we can wrap this entire function within a decorator. Decorator actually means a wrapper on top of an existing function. So when I'm calling a function, if something has to happen before and after the function gets executed, that is what we use decorators for. So let's just see how decorators go. I'm just going to comment on this portion and simply explain how decorators work. So let's say I have a function definition of y. Here I'm not doing anything. Or just print some statement. So let's say I want to wrap this function, call this function within a specific set of preconditions. Let's use this itself. I have to wrap this under this kind of statements, try catch plots. This can be done, this wrapping code can be done in a decorator. So I will just declare a function. Decorator actually means a function itself. So let's say handle exceptions is a decorator name. It's just a plain function. First argument is going to be a function reference to it. So this is how we declare a decorator function. Decorator is also a function which accepts the argument as a function reference. So this function reference we are going to pass to handle exceptions. So inside this template of how to define a decorator is like this. I will define an inner wrapper function. And then from inside that function, I'm going to call whatever is passed to handle exception. This function, whatever is passed into this as an argument, that function I'm going to call inside the wrapper. That's it. And then I will return wrapper function. This is actually a decorator. Now I can use this decorator for any function that has no arguments passed. Let's just put this above this one. So now this is a decorator. I'm just putting a comment here. It's not necessary decorator function. So now how do I use this decorator function on any function like this? So this name I should copy and put an @ symbol just above this function and then use that function name. This actually means this function is decorated by this handler, this function. So handle exceptions is a decorated function that is decorating this function. What this actually means is that this function reference, my function reference, is actually going to get passed as argument for handle exceptions. So when I'm doing this syntax, if I'm typing like this actually means I'm actually passing, let's say this is equivalent to handle exceptions of my function. That is what this actually means. If I'm decorating like this actually means this. Define this and then pass handle exception, call handle exceptions with my function. So whenever my function gets called, internally, this is what is going to happen. This handle exceptions function is going to get called with this function and all the arguments that passed to this function. So now let's execute this. So this function I'm going to use try catch with. Inside the wrapper, I'm going to use that try catch and call this function inside the try catch block. Try itself. Simple. Now let's execute this my function. My function, I'll just scale. And my function. This is what it has. The same function, let's do the same thing with this cause error. We want to put it below here. This function also I'm going to use handle exceptions. Now 2 times I'm using the same code format and I'm not repeating this try catch box. So instead of try except, I'm just going to put all this code to handle all types of errors so that I don't have to repeat for every function call. So this is a good use case. We don't have to repeat for every function call. We don't have to repeat this exceptions handle. Now there is a simple small error. So this function does not accept any arguments, but this function accepts one argument. So Python is going to complain about that. Let's try running it. And this cause error also we should call, let's say, zero. Cause error. It's divide by zero error. I'm going to trigger. Let's do that. So this Python complains that handle exceptions local stack takes 0 positional arguments, but 1 was. So basically what is happening here is when I call cause error with 0 as a first argument, this is actually calling handle exceptions with function argument. We are passing this also 0. It's calling cause error with 0. So this function, what we declare here, this function does not accept any positional arguments, but we are actually passing by calling this cause error function with an argument. Yes, this function is declared with one argument. This is calling out. So in order to handle this scenario, we have already seen one instance of declaring a function. Let's just revisit that. Let's say I have a definition of a function from 1 as 1 to 1, 3 arguments. Then so now this is the sub. Okay. Now, if I have to pass n number of arguments instead of 1 or 3 arguments, if I want to handle n number of arguments, any number of arguments, I can declare a function with star cards which accepts a list or a tuple of arguments and then sums it up. It's called from 2, 1, 2, 2. So this does, let's say I can pass 4 and 5 also, any number of arguments I can pass. So that this function is able to handle any number of arguments that are passed as parameters. So that's what we are going to implement here. So in a generic way, if I have to fit this decorator to work with any type of function, I need to make sure that star args is placed here. And I can do the same thing here. When I'm calling the actual function, wrap the function, I have to pass all those arguments back to the function. Now, this one gives an empty args list, and this function gives one argument in the args list. So in generic way, we have handled it. Let's run this. So it entered and something to do with 0 division error because we called this function with 0. This time, let's call it with 0 and do the same thing. First call is successful. I'm in my function. This function got called with the exception handling in place, and cause error got called, and because we are handling the exceptions in a generic fashion, the 0 division error statement got printed. When we call the same function with a, type error happened. Because in the quasi-array function, we are doing the sum as well as division. So this is how we write decorative functions. This is an advanced concept of Python. You don't need to immediately understand the decoratives. As you use Python, you will understand more. So leaving that out, now let's get back to the exceptions. So there is something called inheritance we have seen in class type inheritances. We can actually extend exceptions in order to have our own custom errors or custom exceptions. So how do I do that? It is by inheritance. Let's define custom exception. This is an exception and it inherits from exception. So as I mentioned earlier, exception is a base class of all exception types, zero division error, type error, and other types. So all child classes of exception. Exception is the base class, which is a superclass of all. Here I'm going to do nothing. Custom exception, just inheriting all the properties and attributes, functions, and every single detail of exception. So now I'm going to cause the error by tracing an exception, custom exception. And the message I can pass here, right now I'm not passing. It's try causing this error, causing it. Now, this has created a custom exception. And I can actually pass any custom message here. This is custom exception. And the exceptions message also gets printed as a traceback. So similarly, we can have exception types for multiple inheritance we can do, multiple levels of inheritance we can do. Well, I revisit this for custom exceptions. We have defined HPV exception, that is coming from base exception. And I have defined an overriding constructor in this exception that calls the super class, which is exceptions constructor with this specific message. So I'm not implementing that in this child classes, so that this is common functionality that is inherited by point. And we are extending HTTP exception in not found and server exceptions. Now I'm raising the server error, which in turn prints status code messages. So on and so forth. This is about exceptions. So yesterday we stopped discussing about threads. We haven't discussed threads yet. Let's just try demonstrating that threads. Let's say, for example, I have a long square function. Yesterday we just discussed. So this function is going to sleep for 2 seconds. This is just to simulate a long running process. Usually some square does not take much time. But if there is so much things to be done, there can be so many error statements here, and CPU will be busy doing those operations. We have to import the package for line in order to use sleep function. What this actually does is it sleeps for 2 seconds and then turns the square of the number. So I'm going to calculate this square for like 10 numbers. For I can just do with this for n in range 10. I can do 1 square of n. This is one way to do it. Let me do another one. long square of n, where n includes 10. This is a shorter operation. We want to print this list. Or I can do one thing. I can just do print and at the end print the entire text. While it is calculating, we are going to print the number as well as at the end, after all the calculations are done, we're going to print the list of numbers. Let's run this code with let's like takes 20 seconds because each of these long square calls is happening in sequence one by one. I'm going to call this for number 0 and then number 1 and then number 2 and then the number 4 and so on. This is all sequential operations. So this takes like around 20 seconds to complete. So what if there is a way for me to call this function without waiting for the return? So ultimately what I need is the end result of the entire collection. What's the range of numbers, the squares that we result in. So we can make use of threads forward. Threads can be imported with a library called thread. So basically what threading or thread means, CPU is going to CPU is very fast. It's hundreds of gigahertz. 1 gigahertz is like 1000 hertz. Like that many calculations it can do. So this roughly takes 10 or 20 hertz to calculate. So because we don't have to limit the compute capacity by the way we are calling the function, so we can increase the performance by increasing the parallelism. So this threading library allows us to call this long square without waiting on its execution or completion. Let's figure out how to do that. I'm going to comment out this portion. So how do I create a new thread? Every thread runs in parallel. So thread, I'm going to create a variable called T1. And I'm going to initialize this with threading dot thread. And this will instantiate a thread object. So the first argument of this thread object is the target value. Target is a function name which I want to call. Long square is the function name I want to call. The second argument is a tuple of arguments. Arguments I have to pass. Currently, the argument is only one, but the syntax of thread allows you to pass a tuple object in the args. So how do I pass one single element into the args tuple? Is through like this. One comma. I just put one comma. This actually means this is a tuple. If I don't put this comma, this Python will assume that you're only passing one value, which is wrapped in parentheses. There is no special meaning for parentheses in Python or any other language. In order to specifically tell that we are passing a tuple instead of a single value, we have to put a comma. What this means is this arguments, I'm passing a value. That value type is a tuple and it has one single element in it, which is 1. And I'll copy the same line. I'll create another thread, T2, and I'm going to call the same function, but this time with a different node. So like this, for each n, I in range 0 to 9, I'm going to call this line. Similarly, I'm trying to call this long square function 2 times with a threading module. This time, these T1 and T2 has to start in parallel. So calculation will happen in parallel. Whereas this code executes one by one, calculates the squares one by one. This code calculates these things in parallel. So another thread I can add 3. I'm sorry. Now let's start these threads. So we have just created these threads. We haven't started these threads. We have not scheduled these threads to run on the CPU. We haven't even called these threads. Just created thread objects like this. So how do I start the thread? So that is through start function. Even the start means it will start only this thread. I have to start all the threads. Next. Now, okay, this has started. So if the program comes to the halt, I mean, at the end of the line, it exits. So the problem with exiting the program is whatever threads we have triggered, they all get stopped if the program execution stops. So Python doesn't know that there are 3 threads running and I have to wait for those threads to complete. So we have to explicitly tell the interpreter to wait for these threads to complete. Threads are nothing but one independent job that is running or a parallel job that is running on the CPU. So we have to explicitly tell Python interpreter that wait for this thread to complete. So that is through join call. So what this means is wait for this thread or this function to get executed and return it. So similarly, I have to wait on all the 3 threads. I have to wait till all the 3 threads are completed. This will halt the program, pauses the program from exiting till all these threads are completely executed. Let's run this. No, this all things have been completed. But if you see the output here, first output is 40, second output is 1, and third output is 9. But we are actually calling this in 1, 2, 3 order. So the second thread got executed or completed first, and this first thread got completed second, and third thread got completed at the end. So the moment we are starting these threads are independently running. They are not waiting on one another. If I'm triggering all these jobs in parallel, all these jobs can go in their own space. If a process or if a thread is waiting on some input or waiting on the sleep, the other thread actually can come out of the sleep and continue its operation. So that is massive parallelization in terms of threading. Same thing, let's do it with 10 threads. So I have created each thread one by issuing this, creating a new thread object. Let's do this same thing in a better syntax for 10 threads. So I'm going to use the same syntax that I used here. Let's just say threads equal to a list, threading dot thread. Target is going to be long square. Defaults is going to be n comma or n in image. This actually is initializing a list of threads. So for each of them, I'm going to do one. T dot start I can do the same thing, just to do it a bit more with a for loop, just to give you more context on different ways of issuing this. For t in threads, t dot start, that's it. And now we have to wait on these threads, all threads. Same thing I'll do. I can do it this way, t in threads dot join. I can do it this way, or I can do it in a more a compact fashion. We got join. That's it. Now let's run this program. So we are actually triggering all 10 calculations all at once in time. Those things can output in any order we want. If one guy is using one guy waking up and running MC. So this order is not matched. Yeah, order does not matter. Order, when we are triggering threads, order cannot be controlled. So we want, if some job has to be done independently, it can be done independently. So now let's say, yeah, that's a good question. Let's see how to get this list of numbers, squares, which numbers square is what. So we have to store that somewhere in the results. Right? Let's do one thing. Let's create a results object. Results, let's call it as a dictionary. And one small correction I need to do when it comes to dictionaries is I mentioned that if I take my dictionary and have a apple, or like this. So I said that only strings are allowed, but that's not exactly true. The key can be even an integer also. Let's just do it. Integers. 1. We can have objects also, or maybe a 0, 0. It's allowed as long as the key is unique. Any type of key is allowed, and any type of value is allowed in Python dictionaries. So this same thing I'm going to use to store these square values. So this result will have, let's say, 1 will have square of 1, 2 will have 4, 3 will have 9, like this. So I want my threads to update this results dictionary so that I can print the dictionary. Now I can print the results. As of now, we are not passing this dictionary to these threads. Let's run it now, and it doesn't print anything. This results, I need to pass it to the thread calculation logic. Long square, if this accepts a dictionary. And if I am appending the dictionary, yeah, let's say results number, equals number, uh, it adds this and returns it as well. Now, at the end of the loop, I can actually print the results object and then get what is calculating, which value square is what. So that results object also need to be passed into long square. So now long square earlier we was accepting only one argument. That's why we have used only one argument. This So what we are doing here, we are calling the results along with number and passing the results dictionary to this function that is called in the thread. And now I'm going to print that result at the end of all the threads of it completed. Let's execute this. So at the end, it's printing. The order did not matter here, but as long as the number key is 3 and its square is 9, this can be useful. So this is how we use parallelism in order to do calculations. Let's do the same thing without using threads. If I do that, same logic will use it for 10 numbers. This executes in 20 seconds. Without using thread, it's going to take a long time. With threads, it executes in 2 or 3 seconds max. So that's the advantage of parallelism and multi-thread. So what we have done here is, okay, there is one small difference between a process and a thread. So there is, let's say, I can do the same thing with processes. It's just for the let's do this with 0 to 5 and 5 to 10. I'll just use same row. I can thread start. So this is not using threads. I can do this in multiple processes also. Parallel calculations I can do. I can threads. Two processes running. They both are calculating independently. This process is still computing. So the difference between these two things, so the way of triggering two processes and triggering two threads is a little different. So the difference between these two is the memory that is used by threads is shared. Let's say this results dictionary is actually shared between among all the threads. So this, when any thread in this program is referring to results, it actually refers to the same object, so which is shared across all the threads. When I'm processing this in a new process, that results object will itself have a different value. So memory cannot be shared by two processes. Only threads can share the same. So that's the advantage. That's the use cases where we will use threads instead of processes. We can also trigger multiple processes from within this Python code that we will see next. As of now, the main difference we need to understand is threads will have the shared memory. All variables, all objects that are stored in the program, all threads will have the same object references. So if one thread modifies this results object, the other thread also sees the modifications. So when I'm running in a different process, when one process modifies the results object, it is modifying its own copy of the results object. It's not modifying a shared copy. So that is the main difference between running two processes and two threads. So we'll get in depth into threads and processes later once we get familiar with this technology. So for now, it's just enough to know that there is a difference between the process and the. Let's go back and uncomment. This is about threads. So let's now see the processes. Now we have triggered two processes manually from the terminal. So Python, if I execute this, this is actually going to trigger a process. So the same thing, we can do it within the code itself. We can have spawn multiple processes instead of spawning multiple threads. We can spawn multiple processes as well. Let's do that. So especially for handling processes, creating new processes, we have a library in Python called multi-processing library, multi-process library. For that, I need to install a package called multi-process. Multi-process. You can install multi-process. This allows us to create new, spawn new processes. So I need to import this from the process, import process. Also import same code and then copy from previous code. But we have threads, same concept. This time, I'm going to copy this, but not. I'm going to demonstrate the memory sharing process. Instead of threadings.thread, this time we are going to use process here. Similar to this, we are going to use style instead of threads and use processes as the variable name, and for p in processes without start for p processes. This is going to start the processes and then join for the in process, similar to what you did for threads, without join. Same thing we are doing for process as well. So this is going to demonstrate a difference between what a process is, what thread is. Let's run this code. This time, so each of the calculation is going to happen in its own process. Let's run this and then print results. This time results module will not have actual data because results is not shared. So this results object is always going to be wrong. Let's run this. It's on processes. Right. That is a system. So let me introduce the C here. This is specific to Windows operating systems. In Linux, this won't happen. But process processes and range processes process. Similarly, process it upstream and then swing flash. Sorry. Yes, that's there is a problem with Windows. That will be safe. So I think we have to do something like this. Yes. I will explain what this is later. Let's figure it out. Okay. Now we are starting 10 processes in parallel. So let's go back to the syntax of using this. Yeah. Now, what we have seen here, if I'm printing the results here, it's actually printed empty, even though this guy is modifying results object to add these numbers. We are still seeing the results as empty because these threads, apart from threads, processes do not share this results object, even though we are passing this results object or a dictionary. So it's actually going to make its own copy of the dictionary and then use that dictionary as we are doing the process here. It doesn't manipulate this results object because it doesn't have access to this. So the main process is different and this child processes that we triggered are different. They don't share the memory. So that's the advantage of threads. So the main difference of threads and processes is that a process can run on different CPU cores, whereas a thread can run only on the current CPU core. So in modern CPUs, we have multi-core CPUs, right? 4 cores would come in i5 processor. So the advantage with processors is that the two processors can run in parallel in 2 different cores. Whereas a thread, multiple threads, if you are spawning from within a process, all those threads have to share the same memory space and same processor core. So it's just a simulation of parallelization when it comes to threads. In the processes, if you're running multiple processes, that is actual real multiprocessing. So whereas threads only simulate the parallelism by allowing CPU to work on some other thread while one thread is waiting on a certain operation or certain event. So these core concepts we will discuss when we go in depth into computer science concepts. So the difference is that clear now. The memory space is not shared by different processes, but only by threads. So we have to make use of threads and processes based on our use case. If memory has to be shared, if same variables need to be accessed, same data structures need to be manipulated, we will have to use threads instead of processes. So when it makes sense to have different processes, let's say to manipulate files. So having multiple files processed in parallel, that kind of scenarios, we can use processes rather than threads. So that's about threads, multi-threading and multiprocessing. We can do that. I'm just adding threads dot time dot sleeve only to simulate a large process. Let's say instead of this time dot sleeve, I can keep it. You won't see any difference. So because I put time dot sleeve, we are seeing the difference. If I do it in sequence and if I do it in parallel, what visual difference we will see in real time. So instead of this, usually we will have like calculations ranging from like large number of code lines if I have to write. I'm just trying to simulate the workload that we usually put on the programs. This time dot sleep is not needed. So if I just do this and comment this, basically, you won't be able to see that much of a difference. Whether we are using multiprocess or same process, won't make much of a difference. This will Python. So this one, you won't see any difference if I don't put this. So the parallelism that we get, the advantage of parallelism, we can only see when the process is taking too long to complete. If it's like milliseconds interval, if there is a difference, we can't observe it with our perception. So that's the reason I have to simulate a heavy process. That's about processes. So till yesterday, we have seen basic Python, and we have seen some kind of advanced concept called threading processes, multiprocesses. That's done. So for today, let's look into writing files in Python. So let's say in operating system, we have files, right? Even these source code files also are files. So how do I write text files and binary files in Python is what we will look into today. And after that, we will go over the packages, how to use multiple packages within Python. So this multiprocess, all this pip install, whatever we do, these are all packages, or in another term, it's called a library. So how to use those libraries, how to create our own libraries or packages, that we will look into today. So with these two concepts, we'll wrap up Python basics course, and then we'll continue with fast API for creating REST APIs. Then we will look into UI, how to build the UI on top of these APIs. So let's start over. So far we have been using Python shell to execute scripts. So from last class and the previous class, we have been using the files itself. So when I have one file here, I can execute that Python file with this command Python and the file name where we wrote the code. So let's create another file manipulation. Okay. So in this, we are going to look at how to create files, update, add data to files. So as you can see, this folder doesn't have any text files. So these are all Python files. These are all text files in the sense it's all text files. But I'm going to create a new file from Python code and write some data to that file in this folder structure. So how do I create or open a file, new file, if I have to create from Python code? I need to use open function, and the name of the first argument that it accepts is the name of the function, name of the file name. I'm going to give a.txt, and the second argument it accepts is the mode in which we have to open this file. Let's say if I'm reading the file, it means it will be opened in a read-only fashion. So if I need to write the file, then it will use write mode. So if I specify R here as a second argument, that actually means I'm opening the file a.txt for reading purpose. So that means if the file exists, it will open and starts reading the file. Meaning we haven't started reading the file yet. It will just open the file and keep it ready for us to read the data from it. So now there is no file called a.txt here. Let's see what this thing gives us. If I execute file manipulation, and we have this file not found there. No such file or directory a.txt. So there is no file called a.txt. That's why we are getting this error. So there is another mode we discussed just now, write mode. For writing, let's just open f equals open a.txt. And then this time I'm going to open it in write mode. So the advantage with write mode is it creates the file if it does not exist. If there is an existing file, if I open it in write mode, it will overwrite that file. Let's see how this works. And this did not throw any error, and a file called a.txt has been generated. You see, this is empty. We haven't written any data to it. That's why we are showing this as empty. So now I have opened the file in write mode. I can write the data, something I can write. Let's write f dot write. And I'll work one more write call. This is a sample text. Let's run and see if this gets stored in the a.txt. So the advantage here with W right now is that if the file doesn't exist, it will create. If it exists already, it will overwrite it. It doesn't add content to it. For adding content at the end, there is a mode called append that we will discuss in a bit. But for now, so we are opening the file and overwriting this file with this data. Let's run this. And let's go to a.txt and see if this got stored. This got stored. But sometimes OS handles files in a different way. So it's not always evident that it will write immediately. So when I open a file and write something to it, it doesn't always end up in the file immediately. So there is a buffer involved here. The operating system doesn't write data to the files directly every time we write through the code. It has some optimizations. So writing to a file is a costly operation. So that's why the operating system does some kind of buffering. So that once the buffer is filled, then only it will write to the disk. So that kind of situation is there. So whenever I have to make sure that the data that I write into the file ends up in the file, I have to actually close the file. So how do I do that? Is through f.close. This makes sure that as we have opened the file, and when we close the file, all the data that we are writing to the buffer is already flushed into the file. So this makes sure that all data is flushed into the disk or into the file. So this is a basic setup for writing files. So here we have seen a.txt having previously a.txt is there. Now I'll re-execute this code and I'll open a.txt. This has replaced the entire content of a.txt with hello, this is a simple text. So what if I want to add text to the end of the file rather than replacing the entire contents of the file? So for that, I have to use append mode of the file a.txt. Append mode is so f.write. This is another text. So this one I'm just commenting off so that we can demonstrate. Now a.txt has this text. And now I'm opening the file in append mode. And this adds the data to the end of the file. So let's run this code. a.txt, and this is another file has been added at the end. So one thing we can observe here is that, so this is one problem. We are seeing this entire contents in one single line. So there is a special character called \n, which is the new line character. We haven't written this character. Every time this code, when I'm typing one line and doing the enter or return key, so it's actually adding a \n character, new line, that is called a new line character. So I have to write new line characters also. Let's open this file. Let's add the new line characters also. So this thing opens the file in write mode, which actually is going to replace the entire captions. I'm going to write this at the end of that text. I'm going to introduce a new line character \n. This is going to add a new line character in the enter. The return key, if I press, that is what the operating system does, or any text editor does. So if I have this \n character, that is our new line character, we will add a new line. Let's execute. Let's go to a.txt. So now if you see here, this has introduced a new line. This, if it is in the second line, means this there is a new line character over here. Now let's do one thing. So in reality, let's see how this actually looks like. So let's open the same file. I'm commenting on this file. Let's open the same file and read that as text. Text goes f.read. Read does reading of entire text at once. So let's just print text here. And then f.close. So this printed along with the new line characters. Let's just print this not as a text. Let's do something like, how do I show the text is backslash and character is to scaling. Let's try text. It's not actually, when I'm trying to print it in the console or terminal, it's actually not showing the backslash n, but it's actually putting the new line character exactly. So in order to see this, I think I will need to use JSON. This I will explain in a bit. What is JSON? All this. So if I just serialize this text into JSON, to show the new line character. If you see the JSON text, it's actually giving backslash and in between. Hello, and this is something text. This is what the system sees. When I'm trying to print this with print statement directly, it's going to replace this backslash n characters with actual new line characters. So this is the JSON representation of the text, and this is actually, we are trying to print this text. When I print this, backslash n gets replaced by the new line character. So this is how we read a file. And similar to reading, we also have seen append mode. So even in here, I can have, I'll just use backslash n character here also. Yeah, so if I run this, all lines will come in each and each of these lines comes in its own line. Okay, that's about reading, writing, appending. But there is a shorter syntax for this. If I have to do every time when I open a file, I have to actually close the file as well. So there is a shorter method for doing that. That is something called with keyboard with open of either txt in write mode or append mode as if this is a new syntax. I can do file manipulation here, file dot write. Yeah. Okay. Right. So now if I run it, if I'm using this kind of syntax, I don't have to use this f equals open and then f dot close. This one I don't have to use. As long as I do this automatically, or when all the lines of code within this block are executed, it will automatically close this file. So that's something that we can use. So yet another line is going to be appended to this text file. This is how we write and read text files. So after closing, let's just demonstrate one simple example again. So I'm doing A, and if I'm closing the file, if I try to write after the close operation, so you can do the text file. So if I try to write it, you throw an error. So after closing the file, you cannot write. So we have to write all the text that we want to write before we close the file. Once it is closed, it's closed. We can't write anything to it. It will throw section. So that's about how to write read from files. So I just want to show you the JSON syntax also. JSON is a serialization format. Let's say if I have a dictionary. So JSON is by default comes with the Python installation. JSON is a package which will be used in most of our STLs. So this is important. So if I have a structure, let's say my dictionary, let's say a table. So I can actually write this into a file. This data structure I can write into a file, but before writing this data structure, we need to serialize that into a specific format. So in all web programming, we use JSON extensively for writing and reading, for serialization of data representation or data structures in the code. So in order to write this to a file, I have to do with open, say a.json. This name can be anything. W as f.write or json.dump string DOPS of the dictionary. So what this does is it will convert this dictionary into a serialized representation called JSON representation. So once I write this, then I'll show you how this JSON representation works. That's it. We can just execute this file and see a.json. If I go to a.json, and this is how it writes. Although this looks like this same structure, but it is not actually a data structure environment. It's a serialized format. It's a string. So similarly, if I do open and read more and read this text, I'll just print that. I'll just move out this portion. If I read this JSON file, this does read this as a string, not as a data structure or a dictionary. And this is printed as a string. So if I do type of f.p, that's actually going to be a string, not a dictionary. If I do the type of my dictionary, it will show as dictionary. So my dictionary is actually a dictionary data type, and once I serialized it into JSON and read the same JSON, that is actually a string. So in order to convert this string into another data structure like my dictionary, so unpacked data structure. So this f.read, I'm going to store it in one variable, JSON data equals f.read JSON.low string of JSON data. If I do this, whatever is serialized into JSON format, that same data will get converted into a dictionary. So this unpacked data structure will be again a dictionary. If I do print that and the type of unpacked data structure, the type will become dictionary. So once I write it, if I read it, I have to make sure that it is loaded as a data structure from serialization. So this is what is called serialization, and this is what is called deserialization. So a program data structure representation, once it is, if I have to write it into a file, I have to serialize the data and then write it as a string into the file, JSON file in this case. So if I'm reading from the file and preparing a data structure in the memory, I have to deserialize that. So that is what we did with loads, deserialization, and serialization with dumps. Dump S means dump string, and load S means load string. So let's do this. Now, if I read it and unpacked it or deserialized it, that is becoming a dictionary. So that's about JSON. We can actually write custom encoders and decoders for objects. How do I write custom encoder and decoder for objects? Let's custom decoder. Everything. So let's say I have a class called animal. And we will consume it. Okay. That's got it. Now I have a Python dictionary that says A as animal. What? B as CS. Just one should be object. So it works with JSON.dumps, works with plain strings and plain data types that Python uses. So if I have custom data types like classes or objects, if I try to do JSON.dumps of Python dictionary, so I need to import JSON here. If I try to execute this, object of type animal is not JSON serialized. So this object, Python doesn't know how to serialize this object. So in order to work around this and in order to create custom serializers, this is important when we are working with our own custom objects and JSON responses in the HTTP servers. So I need to import another class called JSON encoder. So I need to write another encoder for animals. How to encode animals with the JSON string is animal encoder. This extends JSON encoder. This is inheritance we discussed in the last class. I'll go over this one more time. Here I need to override one simple function called default. I'm writing custom encoders. I have to override a function called default. So JSON has encoded all the properties, attributes, methods will be inherited from JSON encoder here. So I'm just going to override default method. So this accepts first argument as self, and the second argument is the object itself. So I'm giving the name as O here for the object. So what I need to do here is return super dot. If it is object of type of object is equal to animal. So we have to make sure that we are only encoding animal objects. So this O can be anything. If somebody has used some other class and created an object and passed that object, we should not serialize that with this encoder. So it's an array. So if we don't see that this is let's just do do nothing. If the type of object is animal, then we need to do serialize that. Return something called animal the self name. So when I'm serializing this animal object, I need to return the name of the animal in the default. So serialize it. If it is not an animal object, we have to call super classes default is an object. And that's it. So this is how we write a default custom encoder. So now if I do the same thing with JSON terms, and this time I'm going to pass in the encoder function. What's the encoder I need to use? I can specify with an argument called class equals animal encoder. This will be able to serialize the animal objects. By convention, it has yes text value as an animal object. So I can write now execute no more than images of encoders. Oh, because we have to use a separate syntax for this from JSON import JSON encoder. JSON encoder itself is not a module. It's a class within the JSON module. This is how we import a specific class with JSON and inside of it. So I'll go over what modules, how to create our own modules. Okay. So let's run it. Has no attribute name. Actually, I should use O, not self. O dot name, object dot name, or data. Let's run it. Let's say I have a class called animal and I have a property or attribute called name in it, and I have a dictionary that has key as a and value as animal object. If I directly try to serialize this dictionary because animal object is there, it doesn't know how to serialize the animal object. It can serialize basic data types like integer, float, or string, or any other basic data types in Python. So if I do this now, and this object of type animal is not JSON serializable, this kind of error is thrown by the Python interpreter. Now, in order to give the hint of how to serialize this animal object to Python or to the JSON library, we have to have an encoder called JSON encoder. JSON encoder is the default encoder that is used by JSON library when I'm doing the dumps function. So I have to extend this functionality to make sure that the serialization works with. And so serialization in the sense when I'm doing JSON.dumps, that means we are converting this Python object into a serialized format called JSON. So that is what serialization meant. So for this, for making sure that animal object is serializable, we have to create an encoder. So we have introduced to an animal encoder that inherits from JSON encoder. And one thing, only one method I need to override in animal encoder is the default method. And by default, it accepts the first argument as self and second argument as the object itself. So whichever object, if I'm serializing this entity, JSON library will pass in this object in place of O. So here, what I need to do is, if the object type is animal, then only I have to return object's name. So this is the name, right? This object I'm referring. So this A object is nothing but an object of type animal. So if I'm doing O dot name, that means this animal's name we are storing. This name is what will be returned. If it is not a type of animal, then I have to call the super's whatever default functionality that JSON encoder gives. If it is an integer, it will not get passed to this. But the thing is, we have to always handle the data type. If the data type is animal, then only I have to do this. Otherwise, just use the super classes default. Just use return after return. So in this particular scenario, I'm commenting outcast, and I can give a hint to JSON dumps method on what classes to use for serialization. That is through CLS argument. If I see the documentation here, CLS equals, it should pass in JSON encoder. So JSON encoder, we have implemented animal encoder. Animal encoder. When this is called with this clue, if you don't know how to encode a specific item, just call this guy. That's what we are hinting to the JSON library. Now if I do execute this, and the result is when I'm calling the encode, it's giving the name. In this place, it's serializing A as R1 with the name of it. So this is about encoding JSON serialization, writing files, reading from files to everything. Let's now visit a concept called modules or packages in Python. So any package, any file can be considered as a package. Let's say I have a file called primes. So let's say now we're going to the modules concept. Let's say I have a file called primes, and in this I have, let's say, one function is prime function that accepts a number and accepts from primes. This is all logic that we can use to find the prime, whether it is a prime number of power. on primes equals change to integer and the power of 0.5. This I have already explained this last to you when we were discussing about functions. If it is prime, if it is found in previous primes, so what we are trying to do here is, if I have to find out whether a number is prime number or not, we're just trying to get the list of prime numbers that were found from range 2 to the power of n to the power of half. So that is square root of the current number. That is a basic formula for finding prime numbers. So we have to check all the factors. So these are the factors. Let's say if a factor in primes, you have to see if this number is divisible by the factor and odds. Otherwise, reject. So this is just to demonstrate a functionality with modules. We don't have to have this kind of complex function also. So I have, let's say I will declare another function called list primes up to a number, maximum number. This in turn calls this function found primes as an empty. Let's say we shows this one. So n in range will come on max is prime. If is prime, then I will found the primes. Found primes start up and this we are actually collecting all the prime numbers into a list. Done found primes. Forget about the logic over here. Just remember there is two functions and one file called prime.py. I will have one more file called use module. So modules, how do I use modules? Or like I have this in a separate file, and how do I use this code inside this file? That is through importing another file into this. Just like Java, we have import statements. So similarly, we have import type. So if I do import the primes, this imports entire primes.py into this file. So now I can actually call list primes. Print primes dot is prime of 5. So maybe I can have, let's execute this now for now. Again, module. Okay, this is printing. 5 is next. So I can also import in a specific function itself. I'm right now importing the entire primes file into this. I can also import only this function into this those modules. That is through from primes import list primes. List primes is the function name. So only this entity I can import later. So now I can actually call print list primes of maximum number. That's 20. Okay, this also works. It listed all the primes from 20. So this is how we use another file in one file in another file. And what if I have to bunch, collect together a set of files into a separate package? So a package will have multiple files in it. So one file is fine. One file we can directly import it like this and use. I want to implement a package. I can create a folder for a package. And inside it, I have to create a special file called init underscore underscore init underscore underscore .py. This actually says to the Python that this is a package. My package is a package. So I will have one file created here called factors. So this has a function. Let's define function here. Get factors of that. It gets a number and it finds out all the factors of that number. That actually is going to return a list of factors. Factor factor n range 1 from n plus 1 if n divided by factor modulus yes n modulus factor is 0. So this means, so go through 1 till the number 1 to 10, let's say 10 is 10, till from 1 to 10, check if any number is dividing this n number exactly. If it is exactly dividing, then it actually is a factor. So in the same code, let's say I will write another file in this package called primes. .py. I'll implement a function called isPrime again inside this. If I give a number to it, from primes equals 1. Similarly, return get factors. So the definition of a prime number is that the factors of that has to be, a number has to be 1 and itself. So there should be only 2 factors, which is 1 is always a factor to any number, and that number itself, let's say taken 7 as an example. 7 is divisible by 1 exactly, and it's also divisible by 7 exactly, which means there are only 2 factors to 7, which is 1 and itself. So this get factors, we are checking if the length of get factors, number of factors that it has is only 2. Whether it is, if it is only 2, that means 1 and itself is the factors, then it is a prime number. If not, it is not. This get factors I can import from this package, my package factors. Let's import that with that format from my package. Import get from package, my package dot factors. Import get factors. This imports from this my package, from this file, import this function. That is what this says. Let's try executing this. My package comes without doing. Not really following my package. Let's go inside my package. My package is undefined. I think we need to remove this times outside of this range. Okay. Let's go back to this prime student line. What we are doing here, we are importing from my package factors, this get factors function. So when we tried it within that file, it's actually trying to refer to my package, which is not found within this. If there was another package called my package here, that would have detected. So as this file was within this package, it wasn't able to recognize this my package. If I had accessed directly like factors, it would have recognized because within the same file, it doesn't have to refer to this package name. So if I'm writing another file outside of this package, I have to refer it with the package name and the file name. Let's run this code in the primes.primes2.p file. I'll just call this and this prime 5. Get factors needs an argument n. So that was a type mistake. So I have to pass n to the get factors. Get factors actually accepts one argument, which I forgot. So I'm passing n now. That's from the store. And 5 is a random. So what if I remove this init.py? This is very important. I remove this init.py. It considers this just as another folder, not as a package. The Python doesn't consider my package as a package. Let's run this. It is in the tenant, so it's well, somehow it's in the cache itself. It's considering this thing as a package and make sure that we use init.py in any package. Otherwise, it will not recognize this. Let's create another package without this init. Numbers. Just use factors here. Let's remove this. This time we are going to try without the underscore init. Now the name of the package is supposed to be numbers. Let's try numbers.factors. Import get factors. Let's try executing this. And no module name numbers.factors. Numbers is not a package because we don't have init inside the file. If I had init inside it, init now it would consider this. This actually means overriding the existing so let's go with this. Bringing this to my numbers. Package name is my numbers right now. I'm going to change this to my numbers. I don't have the init file in it. Let's try to run this. But this is somehow it is working, but make sure that we have the init file created without which the package mechanism doesn't work. Yeah, that's about packages, how to use them. So this is how we create a package. Every package will have an init file in it, which represents, make sure that it is declared as a package, and Python considers that as a package only when it has init.py in it. Yeah, this is about modules, and this is the last of the lessons that you have to consider. And there is one small concept that we missed. So last time we have used multi-threading processor.py, and here I have used a special logic called if name equals main. So similar thing, let's try running that here. Fine. Just print underscore name here. Let's see what this prints. Main. So it prints main. Whenever I'm executing a file directly, the name of that file is going to be main. If I do the same thing here inside the get factors function, it's doing this. We want to import factors. From my numbers, import factors. When I import this, all of the code that is there in the factors file gets executed. Let's try to print that. When this gets executed, the name of it will also get executed. So the name here, let's just print in factors w in trends let's try running this. In factors.py, the name is numbers.myFactors. This actually gives us the package name in which the file exists. So when we are executing primes2.py, by default, it comes in the main package. Any starting level code that we run to the Python comes under main package. That is why the name is main. So when we used main.py in process UI, when we check the name to be main, this means that we are using this file as a main entry point to source code, main entry point into the Python execution logic. So that is what we are making sure. So this is executed as a main package. So only when this is imported, if it is imported, that will not become a main package. That won't come under main package. That's the difference between using a package and a plain Python file to execute code. So in Python, we want to handle, usually the programs will error out if there is any error in the code. So there is a graceful way to handle these errors, or in another way, we call them as exceptions. So let's just try to create one error. Let's say I will have 1 divided by 0. This is an invalid operation. If I try to run this code, it will crash. So this is actually throwing an error called zero division error. Sometimes we will have to handle these exceptions or errors inside the code so that we can execute programs gracefully, handling all the errors. So especially in web servers, if some issue happens in the code, either due to user input, invalid user input, or due to server errors, if the server crashes, it won't recover. So it will create downtime. So in order to handle those scenarios, we will have to handle our code so that these exceptions are worked around. So let's try creating a stack trace. So this is actually giving a stack trace. This is called the stack trace of the error trace back, if you see. So if I have a function that does this, cause error. If I have this error inside a function, if I call this cause error function, and the stack trace will include which all functions have been called, which all code has been called to get into this particular error. So if I run this, now we have two stack trace items. So as long as we have this, we can debug this information. So let's say, how do we handle these errors gracefully? So it is through try and except blocks. Except. So exception is a parent class of all error types. Sorry, hold on a second. So let's run this code. Try except other. Sorry, I have to call this within this try block. So where the issue is happening, that code has to be put under try catch blocks. So this is happening inside the cause error function, but the invocation happens within the try catch block. So now it is passed without crashing. If I want to see the exception type, what the error is, I can receive it as any variable. And if I try to print this in X, it will give me the error message that division by 0 error happened. So this is about exception handling. So we can have multiple exceptions handled, like except division by 0 division error. As E 0 division error. Based on the error type, we can actually have a different set of error handling code written. And with that, we will have our own custom exceptions also we can create. Let's create a new exception, custom exception. So as I mentioned, so exception is the parent class of all exceptions. We have to derive or extend this particular parent class with our custom exception class. Custom exception is a subclass of exception. I'm not passing anything or overriding any functionality of custom exception. So all the default functionality I'm using from exception itself. So how do I raise this exception is through this code, cause error. Let's say I define a function that raises this custom exception. And then let me call this cause error. Let's execute. And this has raised custom exception. So if I want to give a specific message, this is a custom exception. I can give it in this way. Any specific errors, that description will come in the exception report. So that's a way to extend existing exceptions. We can have our own n number of exceptions. Let's create HTTP exception that extends exception. Just to pass here. I can have n number of exceptions. I will have not found exception, which extends again this HTTP exception, and then I can have its own init function, which is the constructor. In this constructor, I need to access self. And inside this, I need to call super, which means I'm initializing. If whenever I'm overriding the constructor function, I need to call super classes constructor in order to make sure that all the variables attributes have been initialized. Yeah. So we can have any number of exceptions written, custom exceptions written, extending the functionality. Let's go through threads now. So threads are useful for parallel processing of applications and application logic. Let's just demonstrate an example. Let's say I have a function that takes a long time to complete, long square. Let's say I have a function that accepts a number and does some kind of sleep, time dot sleep for 2 seconds. I have to import time module here, and then returns the numbers square. And for I will write a loop that starts from 1 to 10. In range, let's call this long square on each of these. This will definitely take more than 10 seconds because we are sleeping for every number. We are going to wait for 2 seconds and calculate the square. So this is actually to simulate an environment where large number of calculations and large amount of time takes the processing a specific application logic. So I'm just putting a sleep here so that we can demonstrate if there is a long running process or long running function, how do we make use of multi-threading? So this in a single thread, if I'm running it in one process, it's going to sequentially evaluate from 1 to 9. It's going to evaluate this square every time sleeping for 2 seconds. Let's run this code. And at the end, it will return, but let's print something here before returning. Print x, and let's call this. So every time, for every number that we are calculating square root square for, we are actually waiting for 2 seconds, and it takes the whole of 20 seconds to complete for all 9 elements. So this can be parallelized with using threads. So let's use multi-threading for this. So multi-threading is useful for parallel processing. So all this, if I have to calculate 1 through 10 all at once without waiting on sequentially, I can make use of threads. Import threading. Threading is a module we can use for parallel processing. Let's create threads for this. I'm going to create a thread. How do I create a thread? Is through this way. T1 variable T1 threading dot thread. Target is the method name which we want to call. long square is the bucket, and it also accepts an argument as a tuple. So this time I will pass 2 to the long square, and this also has to specify that this should be a tuple. So when I put a comma after 2, this actually means that I'm passing a tuple object which has only one element. If I don't have this comma, this actually means I'm passing value 2, which is an integer, and this brackets don't have any significance if I'm using around a single number. If I specify comma, that actually means that it is a tuple. So I can have like n number of arguments, but this particular long square accepts only one element or one argument. That is why I'm using only one argument, one element in the tuple. So this is creating a thread. So I'll create another thread, T2. Target is same function. This time I'm going to pass 3, and T3 I'm going to pass 4. So this is only going to create a thread, but it doesn't start the thread yet. So for starting this thread, we need to call T1.start. For each thread, I need to call this T2.thread start, T3.start. Okay. Now this will start the threads, and it will start processing these 2, 3, 4 long squares in parallel. And we have to wait for this processors to complete. Otherwise, if the program reaches this point at line number 22, it will exit. We won't wait for these processors to complete. So when we trigger this start, it actually means that start and continue executing the next lines and next line and so on. So that's what it's an asynchronous process. It doesn't wait for the start or process to complete or this thread to complete. That's why we need to wait for explicitly for these threads to complete before exiting the program. So this is how we do it. We have to do join on these threads. Just like start, we have to do join so that we wait for the threads to complete. So this actually executes all these things in parallel. Let's try running this now. All things will execute in parallel. 2, 3, 4, all 3 got printed all at once because they all waited for 2 seconds. Otherwise, each and every thing would have waited for 2 seconds. And then one by one, it would have printed. So this is using threads to parallelly run the program, calculate many things at once. This is for multiprocessing, multi-threading. Let's try using this for like 100 threads. How do I do that for 100 threads? Let's try running this program. Let's have a threads list for T in range 1, 100. Threading. Let's use I as a variable here. Threading.thread. I'm going to create a new thread. Target is long square, and args is the I command. And this thread, I'm going to add it to the threads list, threads.append. So the list can have any type of data structure inside it. So I'm storing thread as the data type in these threads list. So now we have created these 100 threads and added them to this threads list. Now I have to start those and then wait for those to complete. Similarly, for T in threads, T.start. This means for every thread that is stored in this list, I'm starting that thread. So for every thread in this list, I'm starting the thread. And similarly, for every thread in this, I have to wait for that thread to complete. So let's run this program. Python threads.py. So all 100 are going to run in parallel. So they all ran in parallel. If we had taken one by one, it would have waited for 200 seconds overall. One by one, it would have done. So the time it took when we did parallelization is only 2 seconds compared to 200 seconds when we don't use parallelization using threads. And this is one type of parallelization. So how about storing the results of this particular threads output? So we'll do that later once we see how multi-processing works. This is one type of parallelization. Threading is one type of parallelization. There is something called multi-processing. Processors.py. So what happened here is within the same program or within the same process, when I'm running this threads.py, I'm actually starting a process. So if I open one more terminal and do one more time Python threads.py, we'll start another process. So these two are two different processes. So the advantage with threads is that processes do not share memory. So let's say I define the value here, let's say results as a dictionary I have. I'm also going to pass this results dictionary to this long square. I'm also going to pass results. This is going to accept one more argument called results. So after printing, I'm going to append. I'm going to add results of x number equals x. So it's also going to store this value in the results dictionary. So at the end, if I print results dictionary, it's going to have retained that results, entire results. Let's try running this for 10 entries as a sample. So this dictionary is storing the results of all the multi-threading. So even though we are starting these threads separately and they all have the same context object called results. So this results object is shared in memory. So this is the advantage of using threads. Threads can share the same memory space as they are within the same process. So the difference between process and the thread is that threads share same memory space. So if a variable is declared in the program, that all the threads within that program will have that access to that variable or an object. So when I have processes, two processes defined, one process cannot access the variables of another process. Even though I'm running these as separate processes, let's say process, I will create one process. So this results object, if I run two threads, this files, if I run 2 times, those two will have their own set of results objects. They cannot share the same results object because they are entirely two different processes. It doesn't share memory. So using threads, when we are using threads, it's going to run within the same process and it's going to share, all the threads are going to share the same memory space. If I declare one variable in the program or in the process, that variable is available to the entire thread collection and within that process. So now we'll see how processes differ from threads. So there is a library called multiprocess in Python, which we can install with pip install multiprocess. This will help us spawn multiple processes. Usually what we did right now, I can actually go ahead and create one more Python exceptions or threads.py. That will be one process. One more terminal I can open and I can restart the same process. And those two becomes two different processes. And in this particular program, I'm going to spawn new processes within the same program. So this will be a parent process, and new programs, new processes will be spawned on the fly. And we should keep note that the processes cannot share the memory. Even though we are starting new processes from within this process, even the variables within this process are not available for the other process. So if I'm declaring other process and having a variable in there, that will have a different copy of values. Let's try doing that, creating multiple processes from this program. From multiprocess import process. Similar to threading, we are going to do this. Let's copy this code. I'm going to have this function create a new process. Instead of this, let's try creating processes. This is going to be processes dot append threading.thread we are using, but we have to use process in order to create a new process. Same arguments will get passed to the same this process also. Just that we are not using threads, we are using processes instead. So this will be, let's say, P, just to differentiate that this is a process. Let's run this. Process. Oh, sorry. This is going to be P is process, and instead of process, I should use only process. Let's run. Here we are spawning multiple processes, not one single process. So there is a workaround we have to do here because of OS constraints. Equals name. This is what we have to do. So what this name means, when I'm running this program from the console, the name of this will be equal to main. This is called a dunder, 2 underscores one after the other. So this is needed for running multiprocess in Windows. So we are spawning multiple processes here, all 10 processes together, and it's all executed. Now, if I see this print results and it's empty, so this process has declared results object as empty. And even though we are passing this to the process, it's actually going to create a new copy of this results object and pass it on to the new process. That process doesn't have the copy same reference to this results object. So these processes do not share this results object. It's a completely different copy of the object that is passed into the process. So when we have to do multiple processes that do not require shared memory, it's better to use processes. If we have to share memory, it's evident to use threads. So most of the times when we are processing server requests, it's all within the same process, which are spawned as threads. They all share the same system memory or the process memory, whereas processes, they run independently. So if I'm running independent jobs, background processes, that I can spawn with process module. If I'm running this process to simulate faster execution, we will use threads. So that's about processes and threads. Now let's look into processing files. Let's say in our operating system, we have, these are all files, right? How do I read and write files with Python? That we will take a look now. Files.py. So for reading and writing files, we just need to do open any file name. I'm giving a.txt as a file name. The second argument will be a string that represents what's the mode we want to open this file in. So this is R for read, W for write, and A for append. So if there is a file called a.txt, it will open that file in the read mode. So let's try reading this content. So whenever we open a file, we also have to close the file. So this is a standard way to read a file. Just try to print this, but there is no file called a.txt as of now. Let's try running this and see what happens. And it says file not found error. No such file or directory a.txt. So let's comment out this part. Let's say I want to write a new file called a.txt. I will do the same thing. Open a.txt with write mode. After that, f.write some text here. f.close. Let's run this file. It has created a new file called a.txt here. If I see it, some text here is printed inside the file. So let's run this program one more time. I'll have 4 more lines added. Let's run it. 1, 2, 3, 4, 5 lines. And it has 5, 1, 2, 3, 4, 5. But this has not added any backslash and characters, new lines. It's all showing up in the same line. So for adding the new line, we have to add a backslash n character. Whenever we add backslash n character, it adds a new line after the text. Let's run the same code. This time, if I open a.txt, it's all in the independent lines. So what happened to the previous line that I wrote? It got replaced by this new code, new text. So whenever we are opening a file in the write mode, it's going to replace the entire file. If I don't have this file a.txt, it will create a new file. And if it is there already, it's going to replace the entire text of that file with whatever we write here. So what if I want to append text rather than replace the entire text? So I can do that with f.f equals open a.txt. The append mode is used for appending to the end of the text. f.write some more text. I'll add backslash n. f.close. Every time we open a file, we have to close that. Let's run this. Let's go to a.txt. Some more text got added at the end of this file rather than replacing the entire file. If I open this in write mode, Let's see what happens. This entire content got replaced by these new content. So that's the difference between append and write. So let's run this code all together once. And it has written these texts here and appended this text here at the end. So now there is a shorter, whenever we open a file, we have to close that file also. So there is a shorter way to achieve this with operation, with open of a.txt, comma a as f dot write some more text here. So if I do this, I don't have to do explicitly close operation. As soon as this block is completed, this file gets closed automatically by Python. Let's run this. That's all. So this is how we write files, read files. So now let's read the file. I uncomment the first line, or I'll just rewrite that code here with the with syntax with open a.txt, read mode as f dot read. Let's do a print. Let's run this. Read the file and printed that text over to the console. This is how we read and write to the files. And last concept that we need to discuss is the modules. Let's say I'll create a file called use module.py. Let's try running a new file. Create one more file. I'll create one more file called rhymes.py. I'll create a function is rhyme. Let's say this finds out if this is a prime number, the past prime number is a prime number or not. It's none. It's just basic code from primes equals to the 0 and power 0.5 means the root of square root of this number that is passed. You have to check if any of the factors within the range is exactly dividing the number or not on primes. So none else on primes. So what we are doing here is, if we had found previous prime numbers, we can divide the new number with the previous prime numbers. If it is not divisible by any of the previous prime numbers, then it is a prime number. For each factor in these prime numbers, so this modulo operation will give us the remainder of this n divided by factor. If the remainder is 0, that is exactly divisible by the factor, so it is not a prime number. So it is not a prime number. If none of them is divisible, none of the prime numbers are able to divide this number exactly, then it is a prime number. Then n is a prime number. So let's try it one more function that lists all prime numbers till a maximum number. Let's have found primes equals into for n in range 2, 100. we'll calculate till 100, or as we are actually accepting that as an argument, we'll use max argument. For an inference, if is prime of n found primes dot append, we are going to save this prime number into the list for future reference. Return found primes. This will give a list of prime numbers up to a maximum range number. This is one file. I have written one file. How do I use this file in another file? So that is demonstrated here. If I have to use one function here, I have to import this primes module or primes file. I can do it through import primes. If this is with primes.py is within the same directory, then we can use import primes directly here. From here, I can actually call the functions that are listed in the primes file. Primes.is prime of 5. I can call this function. Let's try it. Execute this use module py, and 5 is a prime number it printed. So now let's try to import a specific function list primes from this primes.py. Let's do from primes import list primes. So I can exclusively import a specific function or a variable from a Python file. So let's list the primes and list primes of 20 up to 20. Let's list primes. So let's print them. So this is one way to import another file into one file. So if I have multiple files in a package or a directory, how do I make a directory as a Python module or a library or a package? All three are one and the same. Let's create a new module or a directory called numbers. So in order to make sure that numbers is a package, I should add a special file called init.py. As long as this file is there in a file in a directory, Python will consider this directory as a package rather than a simple directory. So in this, I will create one file called factors. Let's create a new function called get factors up to a number. For a particular number, what are the factors? I'll just return factor for factor in range 1, n plus 1 if n divided by factor is gives a remainder of 0. If we check this logic, I want a number that is from 1 to the number maximum number. Let's say I'm passing 5 here. So the range function gives a starting range of 1, and n plus 1 means it will give maximum number as n. So 5 if I pass here, it will go from 1 to 5. And for each of those numbers, it will divide that number divided by this 1 to 5. If n divided by 5 divided by 5 is 0, and 5 divided by 1 is 0. So 1 to 5, it will go through 5 divided by 2 will give a non-zero remainder, and so on. So if there is a non-zero remainder, it won't add it. If it is 0 remainder, then add that factor to the list, and gives the list of factors that are exactly dividing a number. So this is what the logic of prime numbers is. If the factors are only 2, the one and of n itself, if the factors of a number is 1 and itself, then that is a prime number. So that is what we are trying to find out here. So this gives us a factors. Let's create a primes.py file within this package. Let's import this numbers factors file from primes dot numbers dot primes import. What's the function name? Get factors. Get factors. Print get factors of 5. Let's try running this. Numbers primes.py. No module name numbers primes. But this cannot be called directly. So if I have to write it, let's create a function called is prime of n. Let's do get factors of n if factors equals the factors of n. If length of factors is equal to 2, and return true, or else return false. So if there are only 2 factors for a number, then it is prime. If not, it is not. So in the use module.py, let's import this numbers primes. So instead of this code, I'm going to use from numbers primes import is prime. Length is prime of 5. Now I'm going to execute this use module. I'm going to use circular import and second times get factors. Okay. Numbers are prime. No, we should use factors. Yes, this is wrong. We should have used numbers or factors here. Let's run this code. And that's returning true. So right now what we did in use modules is we have used this nested package, a package within the directory. So in the earlier scenario, we have just imported primes.py directly. In this case, we have imported a package, a file, and a function from a specific package called numbers package. So that's how the modules work in Python. If you go to the is prime logic, it is trying to get the factors, get factors 1 to n plus 1, which is 1 to 15. So any number is dividing 15. 3 also divides it, 5 also divides it. So that's not a prime number.
Okay.
So if the factors are only 2, so this condition checks if there is only 2 factors for a specific number. So there are like we can print the number of factors here, or we can just actually print the factors itself. Print factors. Let's run this. There are 4 factors for this. The factors are 1, 3, 5, and 15. Let's use something like 9 has 3 factors. If I use 7, so it's all mathematics and just deducting a logic from the code. So that's about the basics of Python.